Good morning, everybody. Welcome to the IEEE Young Professional Pitch Competition. Are you able to hear me? Please give me some feedback.
Yeah, Vincenzo, we hear you.
Okay, so first thing is done. So we're gonna start in 5 minutes as scheduled by the conference webpage. Okay, so good morning, everybody. Let's do a quick introduction to young professionals. As yesterday, very short presentation, and then we start with the competition. Okay. So I assume you can see my screen. So
Yes.
young professional, I mean, as just said yesterday, today there is me, the vice chair, and Davide, who is the treasurer, together with us.
Hello.
And
Hello, everyone. Welcome.
on behalf also of the chair and the secretary, we, let's say, welcome you to the Young Professional Affinity Group. Unfortunately, they cannot join us today, Federica and Elisabetta, but me and Davide will try to take their role as best as we could. So other email you may want to know is, let's say, those are the general mail for the full, let's say, for the whole overall IEEE organization, so the worldwide ones. I suggest you to start sending us an email and then move to this one if you want more, let's say, broad information. But who we are an affinity group that is a non-technical subunit of a region. So it's neither a section, is neither a chapter, is a group of people within the IEEE organization which share together some interests, which are, for example, to expand, let's say, their global network, to connect with other people in the same situation as them, that is, to be graduated, let's say, from no more than 15 years, for no more than 15 years, which means you have, let's say, you can make the computation about the lifetime, about the age, the average age of the young professional. And so people that are the beginning of their careers, and from this name, young professional, and that want to, let's say, to improve either their technical skills, so to participate at the event, to be connected with experts, or to make just more, let's say, be part of a community which can provide them network of people which can, let's say, help them in their work or in their personal, let's say, lifetime. At the very end, of course, the last but not least point of being, let's say, young professional is also give back something to the community. So what you learned during your previous part of the first part of your career can be, let's say, brought back to the community with seminar, events, mentorship, and so on and so forth, which of course will help you to elevate your professional image. And this is the very high level goals, that is to put people together will, let's say, improve everyone at the very end. So to increase your career goals, to polish your professional image, create, let's say, the basic blocks of a lifelong and diverse professional network. So this is something we believe as young professional as an opportunity to be taken, and I hope the people that are with us today will also participate in the future to the, let's say, more actively to the young professional program. As I told also yesterday, there is many funding opportunities for event. It's very simple to apply. First of all, you send us basically an email to the people to the email that I sent you before. So basically send us an email telling we want to organize this event, this seminar, this whatever, this award, this hackathon, this you may imagine different thing, and we can, let's say, help you to organize it and give you some advice on how to do it, and maybe some funding if we are able to. And also, finally, we are basically the natural extension of student branches. So if you are part of student branch, or let's say you were a student branch before, you were, let's say, some also committee member of a student branch, remember that after student branch, remember that ends whenever you finish your, let's say, your student path, you can become immediately a young professional and continue your experience with IEEE. And also, even if you're still part of the student branch, we can organize event together. We already did it in the past, so we can imagine some kind of cooperation together. So after this very brief introduction to young professional, I think we can start with with the word competition. I do know that Mr. Micheli was asking to be the first one. So we're gonna start from him.
Yeah, thank you very much.
Okay. Okay. So first of all, we're gonna share the full screen. No, share. Okay. Eccolo qua. Wearable sensor. Okay, I'm not sure you're able to hear my screen.
Good morning, everyone. I'm Umberto Micheli, a PhD candidate at the University.
I can, Vincenzo. I can hear you.
So if I play, you're able to.
Yeah. It's okay.
While if I go to the full screen, you're still able to see the full screen.
I'm seeing the full screen now.
Okay.
Try to run. Let's see if we hear the voice.
And today I'm going to tell you
Okay,
about.
it's working. Okay, thank you.
Let's start again
Good
from
morning,
scratch.
everyone. I'm Umberto Micheli, a PhD candidate at the University of Padua. And today I'm going to tell you about my research outlining why it's extremely useful in wearable smart devices in the real world. In deep learning models across different semantic groups, domains, and devices. Let's take an example of a use case on the next generation of smart glasses. It is nowadays understood that the next generation of smart glasses will have many different sensors and also one or more cameras. These glasses will then be used for a variety of augmented reality applications ranging from marketing, game industry, healthcare, virtual navigation, and so on and so forth. To achieve this, it emerged a crucial requirement of deep and automatic understanding of the surroundings, which can be achieved by a semantic segmentation. Semantic segmentation is a dense prediction task in which every pixel is assigned to a class label, thus enabling pixel-level understanding of the scene. Current state-of-the-art approaches use deep learning architectures to address the task. However, such algorithms have some major limitations when employed in the wild. First of all, they heavily suffer from domain shift. The model is trained on a source domain, which can be as much variable as possible. However, it is inevitable that at test time, each user will see a different domain distribution based on their interests and behaviors. Second, current algorithms assume that the label set is predefined and not updated. This is another great limitation since we would like the model to adapt to the classes of our interest. For example, if we train our model to recognize dogs and cats, the model will become very good in addressing this task. However, when prompted to an unknown class of interest, it will give a completely undesired answer. For example, the border is predicted as a dog, with high confidence. If we were to naively update the model by fine-tuning its weights instead, we would be able to address the new task, while significantly forgetting the previous ones. The bird now is correctly identified, while the prediction of dogs and cats have dramatically worsened. Third, another common assumption regards the centrality of the data for supervised training on a central server, which can see the overall data domain distribution. Users should then send their acquired data to a central server, which will update the model, raising several privacy concerns. My research lies at the intersection of these foundational AI problems in dense predictive tasks to empower the next generation of smart sensors. First, in order to have smart sensors which can adapt to the domain each user experiences, we are working on a supervised domain adaptation techniques. The goal here is to align the domain distribution of the source and target domains in a completely unsupervised manner, without seeing any labels coming from the target domain. We are developing strategies to align them at the input, at the feature, and at the output levels. At the input level, we increase the similarity between source and target samples via style transfer techniques. At the feature level, we force class-wise feature alignment between the features extracted from the two domains. At the output level, we reinforce learning on the target domain by increasing the confidence of the network predictions made on the target domain. Second, in order to have smart personal devices which can learn new tasks without catastrophically forgetting previous ones, we are researching lightweight continual learning methods that can effectively find a trade-off between stability for preserving previous tasks and plasticity for learning the new tasks. In this context, we extend the knowledge distillation to transfer knowledge of the previous tasks from the old model, while updating the new model. The key idea here is to maintain the response of the network as close as possible to the response that the network had in the previous approaches to preserve the encoding capabilities of the model for what concerns previous tasks, while at the same time leaving enough geometrical representation in the intermediate feature space to learn new concepts. Finally, we propose replay approaches, which can recreate samples to maintain previous knowledge by retrieving weakly supervised images either from a GAN or from the web. Third, we wanted to address data privacy issues in sharing data with a central server, while at the same time allowing the model to be updated with data acquired from the end users. This is where federated learning comes into play, where a central server first deploys an initial model to the end users, then users can update the model on their local data and send only model updates to the server, which aggregates the solutions. The procedure is iterated until convergence and no data leaves the device at any time. Since, as we mentioned, each user will likely see a particular domain distribution due to their particular interests and behaviors, we first analyzed how data non-IEEE negatively affects federated optimization, and we proposed a novel aggregation approach which is fair from the user perspective. Then, we further improved the solution by building a feature-driven optimizer which aggregates models, bringing awareness of what each model has learned. Wrapping up, my research focuses on foundational AI problems where we want to make models generalized within domains, personalized with new categories, and trained in a decentralized fashion. Such algorithms will likely be shipped with the next generation of smart wearable devices.
Okay. So now it's question time. If anyone from the audience has some question, you are free to, let's say, unmute yourself and pose the question to Mr. Micheli, who is here to answer your doubts. Anyone? Don't be shy. Okay, I have one. You tell me, let's say, it's the architecture you propose is, let's say, can be embedded, as I said, in, let's say, in wearable sensors or maybe smartwatches or something like that. I assume from what you said at the very last time. Have you already tried to do some sort of application to, let's say, wearable sensor, either someone you have, let's say, designed on your own lab or, let's say, a group, or in some existing ones?
So thanks for the question. And so at the present time, we are currently investigating which are the foundational problems we would like to solve and proposing study algorithms in order to address them. And in a later stage, so for the moment, it's just prototypical stage, right? Because we are just trying to propose new algorithms in order to solve the tasks. And then the next step is indeed putting everything all together. So it's like in a puzzle, we want to embed all different aspects that we want to address, and later then to go into the deployment stage. So the bottom line question is yet, but we are starting to do it now.
Okay, thank you very much for your time,
Right.
your speech. We can move to the next one. Which is Mr. Sara Baldoni, if he's here with us.
Yes, good morning.
Okay, let me share my screen.
Good morning, everyone. I'm Sara Baldoni, a PhD candidate at Roma Tre University, and today I will present a part of my research activity. During the last years, we witnessed a rapid development of the telecommunications sector, which led to a growing dependency upon its services. This does not hold only for final users, but also for service providers and critical infrastructure. In the meanwhile, the security threat scenario is continuously evolving, thus leading to increased performance and security demands. During my PhD, I designed a flexible security framework which exploits the contextual information in order to satisfy both operational framework which jointly processes distributed and local context is currently missing. The idea is to exploit a set of specially distributed information sources that provide their measures to the distributed context building blocks. Distributed context represents what happens around the monitored system, and this information can be employed in order to detect anomalous behaviors of the monitored system. In addition, the information provided by different sources could be separately processed, or they could be combined, both considering sources of the same kind or different in nature. This information can then be integrated with the one coming from the local context. Local context represents what happens in proximity of the monitored system, and it is environment dependent. Thanks to the integration between the two types of contextual information, it is possible to identify the anomaly cause and to suggest the best mitigation strategy in order to satisfy both security and performance requirements. I applied this framework to different case studies, one of which is the positioning scenario. According to the WSAIM market report of 2019, the accuracy requirements for positioning systems are becoming stricter and stricter, going from centimeter to meter level, depending on the application. In order to satisfy these requirements, however, two kinds of hazards have to be overcome, which are global and local. Global hazards are undesired effects with high spatial correlation, and they are usually mitigated through the use of augmentation networks. These networks are made of a set of ground reference stations that provide localization corrections to users. Local hazards, on the contrary, are undesired effects with low spatial correlation, and for this reason, they cannot be mitigated through augmentation data, being environment dependent. In addition, to properly mitigate the global hazards, the security of the augmentation network has to be guaranteed. Among the possible security threats, I focused on spoofing, which is one of the most powerful and tricky. Spoofing consists in creating a fake satellite signal, which in this case is directed towards the augmentation network so that the correction will be altered, and so will be the final position estimated by the end user. This is a representation of the proposed framework applied to the positioning case study. The reference stations provide their measures to the distributed context building block, where a spoofing detection and mitigation algorithm is deployed. In this way, only the reliable information is provided to the integration building block, thus mitigating the global hazard. Then also the information coming from the local context is acquired thanks to the use of onboard visual sensors. Thanks to the use of the local context, also the local hazards can be properly mitigated. The two types of contextual information are integrated to reach two main objectives. The former is the enhancement of the availability of high accurate position information in scenarios in which the satellite-based systems have poor performances, such as the urban environment. The second one is the enhancement of the integrity of the position solution, thus providing more reliable position estimates. To conclude, the proposed framework is flexible and can be applied to different case studies by modifying its building blocks. Concerning the considered application scenarios, it provided promising results, and another interesting thing is that the building blocks can be employed separately or jointly, depending on the specific application needs. I thank you all for your attention, and here you can find my contact.
Okay.
Good morning, everyone.
Okay. So, Mr. Baldoni, hope is here. Well, we did so. Okay. Okay. So, any question from the audience about the Okay, I have one. Okay, which thing what do you think is the most critical aspect about, let's say, your research you need to tackle to be sure that you can have, let's say, something that is effective so that your technology can be somehow adopted somewhere?
Okay, maybe the most critical thing is to model all the is the integration among the information coming from the several sources and coming from the distributed and local context building blocks in order to properly analyze the risks associated to the current situation so that the proper mitigation strategy can effectively be selected.
Okay. Any other question from the audience? No, so thank you, Mrs. Baldoni. We can move to the next speaker. David Rodriguez Duarte, want to be the next one? Yes, you can be the next one. So let me share the screen.
Hi, I'm David Rodriguez, and today I'm going to talk to you about my research, electromagnetic device for cerebrovascular disease imaging. Knowing that applied research requires interdisciplinary work, during my PhD, I collaborate with academic institutions, industry institutions, and of course, because of my topic, with health institutions. During this time, I published 4 journal papers, participate in more than 10 international conferences, and get second prize in one. But also, we know that research has to inspire. And because of that, I also participate in communication activities like the Futuro Remoto, Bienale de la Tecnología, Notte di Ricercatori, Festivale de la Tecnología, between others. Now that you know a little bit about me, let me explain the motivation behind my work. Cerebrovascular disease are diseases that affect vessels in the brain, and normally there are 2 kinds, ischemic and hemorrhagic one. In one case, you have a block, instead in the other one, you have a burst. But are those important? Actually, yes, they are the second cause of death worldwide. From the people who suffer one, 25% die. And from the survival, 25% get a disability. And from those, only 25% get full recovery. So it's a very important issue. So, looking at the medical need, the physician requires a device that is able to detect, classification, and also the continuous monitoring of the pathology. The 2 first are also solved right now, solved with the golden standard techniques like MRI or CT, but the continuous monitoring is still a need. So, this is the point where my research gets more importance. Then the current techniques, MRI and CT, are time-consuming, not portable, costly, not available for the bedside monitoring, and there are also harmful because in the case of CT, use ionizing radiation. So in my thesis, I'm proposing use microwave imaging. This is a complementary technology that could help us with these problems. So the principle behind microwave imaging is in the contrast that present, in our case, the healthy tissues and the stroke affected one. That means that the permittivity of the average brain is different from the permittivity of the hemorrhage or the ischemia. A normal microwave imaging system is going to be something like this, and an array of antennas that you put around the head where the antennas can act like a pulse transmitter or receiver. Schematizing the core of microwave imaging system, we have something like that. As a simple, we have an electromagnetic model that gives us the field in a nominal condition. In the other hand, we have the scattering parameters that we take into different conditions. That means that we can follow up the growing up or the stringing of the stroke. Those are immersed in an algorithm that at the end gonna retrieve us the contrast. That is the factor that we are interested. Then to apply the microwave imaging, we have a system like this that consists of CRISPR. In the left, we have the VNI. In the middle, we have a switching matrix. And in the right, we have the array of antennas. The switching matrix, who is in the middle, is going to act like a multiplexer between the 2 ports of the VNI and the 24 ports of the antennas.
I have lost the audio, Vincenzo.
I think it's
don't know.
muted.
To do that in the experimental setup, we implemented like area of recover all the of the antennas.
Yes, from there.
Okay, so if I mute my microphone, also the rest is muted. Let me see if I can share the computer sound in a more clever way in a second.
So we recover the information from each one of these antennas, where the antenna is a monopole that is immersed in
It should
this
work now, right?
brick that is acting like a coupling medium and allow us to improve the penetration and the resolution of our algorithms. Later of recover all the data, we apply them to the imaging algorithm that we present at the beginning and recover a 3D image. So the microwave system is going to try to follow up clinical scenarios like the one in the left, where you have a growing up of the stroke, and try to get the differential contrast in the middle. To do that in the experimental setup, we implemented these two scenarios, one empty head that mimics the healthy tissue, and later we put a stroke inside, but let me explain more about that. We implemented different testing scenarios using an homogeneous head filled with average liquid, but also with a multi-tissue head where we put an actual brain made of calf's brain and do different experiments. So after recover these parameters, we can apply them to an imaging algorithm and retrieve the imaging. This is a 3D imaging that indicates to the medical staff where is the stroke, and he is showing up the progression of the stroke. There is still many work to do, and for that, we have developed the second version of the system. This is a version that is more flexible, lighter, and less bulky, so it's closer to a preclinical prototype. Also, knowing that we wanted to test with more realistic fandom, we work in collaboration with health institutions to develop a more realistic fandom that they are able to change on time, so making more realistic our experiment. As our first test, we tested with an homogeneous head and do the monitoring in real time of a stroke that is changing the volume between 5 to 15 centimeters. As we know, this is the first real-time monitoring. With this, I'm concluding this work. I'm David Rodriguez, and in this work we move from the theory to the real implementation of a microwave imaging system for monitoring the brain stroke.
Okay, welcome back. Thank you for your presentation. Any question from the audience who want to maybe ask some question to Mr. Rodriguez Duarte?
I have a question.
Right?
Sure.
I did not understand very well. So the novelty is in this work, I mean, it's not the MRI per se, because I think that is technology already known, is the fact that it's real time.
No, MRI is just, we take it for comparison. Actually, we are using a different technology that is based
Okay,
in
no, because I did not understand. So can you explain it again? Thank you.
Sure. No worries. Yes. So what we do here is a new technology that uses microwaves and could be used complementary to MRI. We are not trying to replace that, but this is a technology that works in a frequency of microwaves, so around gigahertz, that also is used for do the imaging. The special thing of this is that if you consider the technologies that they are right now, like a CT scan or MRI, they are not able to do real-time monitoring. In the case of the CT, it's because you use ionizing radiation. So if you use ionizing radiation, it's dangerous for the people, for the patient. Instead, if you try to do MRI,
they takes time. And if you consider in a normal hospital, you maybe gonna have just one MRI. So you have to put all the patients, you need to treat all the patients with the same MRI. With our technology, we are implementing one system that is gonna be compact. So also gonna be cheap, so, and could be put it in the bedside of the patient. That's, I answered the question.
Okay, yes, it's much more clearer now. Thank you.
Thank you for the question.
Okay. I see that Mr. Shane Steinberg has raised a hand.
Yep, I have a question. So
yes,
I think based on your video, you're proposing a kind of like a wearable sort of headset that emits the microwave radiation for the continuous monitoring. Is that correct?
Yeah.
So I'm wondering, like, what is the safety of continuously sending these microwave signals into the subject's brain? Thanks.
Sure. So because we are working in microwaves, and also we are using a very low power, like is in comparison, it's less power than the power that use a cell phone. It's totally safe. You can use it continuously without any problem. We are not working in a range that could be affect the cells of the tissues. So you can use it as much as you want. That's the advantage, and it's totally safe.
Thanks.
Thank you for the question.
Okay, if there are no more questions, we can move to the next one. Many thanks to Mr. Rodriguez Duarte for his presentation.
Grazie, Vincenzo.
So let's go to the next one. Let me share my screen. Okay. And we can go with Mrs. Nuzia Molinaro is here with us. Please give us a feedback.
Yes, good morning, everyone.
Okay, so we can play. Okay. So, any question for Mrs. Molinaro from the audience?
Yes, I have one. I'm curious to know what were the conditions where you performed the test, because I suppose that maybe the positioning of the person, let's say under test, has an effect maybe on how the system is performing, if the person is moving or not, if it's laying down.
Yes, the tests were performed in a stable position. Even if and we are trying to do other tests, trying to simulate motions artifacts and test the performance of the systems in detecting these movements. But the position of the user is important, because the signal that I extract from the video can be affected by these motions artifacts.
Okay, thank you.
Okay, so thank you for your presentation. Let's move to the next one. Okay, so Mr. Shane Steinberg, sorry if I miss the correct pronunciation of your name. I assume you're still with us. Is it true? Please give us some feedback.
Hi, yes, I'm here. Thanks.
So let's start it.
Hello, my name is Shane Steinberg. I'm a PhD student in computer engineering at Carleton University. Today I'll be talking about our lab's recent research on the development of a wearable single-element ultrasonic sensor for continuous artery monitoring. Ultrasound is a commonly used imaging modality, as it is non-invasive and can be used to quantify the viscoelastic and dynamical properties of the artery tissues. Using these properties, local blood pressure estimation and quantification of risk indicators for cardiovascular disease may be obtained. This includes assessment of the degree of atherosclerosis, a leading cause of death worldwide. The conventional ultrasound imaging probe is prone to motion artifacts and operator variability that can affect the tissue dynamics and cause misinterpretation of the physiology. To avoid these issues, we propose a wearable single-element ultrasonic sensor for continuous artery monitoring. Using the wearable sensor, the artery diameter changes over the cardiac cycles should be automatically tracked for subsequent estimation of the local blood pressure and artery stiffness. The sensor was connected to an ultrasonic pulsar receiver that was triggered by a function generator. For each trigger event, the analog digital converter was also enabled to digitize the received signals. The wearable sensor was operated using the pulse echo technique, as shown in the figure on the right. The sensor was electrically excited using impulses at regular intervals. Pulsed ultrasound was emitted by the sensor, and the received echo signals were digitized and saved. The unfocused plane wave ultrasound emitted by the wearable sensor introduces more scattering echoes in the received ultrasound signals. The illustration on the left shows a signal model of the wearable sensor for artery monitoring. The larger surface area of the sensor introduces a high volume of scattering echoes from tissues surrounding the artery. On the right, a signal model of a conventional array used for ultrasound imaging is shown. The focused beam improves the lateral resolution, reducing the amount of scattering echoes in the received signals. The top left plot shows a signal acquired from the carotid artery using the wearable sensor. On the right is a signal acquired using the conventional focused array. The artery echoes are obscured when using the wearable sensor. The bottom images show a succession of signals acquired over time. The fluctuations of the echoes contain the motion of the artery walls over the cardiac cycles. A matching pursuit signal decomposition was proposed to address the issue of the high volume of scattering echoes in the signals acquired using the wearable sensor. Each acquired signal was decomposed using a mathematical model of the ultrasound echo and prior knowledge of the spectral characteristics of the sensor. The artery wall was isolated by identifying the parameters of the echo model using prior knowledge. Then the isolated wall echoes were tracked using the signal model. The figure on the right shows the estimated near wall displacement of the artery over 4 cardiac cycles using the proposed method. Signal features associated with the blood pressure waveform are present. In conclusion, artery wall tracking was demonstrated using the wearable sensor. A signal decomposition approach was able to isolate and track the artery wall echoes among the high volume of scattering echoes in the signals received using the wearable sensor. Future research will evaluate the accuracy using a reference measurement with increased number of subjects. A fully automatic artery wall tracking method will be developed using machine learning and features of the decomposed signals. The excitation electronics will be fully developed for a wearable device. Thanks.
Okay. Any question from the audience? No. So thank you for your pitch. Let's move to the next one. Which is Mr. Camuffo, Mrs. Camuffo 1 is here with us. Please give us feedback.
Yes, good morning.
Okay, so let's quickly start it.
Good morning to everyone. My name is Elena and I'm here to present you my research in 5 minutes. Well, my topic is curriculum and contrastive learning in LiDAR semantic segmentation, and this project have been developed for my master thesis. LiDAR semantic segmentation is a computer vision task that provides fine-grained scene understanding, taking as an input some three-dimensional data points and identifying some meaningful objects inside the scene. It finds application in many fields, for example, in autonomous driving. And it is usually tackled with deep learning methods. For this project, we have selected a large-scale dataset for autonomous driving, namely Semantic Kitty, and a well-known deep learning point-based model, which is RandoNet. RandoNet architecture is structured as an encoder-decoder, taking a raw point cloud as an input and providing semantic labels as an output. It have been trained with the standard configuration, and the output have been analyzed jointly with the dataset in order to provide some considerations and to choose the best method to train the model in order to improve the performances. Using some clustering techniques on the confusion matrix produced with the standard training, we have found that the classes inside the dataset can be grouped in 4 macro categories, and this subdivision have found to be very useful in order to be included in the training procedures and improve the performances of the model. In particular, we have found some methods that we are going to present that improve these performances. The first one is to include a regularization term in the loss function that is a cross entropy on the macro categories. Another method we have tested exploits a coarse-to-fine training scheme that provides a 2-stage training of the network. The first one, a coarse training on the macro classes, and the last one, fine-tuning on the micro classes. The last method provides the use of the Jane's Fairness Index, computed separately on each of the macro classes and included as a regularization term inside the loss function. If we look at some results, we can see that the coarse-to-fine training scheme, as well as the hierarchical loss function, provides a better subdivision inside the 4 macro categories, as you can notice from those confusion matrix in comparison. Another important result of our methods is an improvement of the mean intersection over union measurement. In particular, you can see here that the fairness improves not only the overall mean intersection over union, but also the per class mean intersection over union, in particular on the least rated classes in the standard procedure. This means that in the fairness test, the classes are more balanced. I will present you some qualitative results. You can notice from this example here that our methods achieves even better qualitative results. In fact, looking at the building and the other vehicle inside the red circle, they are misclassified with the standard procedure with respect to the ground truth, while with our methods they are correctly classified. In conclusion, we can say that our methods achieve better results in terms of macroclasses classification and a better balancement of the classes. Our methods are, in addition, even faster and better in terms of mean intersection over union with respect to the standard configuration. For future works, our purpose is to focus also on the feature level and to generalize our methods by changing the dataset, the architecture, and even the task. That's it. Thank you very much for your attention.
Okay, many thanks. Any question from the audience? Doesn't seem so, so we can move to the next one. Many thanks, Mrs. Camuffo. We can go to Mr. Mari, is with us, Daniele Mari.
Yes, good morning, everyone.
Okay, so let's play the video immediately.
Good afternoon, this is Daniele Mari from Università degli Studi di Padova, and I'm going to present to you my research work entitled Syndrome-Based Autoencoder for Learn Point Cloud Coding. The aim of this work is to develop a codec for point clouds that is able to compress both geometry and attributes. The current implementation is based on deep learning and on the distributed coding framework. The main idea of this particular framework is that the receiver is already in possession of a signal called side information that is highly correlated with the one that the sender wants to transmit. For this reason, the latter just has to send some correction bits called syndromes that the receiver will use to correct the side information to reconstruct the original signal. What happens in our codec is that the point cloud is preprocessed, then it is downsampled and encoded using TMC13, that is the standard MPEG codec, and transmitted to the receiver where it will act as side information. Then a deep learning-based autoencoder is used to produce the syndromes that are sent to the receiver and are used to reconstruct the original point cloud. More in depth, what happens during preprocessing is that the point cloud is voxelized, meaning that it is displayed into a grid where it can be processed by convolutional neural networks, and then it is partitioned into blocks that are encoded independently. For this reason, this approach is very efficient because it is highly parallelizable. The network needs fewer parameters with respect to the one that it would need to reconstruct the whole point cloud, because the task is actually simpler, and it is also hard to overfit because from a single point cloud we can obtain multiple blocks. That means that we have a bigger dataset for a simpler task. For what concerns geometry, we have compared our work with other two state-of-the-art approaches that use deep learning, in particular the one proposed by Guarda and the one proposed by Wang. In order to do so, we computed the beyond-the-guard rate difference. That is a metric that is used to understand how much a codec has improved with respect to another one. All three approaches were compared to TMC13, and it is possible to see that our work performs better than the one by Guarda, but not as well as the one by Wang. For what concerns attributes coding, to the best of our knowledge, not much has been done in order to use deep learning to solve this task. So we had to introduce some new techniques. But unfortunately, the overall PSNR of the codec is lower than the one outputted by TMC13. This is due to the fact that our codec is not very good at reconstructing high-frequency components. But in general, one might argue that considering 2 point clouds with similar sizes, one reconstructed by TMC13 and one reconstructed by our codec, one might say that our is actually visually better because of the fact that it is much denser and it doesn't have any holes in it. But when we compare it with a model reconstructed by TMC13 with similar density, we can actually see that it is a lot smaller in size, but as previously mentioned, the high frequency components are a lot less sharp. So in conclusion, we actually developed a framework for geometry coding that actually rivals other state-of-the-art approaches. Then we also introduced some techniques for attributes coding, and as a matter of fact, our codec is able to compress color, but it is also easily extendable to other attributes that are normalizable in the 0-1 range. And finally, we also analyzed the neural network in order to make sure that it was working as intended, because of the fact that in general, it is very easy for the network to just learn to interpolate the set information and not to learn to perform reconstruction. For future improvements, a good idea would be to improve the rate control, since right now it is only possible to reconstruct a certain amount of different qualities for the point clouds. And in general, it might be a good idea to test this approach with bigger block sizes in order to try to obtain better performance. Then a good idea would be to divide geometry coding and attributes coding, as is done in TMC13, while in this approach they are encoded together. And finally, it would be a good idea to try the distributed coding approach also for other types of point clouds, such as the dynamic ones. This is the end of the presentation. Thank you very much for listening.
Okay, any question from the audience? Doesn't seem so. So thank you, Mr. Mari, for your presentation. We can move to the next one. Mr. Breen Loftness is here with us.
Yes, I'm here.
Okay, so we can start your presentation. Okay.
Hi, my name is Bryn Loftness. I'm a complex systems and data science doctoral student at University of Vermont in the United States. And today I'm going to be discussing with you my research project developing novel techniques for assessment and digital phenotyping of childhood internalizing disorders. Anxiety and depression, which are two internalizing disorders, are chronic conditions that start as early as preschool years and can impair a child's relationships, development, and functioning throughout their entire life. Children with internalizing disorders, where symptoms often go unobservable, are less likely than those with externalizing disorders to be identified as needing professional assessment. Current screening is currently entirely reliant on kind of a gold standard parent report questionnaire, which relies on observable childhood symptoms and takes additional time for staff to interpret and score these gold standard assessments. Given these barriers and extreme limited access to expert clinical assessment in many areas, pediatricians urgently need objective, accurate, and most importantly, low-burden tools for detecting anxiety and depression in young children. So for our project, we aim to create, like I said, a more objective, standardized screening, which relies on not external informants, but actually the child's physiology. We've been using several wearable sensors and mobile technologies, which we've developed to try and create a new system that's more data-driven to identify physiological markers that are specific to kids with internalizing disorders, which can help us identify kind of that digital signature for a child with an internalizing disorder, which would be the digital phenotype. The project is broken up into 4 separate behavioral assessment tasks. The first task is the approach task, which resembles a potential threat scenario. The second is a speech task where the child is asked to give a 3-minute presentation, and this represents an acute threat. The third task is a bubbles task where the child gets to play with bubbles and we get to see those positive responses associated with a reward response. Next is a reward task where we stand in front of the child and say we're about to give them a toy and then wait about a minute while we kind of build that anticipation for the child. These behavioral tasks have all been tested through previous studies in our group to see if we can do a similar kind of methodology of creating a machine learning model based on what we see between children who are affected with internalizing disorders versus children who are not. And now for this study, we're putting together all 4 of these tasks. And so through these different behavioral tasks, we collect gyroscope, accelerometer, speech, muscle sensing, EDA, as well as ECG and surface temperature to see through these different mood induction tasks how their physiology really changes, and through all these different signals, what are the signals that really show best and are the greatest indicators for changes in physiology. From these signals, I create a machine learning model that extracts these digital signatures, these digital phenotypes, and identifies them like I was kind of referencing earlier. And then we compare our model to the standard assessments, which each child in our study does get. So from this machine learning model that I'm in the process of developing for this kind of array of behavioral tasks instead of just the individual tasks like we've done in previous research, is we're trying to create an open source software package that includes a phone app that we are developing that pairs with whatever sensors we find give us the best signal, and then make that an available and open source thing that, you know, pediatricians from across the United States and hopefully eventually globally can use as a supplement or in lieu of these long, not so objective procedures, this gold standard assessment that doesn't actually rely on the child. And for internalizing disorders where a child may not be showing symptoms, really does identify more children early on to provide that early intervention, which is what we would want. You obviously can't ask questions. I wish you could. But just to kind of recap, I went over how we're leveraging different signal processing techniques with machine learning to identify a digital phenotype of childhood internalizing disorders, and really using these new advances in digital health to create a new, unbiased, objective procedure for early intervention of these childhood internalizing disorders. Here's a few references to our previous studies identifying the differences in just one of the behavioral tasks and the body signals. I hope you enjoyed and learned a little bit about my research here at University of Vermont. Thank you.
Okay, any questions from the audience?
Actually, I have one. It's just a curiosity.
Great, yeah, go for it.
Yeah, how can you I show my video so it's a bit better, right? Okay, I mean, how can you identify that that a person, for example, has some disorders or not? I mean, do you have a kind of data set of people, in this case, children that have particular symptoms and they are already classified as, because, you know, for psychological illnesses, it's not as simple as another kind of illnesses. So that you can say, okay, these are, it's kind of, I don't know, just for curiosity.
Yeah,
It's not a really clear difference. Okay, you can say ill or not ill. So that's my doubt.
Right. That's a great question. So for each of our children that come in for our study, we collect not only their physiological responses through the different behavioral tasks, we also put them through the typical kind of standard diagnosing procedure called the KSADS. And through the KSADS, that's kind of a series of surveys and assessments that the parent takes of observable child symptoms. So basically like what the parent has observed over time, and then everything is kind of diagnosed on a scale. And so if they see like certain tendencies towards anxiety or kind of apprehension in certain scenarios and stuff like that, we kind of build our system not to be a yes or no, they're experiencing this disorder, or something like that. It's more, signals are more related to children on this kind of area in the spectrum versus not at all. And so we validate our machine learning model with those standard assessments to kind of use it both ways, because currently all we have is the standard assessment. So definitely a great question, and it's definitely not black and white. Are they experiencing this disorder or not, and to what degree? So that's a great question.
Okay, cool. It's fine for me.
Okay, thank you for your question and thank you for your answer. I would move to the next one so that we can stay on time. Thank you for your presentation. Okay, Mr. Gustavo Gonzalez is here with us.
Yes, I'm here.
Okay, let's start.
Hello, I am Gustavo Gonzalez, PhD in Materials Science and Technology, and I would like to give you an overview of my works based on developing new polymeric materials for a point-of-care device by 3D printing. What if I told you that soon we are going to be in a world where almost any biomedical component can be produced for specific patients in nearby hospitals? What if devices for medical analysis can be produced in remote areas with economic difficulty? Actually, this and much more could be possible using 3D printing. 3D printing is a set of techniques that allow us to produce objects through the sequential addition of materials starting from a digital model. 3D printing enables to create complex geometry parts in a few minutes, and the interest in these technologies is so huge that only in 2020 around $20.2 billion were invested in this technology, and it is expected to be $63.5 billion in 2025. Among all the different materials used for 3D printing, polymers is the most used materials thanks to their low cost and simplicity of processing. And indeed, using polymer materials, we can produce other objects like those shoes, prosthetics, and much more. And the current pandemic situation shows us how the technologies can be immediately of big help, even in an emergency. However, looking to increase the number of possible applications, especially for the biomedical field, we need new materials that meet some of the basic requirements in the biomedical sector, like biocompatibility and antibacterial properties. And here is where my research is focused. My studies aims to develop new polymers, specifically photopolymers for 3D printing. Photopolymers are made up of liquid substance which solidify quickly in the presence of light. These materials is already used daily in various applications for nails and dentists. So 3D printing machines based on this principle of photopolymerization can be used to produce complex shapes and precise objects. Here, by mixing the adequate ingredients in the liquid, we can produce parts with the desired characteristics. For example, one of my works was focused on developing devices with functional properties given by using main chemical components to induce antibacterial effects. In this way, we can produce parts with antibacterial killing effect up to 94%, which can be potentially used in hospitals to decrease the risk of infection in patients. In one of our last works, we developed a series of polymer devices that can control the bacterial proliferation in environmental conditions. This type of device can be useful for microbial fuel cells, for example. Additionally, we have created and tested three-dimensional microfluidic systems to carry out automated biological studies to study drugs for cancer cells. And this device can be used to analyze substance on a much smaller scale than current protocols, saving time, cost, and specialized operators work in laboratory. The idea behind my research is to expand the range of functional polymers for biomedical applications and thus contribute to the development of intelligent devices that can be integrated with electronic elements for fast and accurate medical analysis. So thank you very much. My name is Gustavo Gonzalez, and thank you again for your attention to my research. Thank you.
Okay, are there any questions from the audience? No. So we can thank you for your presentation, Mr. Gonzalez. We can move to the next one. Mr. Simonetto, Adriano Simonetto is here with us.
Yes, I'm here.
Okay, so we can start your presentation.
Welcome everybody, my name is Adriano Simonetto and today I will talk about multipath interference correction for indirect time-of-flight images. Here we have a brief overview of what we're going to see today. So we will start with an introduction to time-of-flight, and we will then explain what multipath interference is and what we try to do in order to remove it, only to finally show, of course, some experimental results. So first thing first, what is a direct time-of-flight camera? Well, this is some kind of device that tries to recover the depth information of a scene by sending a very narrow impulse of light towards it. At the sensor side of things, what we do is just compute the time of flight, so the time it takes for it to go and come back. And then with a very simple multiplication, we can retrieve that information. I work instead with the indirect time-of-flight cameras, which are similar devices, but instead of an impulse of light, they send a modulated light towards the scene, so sine or cosine waves. And at the sensor side, what we do instead are some correlation measures. So we just integrate information, and from that we can get this phase delay delta phi. This is again useful because with another simple multiplication, we can recover the depth. This kind of devices, however, have some inherent problem to the technology. So what happens is that we send this light, which, however, bounces multiple times inside of the scene. At the sensor side, so a single pixel, what it sees is not just the shortest path, which is what we want to recover the depth, but also all the other components which follow longer paths and lead us to this overestimation, because everything is integrated, of course, and we cannot distinguish between them. On the right side, we can see an example where green means good estimation of the depth and red means overestimation, which is what we want to clean. Before going onwards, we need to first understand how things look like from the direct time-of-flight pixel point of view. So on the bottom left, what we show is the light behavior incoming to a direct time-of-flight sensor. So the first thing that we see is this so-called direct component, which is due to the first reflection. So a very strong reflection due to the shortest path, which is what we want to keep. Everything else, all the noise, is due to all these different bounces inside of the scene, which, however, are received by the sensor, of course. Why is this useful? Well, the point is that there is a pretty straightforward link between the direct time-of-flight domain and the indirect one. In practice, it is a simple matrix multiplication. So we can take this vector x, compute phi times x, and we get v, which are our height of measurements. How we cannot invert this matrix, but what we can do is exploit it in a different manner. So let's imagine we have this vector v in input, which are our height of measurements corrupted by MPI, but we can say that there must exist a direct time-of-flight image, which of course we don't have, but it must exist. And what we can do is then split this in two parts. So one part just corresponds to all the direct components, which are these peaks, and the other part corresponds to all the nodes. Again, we can now make this go through the model, so this phi time with this matrix multiplication, and we get again back to the height of domain, only that this time we have two components, one of which, it's very important, it's called VD, corresponds to the height of measurements only due to the peaks. Of course, if we manage to recover this, we have no multipath anymore. So what do? Is we use a convolutional neural network, a very small one, that starts by getting in input the height of measurements, the corrupted one, and tries to estimate the clean ones. Now, what happens is that we are also working only on the third dimension. So keep into account this network has a very small receptive field due to the fact that we're using only the information due to the different height of measurements. We need to make the receptive field a little bit bigger, just because of other noise sources, which we cannot clean otherwise. But in practice, we're working with an extremely small network, which has a total receptive field of something around 11 by 11. To conclude, we are here. Here we can see some experimental results. So let's focus first on the right side, where we have, well, on top of the input of the network, corrupted by MPI, and on the bottom we can see how well that has been cleaned by the network. And finally, let's just focus on the comparison with the state of the art. This work by Agresti et al. And we can see how we managed to beat them on this S4 dataset, trail only a little bit behind on this S5 one, all while keeping just 1/7 of the parameters. So this concludes my presentation. Many thanks for your attention.
Okay, many thanks, Mr. Simonetto, for your presentation. Are there any questions from the audience? No, so thank you again. Let's move to the next one. Is Mr. or Mrs. Raytold here?
Yeah, Meg. Yeah, I'm here. Good morning, everyone.
Okay. So, good morning. Let's start your video.
Good morning. My name is Meg Rathod, and I'm very excited to share some of my work at the IEEE Wearable Conference. I'm currently a master's student in biomedical engineering at the University of Toronto. I'm supervised by Dr. Daniel Franklin. The focus of my work is on optoelectronics and wearables and their application in cardiology. So, heart failure is a devastating disease that affects 26 million people globally. In Canada, for example, 2.4 million Canadians are affected with an associated cost of $2 billion a year. So you can only imagine what the global cost might be. Unfortunately, almost half of all fatal events occur outside of the clinical setting. The chronic nature of the disease begs the question, what if there's a way to periodically monitor and manage it? Sadly, current methods for cardiac monitoring are often invasive or require clinical imaging, both of which only provide a brief snapshot of what's happening and are resource intensive. Therefore, the development of a continuous, non-invasive monitoring system would be an invaluable tool to identify changes in cardiac function, improve individual outcomes, and save billions in healthcare costs. And that's where wearables can come in. Advances in wireless technology and miniaturized sensors have improved the capabilities of wearables, allowing them to leverage light tissue interactions to monitor cardiovascular metrics, such as blood oxygen levels, which were once only possible via invasive blood tests. Wearables are gaining popularity for their ease of use by both patients and clinicians. However, these devices are not perfect. They do present many challenges, some of which are highlighted by a great review published by Fine in 2021. One of these major issues is skin tone variance. The variable presence of melanin introduces additional light absorption that leads to inaccuracies in optical methods if not taken into account. This inaccuracy results in a documented clinical bias, where existing pulse oximeters overestimated SpO2 in dark-skinned patients 3 times more than in light-skinned patients when compared to the gold standard invasive arterial blood gas analysis. This faulty overestimation is dangerous because it can cause at-risk patients to be overlooked when assessing for hypoxia, a sign of impending heart failure. Correcting this optics-based diagnostic technology is imperative, considering how it may influence triage decision-making. Now, the goals of some of my work are to develop novel optical sensors and algorithms that account for natural variation in skin tone. Currently, conventional SpO2 measurements use only 2 wavelengths of light, one below and above 800 nanometers, the isospastic points of oxygenated and deoxygenated hemoglobin. The AC and DC components of the signals are then used to derive SpO2 based on Beer-Lambert's law of optical absorption. However, melanin has a non-uniform absorption spectra, and variations in its concentration will impact measurements at the 2 wavelengths differently. We intend to address this challenge by implementing miniaturized spectrometers in wearable technology and expanding the number of wavelengths used in SpO2 calculations. Through on-skin spectroscopy measurements, we'll be able to 1. Determine melanin concentration, and 2. Develop an SpO2 algorithm that takes this into account. So in order to achieve this, we have an established collaboration with AMS AG, which is an international semiconductor sensor manufacturer, to integrate these novel miniaturized spectrometers within wearable platforms. After we've designed and tested this device, we're comparing it to a traditional spectrophotometer and also using skin phantoms and optical simulations to support it. Eventually, we're progressing into a pilot study using a diverse lab population to test in humans. The ultimate goal is to develop a pulse oximetry model that will take melanin into account to make sure these devices can work regardless of your skin color. However, that's just the beginning. This multi-wavelength spectral technology can be taken even further to account for other forms of interpersonal variability such as fat content or fluid status. But we want to go even beyond there. Using this spectral technology, we can play a big role in defining new metrics of cardiovascular function or dysfunction. In these images here, we have started some exciting new exploratory studies to see if we have the sensitivity needed to capture changes in vasculature. So we did some sympathetic nervous system tests, such as ice submersion, to observe shunting of the arteries. We were actually able to detect full body changes in the microvasculature on the other hand, and we even confirmed some of this work by using ultrasound to image the arteries and check for constriction or dilation. In summary, leveraging light tissue interactions are an exciting field with much potential, and that gives me and 26 million others around the world hope. Thank you.
Okay, any question from the audience? Nope. So, Mr. Radov, many thanks for your presentation. Let's move to the next one. Or yeah. Oh, Miss Oltiana Seitai, sorry if I really mispronounced your name, is here with us. Mrs. Oltiana.
Yes, I hear very well, but it's noise here. Sorry.
So I will start your.
Okay. We can start my video, so you see and.
Hello everybody, I am Oltiana Seitai, a PhD student at Applied Electronics. Well, the topic I have chosen is elaborazione e classificazione di immagini mediche per il riconoscimento automatico di patologie. Well, I think it is a topic that everyone needs in a way to make life easier. The technology indeed has its main purpose to ease your life. So when somebody of us is sick or doesn't feel well, we urgently run to call the doctor or to call to go to the nearest hospital. But sometimes has its own difficulties. Because you need urgent help, and meanwhile you don't have time to wait. So how to help ourselves or somebody else? Just with a simple app downloaded in your smartphone. This app or application has its main database of a photo of us. He knows us very well. He knows our fingerprints. He knows our eye color and our face mimics also. So we can say that our smartphones knows our better than everyone else. So why not to use this knowledge equipment to distinguish in an automatic way different pathologies? So you have just to stay in front of your open app at your smartphone and it will be work for you. It will have a database where it keeps tracks of your past and your future pathologies also, and it will suggest. For example, when you have red eyes, you have high blood pressure, or when you have skin contact, you may have a reaction, etc. So it will be connected with your family doctor, and he can give you some advices or something else, or your treatment. That's why I've chosen this theme, and I think it's very comfortable and will have success. So I have here for I'm writing. I have write a little for deep learning. Why? Because to gain a more practical understanding of deep learning, we have some categories. That is classification, object detection, semantic segmentation, image processing, and natural language processing also. So if you have these categories, you will see here where the image classification predict the type or class of an object in an image. So it has also its input and output also. Object localization locate the presence of object in an image and indicate the location with a bounding text on input and also output. And object detection that locate the presence of object with a bounding box and types of classes of the located object in an image. That's why I've chosen this step. It's, as I said before, it's very meanwhile is for the future studies, and I think it will be a great success. But for the moment, I've not. I've just started it, and I think that will be very comfortable for everyone to listen to it and also to work. So we can continue to textual analysis plays a supportive rather than a comprehensive role in the future of medical image interpretation. I also have take data meaning techniques and everything else that is very comfortable to work for it. I think that MATLAB it will be the best of the main program I will work with. For the moment, that's all. I think it's only a big presentation, only a small presentation of the work, of the big work I have to do. Thank you, everybody. Thank you.
Okay, many thanks for your presentation. Are there any questions from the audience? No? So let's move to the next one. Mr. Andrea Celentano is here with us.
Yeah, it's me.
Okay, so we can start your presentation.
Hello, I am Andrea Celentano, and I am presenting my PhD work about an optimum PowerPoint tracking algorithm for power regulation in biomedical wireless power transfer systems. My PhD advisor is Gianluca Setti. Let me do a brief introduction to the topic. Wireless power transfer is somehow becoming more and more common in both industrial and biomedical implants. We are going to focus here on biomedical applications such as neurostimulators, as the one in the slide, where wireless power transfer represents a viable alternative to overcome the issues that derive from implanted batteries. Particularly in cases in which the two systems are located in close proximity of each other, wireless power transfer is based on inductive link, in which one coil is placed immediately outside the human body and the other one inside it. This system is characterized by the inductances of the two coils, which is generally known, and the coupling factor K, which is unknown, since it depends on coil distance and misalignment, and it is typically very low. The wireless power transfer block, in the top-level block diagram of the neurostimulator, is highlighted with a red dashed box, which can be easily represented as made of a power supply, a transmitter and a receiver circuit, and a load. To give you a bit of context about my research, I want to show you how a wireless power transfer is generally designed, and what is the novelty in what I do. By increasing the system complexity, we can design the system according to different design methodologies. The first is the classic RF approach, according to which the transmitter and the receiver are independently designed. The transmitter is designed as an RF oscillator, and the receiver as an harvesting block, with the aim of taking as much energy as possible. An alternative is to design the transmitter and the receiver block together by exploiting the knowledge of the CDC converters. Not every CDC converter is suitable, but it must be obviously isolated to guarantee isolation between primary and secondary side, and it must be capable to achieve relatively high efficiency at high frequency. By the way, I consider as high frequency the ISM band of 7.78 MHz or 13.56 MHz. High frequency is required to reduce the size of the reactive components, but at the same time, we cannot afford too high switching losses. This is the reason why resonant topologies, which exploit the soft switching, are exploited, and among all the possible converters, I have focused my research on classic ones. Moreover, my aim is to define a control system without the need of any feedback from the implanted part, and track the optimum power point in order to reduce the wasted power at the implanted site. To make the optimum power point tracking possible, a power regulator is added to the basic block scheme of a wireless power transfer system. A power regulator is a device that guarantees the nominal power Pn to the load, if the output power of the wireless power transfer link is greater than that. If the output power is less than Pn, the power regulator is off and the load is directly connected to the converter. The optimum power point tracking algorithm is meant to supply the exact amount of power to the load. By considering a linear model of the converter, depending on its output resistance, two cases can be considered, that are the wireless power transfer link modeled as a real voltage source and as a current voltage source. Let's focus first on the voltage source case, in which we use the current limiter as a power regulator. If the output resistance is much less than the load resistance, we can demonstrate that when the current limiter is on, the input current is constant, while when the current limiter is off, the input current is linear with the input voltage. It means that there is a change of the slope when the power regulator switches from on to off. Our purpose is to stay at the corner point in order to guarantee the exact amount of power to the load. Likewise, if we consider the dual case of the real current source, we use a voltage limiter as a power regulator. Again, if the power regulator is on, the input current is constant with Vin, otherwise it is linear with the input voltage, and this relation holds until the output conductance is much less than the load conductance. To better understand, a SPICE simulation has been reported in order to confirm the previous results. Let's start with a certain input voltage that ensures the regulator to be on. If we change the input voltage and the regulator is still on, the input current almost doesn't change, and the output voltage stays the same. On the other hand, when the regulator turns off, small changes in the input voltage cause appreciable changes in the input current. So from here, the desire of working at the borderline between these two regions, which ensures the minimum possible wasted power. For further information, just drop me an email or have a look at my publication.
Okay, thank you, Mr. Celentano, for your presentation. Are there any questions from the audience? No, doesn't seem so. So, thank again, and let's move to Mr. Michael Neri, if he's here with us.
Hello, everyone. I'm here.
Okay, so let's start with your presentation.
Good morning, everyone. My name is Michael Neri, and I am a first-year PhD student in Applied Electronics at the University of Roma Tre. Today, I'm going to present my PhD research called Improving Safety by exploiting AI-based anomaly detection in audio signals. My research is part of the European project INSECT, which aims to provide intelligent processing of data and communication characteristics at the edge to perform real-time and safety-critical industrial applications. INSECT proposed 16 different use cases that cover high-relevance areas to European society and industry. More specifically, our use case focuses on improving the vehicle control by implementing real-time monitoring and automatic alarm generation on the bus, inspecting audio data. This research touches four main research interests. We extract relevant features from different audio representation in order to perform anomaly detection and classification with explainable deep learning algorithms. During the process, we take care of human and data security by elaborating audio signals as close as possible to IoT sources with edge computing devices such as the NVIDIA Xavier module. Our proposed framework deploys a coarse-to-fine approach for detecting and classifying anomalous events during the run of the bus. The coarse detector is responsible for determining if an audio signal is anomalous in real time. If so, the fine detector aims in recognizing audio events with their onset and offset timestamps. This framework allows to reduce the computational cost on the edge device and provide more reliability of the monitoring system. We extract the audio features from two different domains. The time domain shows the change of amplitude during time, whereas the time frequency domain contains the information of spectral power variation during time. In our work, we fix the length of the audio signal to 4 seconds since it is the average time required by a human to recognize the environment and the anomalous events. Deep learning techniques require a large amount of the audio samples for extracting robust features. For this reason, we are going to generate a dataset for each level of detection. Audios from DK's challenges, Urban Sound AK, and Free Sound websites are synthesized using Scaper for creating the datasets and then train the two detectors. Here we can see the proposed model. State-of-the-art sound event detection system exploit the MEL spectrogram to extract visual features using 2D convolutional neural networks without examining amplitude changes during time. Our scope is to add a branch which extracts features from the time domain. Then, a feature fusion module with attention is employed in order to obtain explainable feature maps, or heat maps, that can be used for each level of detection. Our 2D convolutional neural network pre-trained on audioset dataset is already in top 5 accuracy on the Urban Sound AK dataset, and we expect to improve the result with the time domain features. Moreover, to overcome the problem of lack of annotated data, we are going to train a network using the self-supervised learning paradigm. More specifically, we train a network that recognizes the type of augmentation of the input signal. This method forces the network to create meaningful internal representations of the audio data without labels. Moreover, this approach can exploit the large amount of raw audio samples without the need to annotate the data manually. When the training is complete, the model can be employed in the fine-tuning process using the aforementioned datasets by applying the transfer learning approach. Finally, we present some cascade works that we are going to handle in the future. Using the aforementioned technique, we will focus on AI-based emotion recognition from speech in noisy environments such as the bus. Moreover, the IoT infrastructure has to be secure with respect to cyber attacks, such as port scanning and low-rate denial of service. In the future, we will work to generate a dataset of attacks which permit to train a neural network for cyber attacks detections. Thank you for your attention. If you have any question, feel free to ask.
Okay, any question from the audience? No, so if Miss McCarthy is here with us, we can play his video.
Thank you all.
Okay, Mr. McCarthy. Okay, she's not with us, so we can move to the final vote. Okay. Okay, so let's share the screen. So I hope you're able to see my screen. Yes, so you have to go to menti.com and use the code over there so you can vote. You can vote. So go to menti.com, and you can, let's say, use the code to vote the one that you prefer among the presentations. Okay, so let's stop the vote, please. So definitely the winner is Miss Nunzia Molinaro. You win the award. Are you here with us? I see you.
Yes, can you hear me?
Yes, so you definitely won the award about the best speech presentation today.
Thank you very much.
I'm very happy to say it. And so
Thank you very much to all you vote me.
okay, so thank you very much. I don't know if our chair who is here with us want to say some words to close.
Hello.
Good morning. Yes, I'll be quick. Sorry, I joined later because I had lecture. But of course, I went through the pitches that were delivered beforehand. Of course, the committee, we went through all of them. So thanks. The quality was very, very nice. And thanks for participating. Congratulations to the winner. And I hope you enjoyed this session and enjoy the rest of the conference. And thanks, Vincenzo, for holding this session today.
Yes, let me remember, I already see Carlo because he's always with us, but let me remember that now the workshop continues. So it's gonna start in 10 minutes. So we were in the schedule as promised. Also the coffee time, the coffee break. So I leave Carlo the word. I want to thank again the WSAIM organization for letting us organize this event, this competition. Many thanks to Carlo and the others.
I want to thank you, Vincenzo, and all the IEEE young professional for the amazing event. It was an interesting event inside the event. Yeah, thank you for this first part of the workshop. And yeah, I renew the invitation to join the second day of the workshop in 10 minutes. Yeah, just have time for a coffee. And thank you again.
Okay. Thank you very much and bye-bye.
Bye.
Bye.
Hello, can you hear me?
Yep.
So welcome back to the workshop second day. Ladies and gentlemen, very good morning to all. It's my great privilege to welcome you all again for this excited second day workshop, IEEE second international workshop on wearable sensors and devices, artificial intelligence and wearable markets. Myself, Vijay Kumar Varadarajan. I am one of the general chairs of this workshop, which is sponsored by IEEE, IEEE Engineering in Medicine and Biology Society, IEEE Young Professionals, IEEE Sensors Council Italy section, IEEE Students Branch Rome, and IEEE Systems, excuse me, and IEEE Systems Man and Cybernetic Society Italy section. In IEEE WSAIM 2021, we will explore different aspects of the wearable biomedical sensors, from sensors design and development to the AI algorithms and machine learning to retrieve robust data for medical applications to the market of wearable sensors for healthcare, occupational settings, and sports monitoring. I would like to say thanks to all the organizers for devoting a significant efforts to organize WSAIM 2021 in online mode in this COVID pandemic situation to tackling the gap of face-to-face live workshop. And this entire event is hosted in full live and interactive online mode. WSAIM 2021 broadcasted online via Zoom. All the chairs will take their sessions live. We hope that the solution will allow all the participants to interact each other seamlessly and enjoy this workshop in online mode. IEEE WSAIM 2021 is dedicated to provide the latest research findings, ideas, and applications in the area of wearable sensors and systems, artificial intelligence, and machine learning algorithms, and to understand how the wearable markets are evolving. This workshop is intended to provide a forum for research scientists, engineers, and practitioners, and will provide you all the best tools to interact with our top-level speakers during the whole conference. Today's workshop aims in artificial intelligence, which is already started booming from the past many years, and I am sure it will be the future. I too felt AI may lead the intelligent machines to rule the world very soon, which we can say so far the humans control the machines, but in future, we may experience the machines to control the humans. The first speaker of the day will close the track 2 that started yesterday. Professor Occupancy will show us how to design a wearable sensors and the open challenges in the field of health and well-being. In his talks, we will see biosensors, new materials for capturing physiological quantities, microelectronics, integration for sensing applications, new enabling technologies, even energy harvesting technologies to push forward the current applications of both wearable and implantable devices. In this third track, Dr. Pau from ST Microelectronics, that is Dr. Seppa from Ravinia Research, Dr. Nicholas from SAP, and Dr. Vaidyanathan from Movelle will talk about their experiences in the field of wearable sensors in different scenarios and the current and future trends with insights on how Turing academic research to medical device business. Lastly, track 4 is devoted to machine learning and AI. Dr. Karini, Professor Mandik, and Professor Inan and Professor Lee will give us an overview of the interoperability of data collected from wearables, advances of computational methods and techniques even based on machine learning and AI in the field of physiological monitoring and human performance and personalized rehabilitation. So the agenda of the second day is similar to the one of yesterday. You can find all the details on speakers and talks on the website of the conference in each moment. Moreover, at the end of the day, we will be very happy to give you information about the certificates of attendees, statistics, and anticipation on third edition of the workshop. I really want to thank again our great technical sponsors. So at the end, I would like to say thanks to all colleagues involved in the organization of the workshop. I want to convey my heartiest thanks to my friends who worked along with me as a general chairs, Dr. Carlo Massaroni, University of Campus Biomedico Roma, Italy, Professor Paolo Bonato, Harvard Medical School, USA. Well, the second day of the IEEE WSAIM 2021 has started. Please enjoy the workshop. I welcome you all again. And also I would like to welcome the track chairs, Dr. Emanuele Maiorona and Dr. Eleni Bergamini and Dr. Amanda Pia Silvati, all from Italy. So after the break, the track for one will be starting. So enjoy the workshop. Thank you.
Thanks a lot, Professor Badrajan, and hi everyone. I am Emanuele Maiorana from Roma University in Rome, in Italy, and I will share the first session on the second day of the IEEE Second International Workshop on Wearable Sensors and Devices, Artificial Intelligence and Wearable Market. The first lectures, as you said, will be given by Professor Luigi Occhipinti and is entitled Sensor Technologies and Energy Harvesting for Wearable and Implantable Electronics. Professor Occhipinti worked for over 18 years in the global semiconductor player ST Microelectronics with responsibility of teams located in Italy, France, and Singapore. Since 2014, he works at the University of Cambridge, Department of Engineering, where he is currently the director of the Research in Graphene and Related Technology Laboratory, and also has the role of Deputy Director and Chief Operating Officer at the Cambridge Graphene Center. He is senior member of the IEEE, sits in multiple advisory boards in multinational collaborative research programs, as well as in the editorial boards of scientific journals and book series. His research interests are centered around four main strategic themes: bioengineering and healthcare medical devices, complex, resilient, and intelligent systems, stretchable and biodegradable electronics, energy transport, and urban infrastructure. The outcomes of his research are captured in over 130 scientific publications in journals and conference proceedings, with over 5,000 citations, 3 book chapters, and over 65 patents and patent applications. In his talk, Professor Occhipinti will discuss the design, advanced materials, and heterogeneous integration technology requirements for next generation wearable and implantable electronics, with attention to their sustainability and end of life. I would like to remember the audience that questions could be proposed in written form through the question and answer tool and will be read after the ending of the talk. So thanks a lot for your availability, Professor Occhipinti, and I can give you the word for your lecture.
Thank you. Thanks, Emanuele, for the nice introduction. So let me try to share my screen. And I'll put in presentation mode. Can you see the screen?
Yes.
Perfect. Okay. Thanks. So yes, my talk will be on sensor technology and energy harvesting for wearable and implantable electronics. Okay, let me start with an overview of the proliferation of IoT and how this impacts the design of sensors and energy harvesters today. So these days we are assisting to an exponential growth of Internet of Things, which drives the transition from centralized cloud-based or internet-based computing towards edge computing. Here, what happens is that the edge devices are the hardware enabling IoT applications in different market sectors, from smart surfaces to smart lighting, personal healthcare, smart packaging, security, logistics, and others. This also means that more edge devices are gradually becoming portable and autonomous from both the energy and from the data processing standpoints, so that they can be embedded into everyday objects, either for long-term operational low-duty cycle, as in the case of sensor networks, or with a shorter lifetime, as for instance in the case of disposable electronics, smart labels, single-use sensors for personalized diagnostics, and so on and so forth. And this transition is also seen as the enabler of the Industry 4.0, the fourth industrial revolution. Now, when it comes to printed electronics is developed along the path that aims to intersect the global Internet of Everything megatrend from a business opportunity which is larger than $100 billion, almost a third of the entire semiconductor market today. This is explained in this slide, which, by the way, I borrowed from the company Thin Film Electronics, by the extra TAM which is available on upper rails, with 80 billion units sold per year, as well as for disposable items, which is estimated in the several trillion units per year. The printed electronics is actually a technology which is considered uniquely able to address both the lack of scalability and the cost of integration with conventional electronics. However, proliferation of Internet of Everything poses some important sustainability challenges. For instance, in terms of eco-friendliness of the substrate, when it comes to the carbon footprint associated to their manufacturing, as well as in terms of end of life, especially for disposable systems when there are concerns that a lot of e-waste may contaminate our environment, our oceans, our soils, and so on and so forth. So the trends towards autonomous IoT nodes or systems also poses some challenges in the way energy is harvested and stored in the system, which I will comment, by the way, in the next slide. So in order to put things into context, let's assume we start from a typical flexible electronics autonomous sensor system, which is represented schematically in this slide. This is composed by the sensor and the data processing unit, the communication module, the energy subsystems, and last but not least, the entire substrate. Our aim and research approach has been to assess the sustainability of each module and address the challenge by looking at the design and selection of novel materials, processes, devices, and system architectures. So let's start with the energy subsystems, which is highlighted here. It is clear that powering IoT devices with batteries may not sustain the evolution of the IoT ecosystem when it proceeds to the 1 trillion nodes. For instance, considering just the lithium, which is included in a standard CR2032 battery, it is expected that 1 trillion batteries will absorb at least 100,000 tons of lithium, which is a significant portion of the overall production of lithium, expected to reach 1.5 million tons per year by 2025 to serve all the application sectors, including automotive batteries and so on and so forth. So it is therefore important to consider other solutions that help reduce the burden of the lithium resources, as well as the other materials that are used in batteries, for instance, cobalt, to name one. So what we've seen is other chemistries being considered and being developed in parallel to the lithium-ion batteries. So for instance, zinc batteries compared to lithium-ion are good candidates in terms of environmental impact. This is due to a few technical reasons. So for instance, mining of zinc may be much easier than cobalt. The use of aqueous rather than solvent-based inks, so more environmentally friendly and less flammable materials, as well as the packaging. I mean, for zinc batteries, the packaging can be full plastic rather than metal plastic laminate, which is required for the lithium option, and therefore it's rather hard to delaminate and recycle. Another way to leverage the energy requirements and eventually reduce the size of batteries in IoT nodes when the nodes is equipped with an electronics that absorbs peak current, for instance, during radio transmission or reception of data, is by combining batteries and capacitors, either ultra capacitor or super capacitors. In fact, when the load circuit, as in this scheme, absorbs a relatively high peak current for a short period of time, actually what happens is that the standard battery with its internal resistance operates such that the output voltage will reduce to accommodate the voltage drop across the internal resistance, which means that in practice, the circuit operational capability is much reduced when the device requires absorption of peak current as for the transmission and reception of data periods. In other words, combining the high power density with the of ultracapacitors with the high energy density, which is typically offered by the battery element, would help reduce the size of the battery and, of course, optimize the efficiency of the energy storage. When it comes to the energy harvesting, of course, the primary source will be what is available already in the ambient, right? Because IoT is distributed everywhere. So here you see examples of sources that are available as ambient energy and could be harvested, going from the photovoltaic, the outdoor and indoor photovoltaic for harvesting light, energy from light, the RF antennas for harvesting energy from either GSM or Wi-Fi networks, as well as from thermal gradients or from mechanical vibration and movement. Each one of these technology has the typical characteristics in terms of both energy supply capability and efficiency, and different level, of course, of availability, of predictability, of controllability as a source. So for instance, when it comes to photovoltaic, I mean, indoor photovoltaics is relatively predictable, controllable, and it's also widely available in any building, if you wish. So in our daily environment. Ambient RF is also quite ubiquitous, at least in the urban environment, a bit less in rural areas, of course. But then when we look at the tech and thermoelectric generators, then this is only applicable in the immediate vicinity of the thermal source. And in the case of piezoelectric generators, the output of the harvester strongly depends on the actuator, on the source of the mechanical actuation and its specification, the frequency, the energy, and so on. So it's relatively important to consider these characteristics. In fact, when as you can easily figure out, then in many cases where the source of energy harvested is intermittent, as in mechanical harvester or in outdoor solar, for instance, and whenever the power absorbed by the load is also rather disuniform, as in wireless transponders, it is not possible to use the ambient energy directly without storing it on board. But this is why, of course, we go from the harvest use architecture to a harvest store use architecture with an embedded power management. In our progress report that we published earlier this year in Advanced Energy Material, together with Professor Vincenzo Pecunia at Suzhou University. He just, by the way, moved to the Simon Fraser University in Canada, and also with Robert Hoy at the Imperial College. We reviewed systematically the energy requirements for powering the Internet of Things, and compared the different energy harvesting technologies, then focused on the emerging indoor photovoltaic technologies that are designed for sustainability, and also on the emerging eco-friendly materials and processes for indoor photovoltaic. So to put things into context, here you can see a comparison of the 4 indoor photovoltaic technologies in terms of both efficiency and sustainability for indoor applications. And this is under artificial light with either fluorescent or with white LED illumination, both considered at 1000 lux. It is worth noting that in the case of indoor photovoltaic, the optimum band gap required by the absorbers is in the range of 1.9 to 2.0 electron volt, while for the outdoor is much lower, is between 1.1 and 1.4 electron volt, which makes a strong difference in the absorbed material to be selected for this type of applications. So then when we look at the hydrogenated amorphous silicon, this is probably the main commercially available technology for IPV today. It has good sustainability in terms of economic impact. It relies on very good and established manufacturing processes. However, when we look at the positioning of the amorphous silicon, or the hydrogenated amorphous silicon, of course, the technology is still limited by a relatively low power conversion efficiency. And on top of that, there is an intrinsic degradation which is induced by the lagged exposure in the first few months of operation, which is already well known and documented. From the efficiency point of view, it is clear that dye-sensitized solar cells hold a strong advantage of nicely fitting the spectrum and also producing a relatively high power conversion efficiencies, theoretically limited to around 34%. However, historically, many of the dyes used in the SSCs were based on ruthenium, which is a scarce element that negatively impacted the overall sustainability profile of the device. So to improve the environmental compatibility, there have been efforts to replace ruthenium-based dyes with organic dyes, paying attention, of course, of the entire set of materials, including the solvents, the reactants, the catalysts, and so on, and also looking at natural dyes, so sources from plants, which have been considered. However, the efficiency and stability of these devices are still rather low when compared to synthetic dyes. The third technology, the organic photovoltaic, despite a lower band gap and relatively, well, a bit lower efficiency, they are the ideal candidates for, or at least very good candidates for indoor photovoltaic in terms of sustainability. They can reach theoretical efficiencies in the range of 30–31%, similar somehow to DSSCs, but also their sustainability profile and eco-friendliness is very, very good for the materials that are considered. Also, more recently, the issues that are typical in this technology related to the light-induced degradation which is actually derived from the fullerene-based acceptors, is being mitigated by the use of non-fullerene-based acceptors, which show longer stability when exposed to light. And finally, lead-halide perovskites. These recently have been introduced more recently in the scene of photovoltaic technologies. They are capable of the already highest theoretical power conversion efficiencies, up to 37%. A key challenge, of course, in lead-halide perovskite is still their limited photothermal and environmental stability, which is due to the presence of the methylammonium cation. This can be compensated, however, by the introduction of barrier layers and control of the interfaces, or even replacing the methylammonium with other cations, having better stability. However, the main concern is still remains with lead, because lead is an hazardous element, although the amount of lead contained in these perovskites may be still low, but this is still considered as a toxic element, a toxic material that can contaminate the environment, along with some of the solvents used to manufacture these cells. So this is why there is a strong interest actually to move towards a non-toxic lead-free perovskites equivalent, or so-called perovskite inspired materials. So in another publication earlier this year, together with again Vincenzo Pecuni and Robert Toy, as well as with Judith Driscoll, the material science here in Cambridge, we reviewed the different lead-free IPV absorbers and investigated the materials that are perovskite inspired, such as bismuth and antimony-based compounds that have much lower toxicity than lead-based compounds. Actually, what happens is that both these compounds have optimal band gap for indoor photovoltaic, 1.93 for bismuth and 1.95 for antimony-based compounds. Also, they are present in a 2D, in a layered structure rather than a 0D crystal structure, which contributes to improve the charge mobility and ultimately the efficiency of these absorbers. So devices based on these compounds have reported efficiencies that are still relatively low, but much better than in indoor than what they can achieve outdoor. The increase of the power conversion efficiency for indoor use is 4 to 5 times as compared to the outdoor, and also they are quite stable. They've been tested for over 5 months without encapsulation, which is quite promising. Now let's move on to the wireless communication module. In this case, the electromagnetic field is often used not only to send receive data, but also to harvest energy from the RF source. So for instance, in this example, we developed it in collaboration with 2 Cambridge-based companies, CITC Ltd and Zinergy UK. We developed a proof of concept of a system powered by an RF energy harvester in the sub-gigahertz at UHF, and assisted by both a thin film battery, a printed thin film battery, and a printed thin film supercapacitor, which are shown in this slide, along with a suite of standard sensors available off the shelf. So this is the concept of a device which is called wear and forget. So it can harvest energy from the ambient, or at least from an RF source. And then this energy is stored in the battery as well as in the supercapacitor to provide the high power density as discussed earlier. So in this type of battery assisted far field energy harvester, the presence of the battery and the supercapacitor along with the UHF energy harvester allows to increase the read distance from the source of energy, so operating at several meters of distance from the source. Finally, when it comes to the sensors and electronics for data processing as well as for the sensor, we need to consider the impact of power consumption, which is required to operate the electronics and the sensor front end. So another work we reported back in 2020 with a group of Vincenzo Pecunia and Thomas Santopoulos at KAUST was the development of a unique printed semiconductor carbon nanotube transistor-based technology with some nanodielectric, and this is operated in the deep subthreshold regime. This means in practice operating voltages lower than 0.5 volt, which achieve record low power consumption in the order 10 femtovolt to 1 picovolt per micron of channel width, which is just a fraction of the leakage current conventionally in conventional CMOS circuits, and also the lowest power consumption available at the time of publication for printed electronics. So we use the ambipolar transistor in this case, which is attractive because they reduce the material complexity, or at least the bill of materials, a lot compared to other CMOS equivalent printed electronics approaches. So you don't need a P-type and an N-type semiconductor, you just use the same channel, which is in this case a polymer sorted single wall carbon nanotube network to develop the ambipolar transistor. Also, the significance of this breakthrough is that actually, although ambipolar transistors were considered so far always on devices and therefore devices that intrinsically absorb a lot of power, in this case this is not true anymore because we operate in the subthreshold regime. So actually as mentioned earlier, the power is the lowest reported in printed electronics so far, and also we could reach a good balance in terms of subthreshold slope, high subthreshold slope, the high noise margins when operating in the subthreshold regime between 0.2 and 0.5 volt. With this technology, eventually we could demonstrate the possibility to design more complex logic circuits, starting from the basic NAND gate as a core unit that could continue to function with just a small fraction of energy obtained from the ambient, even without the need of a battery. In fact, here you can see that we assessed the technology with a millimeter size indoor photovoltaic cell, and that was made with the bismuth and with the antimony based compounds that I described earlier to power on a simple logic gate circuits made with carbon nanotubes based electronic technology described in the previous slide. Also, in terms of chemical and biosensors, an interesting area we explored is a graphene-based field effect transistors. So already back in 2013, in collaboration with a group of Thomas Palacios and Jing Kong at the MIT, we developed the first proof of concept of a pH sensor on a flexible substrate to monitor skin pH, which is using the shift of the direct point in ambipolar characteristics of the GFET, of the graphene field effect transistor. And this is actually the transduction mechanism for hydrogen ions that interact with the graphene channel. Moving alongside the same concept of building upon the same transduction mechanisms, different groups have developed the graphene field effect transistors based biosensors recently, where the graphene channel is functionalized with the specific receptors to the molecules of interest. For instance, in a recent a review of graphene biosensors for point-of-care testing, we provided an overview of the technologies that are available to date in this field, and also their sensitivity and their application, and not only for chemical sensors, but also for biomolecules, for metabolites, for DNA, RNA, cells, proteins, also for the COVID-19 virus testing. Further to the development of these integrated smart systems, we have analyzed the substrate materials, as mentioned earlier, in terms of both mechanical reliability and biocompatibility, both for wearable, patch-like, and for implantable use case applications. This slide summarizes the work of Edward Tan back in 2018 with sensors embedded in a stretchable PDMS substrate that avoid any potentially toxic material and solvents, while providing room for both high resolution and mechanically compliant patterned electrodes. So in terms of application, when we look at the application in the healthcare space, there's been also first wave of smart systems for vital signs monitoring, which have been implemented and are already been adopted in hospitals and clinics that allow the assistance of patients requiring 24/7 monitoring of their vital parameters, along with systems for remote assistance of elders at their home towards more independent aging, and of course systems for self-diagnosis and personalized treatment. In this space, in the medical application space, there is also a broad range of devices that are developed for single use or disposable electronics, which are provided to the patients already sterilized and are used once and then disposed, of course, to avoid any contamination issues. Of course, this has an impact, again, in the sustainability of the technology, both from the economic perspective and from an environmental one. And in many cases, that led to systems that are only partially reusable, where you have the electronics and connector that can be reused multiple times. The battery can eventually be replaced, but it's generally a disposable battery in this case. and then only the electrodes and the biosensor module is detached and eventually disposed after use. From this concept, that was the first generation of this type of devices. Of course, the evolution is towards either batteryless systems where the entire system can be fully encapsulated and only use energy harvested from the environment, as in the case of a smart contact lens, or systems that can use rechargeable batteries and energy harvesters, and eventually which allows to extend the lifetime of the battery quite considerably. And of course, finally, systems that can have a battery tuned or a power management and storage system tuned to last for the entire lifetime of the system. Yeah. Okay. So, for instance, in the case of smart contact lenses that I mentioned earlier, a work we developed some time ago within ST Microelectronics and a company called Sensimed was the development of this smart contact lens, where we used an ASIC, an antenna for harvesting energy through inductive coupling with an outer antenna, and then a sensor, a strain gauge sensor, to monitor the intraocular pressure. And this was used for early diagnosis of patients affected by glaucoma over a 24 hours period. The significance of this is that, of course, that technology could allow to monitor patients for a continuous period of time, especially at night when it is known that the disease could produce increase of the intraocular pressure and eventually irreversible effects back into the patient. So this would allow the doctor to monitor the patient and eventually establish the best dose and the best time to deliver the drug so that the intraocular pressure can be maintained under control. Of course, there are other use cases where the devices need to be implanted. So in this case, each of the device has specific requirements and characteristics. For instance, in this slide, we analyze the typical requirements of the most common implantable devices in terms of energy budget, as well as lifetime and availability of the energy source. I think I'm cautious of time, so I will accelerate a little bit. Also, when it comes to subcutaneously implantable biosensors for monitoring chronic conditions such as diabetes, the device is generally approved to operate only for a few days. So the battery can be tuned to operate in this period of time, and then eventually the sensor part disposed, as well as in the case of the insulin pump. What we've done here in collaboration with Bruno Pignataro at Palermo University and the former colleagues at ST Microelectronics was to develop a simple proof of concept demonstrator of a printable enzymatic sensor assembled together with a passive RFID based microcontroller system that can harvest enough energy from the reader to power on the sensor, read out the sensor, and return the value of the data stored eventually in the memory to the reader or to the smartphone to provide this information back to the user. Here, in collaboration with Stefano Pluchino in the clinical neuroscience here at Cambridge University, as well as with Fabio Biscarini at the University of Modena Reggio Emilia and Ricardo Garcia CSIC in Madrid, we analyzed the substrate more from for implantable devices, more from a foreign body reaction point of view. For instance, in this case, the macrophages were so macrophage cells were assembled on top of the cantilever in a AFM setup. So this is called a single cell force microscopy, force spectroscopy, we could monitor the adhesion forces of the macrophages onto the substrate, which is in a way providing a sense of how the macrophage, how strong the macrophage reacted to a foreign body. And at the same time, we analyzed the protein expression of the macrophages, which again provides a clear understanding of the foreign body reaction of different materials. Here, for instance, we compare the PLGA with PDMS as both biocompatible materials and in some cases bioresorbable in the case of PLGA. This was followed by the use of selected substrate materials to develop active medical implantable devices in a European project called I1, where the purpose was to implant a device in a spinal cord of patients or animal models rather affected by spinal cord injuries, and try to promote the neuronal regrowth as well as reducing the inflammation. This was done together with a microfluidic channel that allows to develop also to deliver also an anti-inflammatory drug, minocycline, which is a small molecule anti-inflammatory drug in the site of injury. And here you see how the device was implanted in mice and rats models. We tested, of course, the device in terms of toxicity, meaning that the model is able to perform normally at the same day of a surgery. And then in a model of a spinal cord injured mice, we could bypass the site of injury using a stimulation, a functional electrical stimulation via the implantable device. And the device was also using an organic electrochemical transistor as both the transducer and the stimulator. How much time? Okay, 2 more minutes probably. The very last activity I would like to discuss was in terms of exploring again new substrates, was an activity we've done coordinated by Cambridge University in the past 4 years in a European project called 1D Neon. This is trying to move from 2D or 3D integration towards 1D integration in fibers, so developing smart fibers with functional elements as either sensor, energy harvesters or storage, and also as a component as transistors. When you have that, then of course the next step is to integrate the components into a more complex system or a circuit using typical textile manufacturing technologies, from the fiber extrusion down to the weaving and knitting of the multiple fibers into a functional element. So I'm cautious of time. Rather than giving more detail on that, I would like to show you a very brief video of this smart textile system, where we have embedded all the functional element into a smart display that can be rolled, can be stretched, and also we use the various technologies into the for RF and piezo energy harvesting, for energy storage via fiber supercapacitors, for sensors, various type of sensors, thermal, photodetectors, and so on and so forth, and also some fiber transistor circuits to drive the actual devices. The technology details are currently being finalized into a paper that has been accepted in Nature.com, so this should appear relatively soon. So to summarize, I hope I convinced you that energy harvesting from multiple sensors, from multiple sources of ambient energy in autonomous sensor system is critical to achieve a positive impact on sustainability. Ultra low power printed electronics was demonstrated, and this can be used as a new way to develop a femtowatt printed electronics. Graphene-based sensors are capable of ultimate sensitivity and also selectivity that can be developed using the ambipolar characteristics in GFACT and as a transduction mechanism. And then the next generation wearable electronics, I might want to consider different substrates available, moving from conventional silicon to plastic, to fibers, textiles, as well as to paper, and maintain a high sustainability profile. And with that, I would like to acknowledge the collaborators, the group members and alumni, and of course, the funders. Thank you very much for your attention. And I'm ready to answer any questions.
Thanks a lot, Professor Pinti. Thanks a lot for your availability and for the great presentation you gave us. It has been full of very interesting technologies. I was looking for questions from the audience. I cannot see any currently in the question and answer tool. I don't know if anyone wants to propose some question. Well, in the meanwhile, I can apply for a question. Just for under your opinion, which is among the several technologies you have shown us today, is there anyone which you think will be most disruptive among others and possibly implemented soon in commercial applications?
Yes, I believe that the shift towards textile-based electronics, because this conference is on wearables, I think this is something that is happening and is happening now, right? So of course there are challenges still open. For instance, when the textile is actually a cloth, is clothing, of course, washability is one of the major challenges. I mean, not every piece of technology can survive standard washing cycles, which is why we are working on demonstrating washability, finding the right combination of materials as well as the right architecture of devices that can be encapsulated and therefore may protected from the washing. From the washing issue. Of course, the other option would be to have detachable systems, but this is still an intermediate solution. What we want to achieve in the long run is actually having everything embedded into a standard fabric, and this fabric can be a technical textile, either a coding or a carton or any sort of textile material that can be easily introduced in our daily life.
Thanks a lot again. Actually, that is a very practical issue which has to be faced as soon as possible.
Definitely.
I don't know if there are other questions for Professor Pinti. I do not see any further question. So if this is the case, I would like to thank you very much once again, Professor Pinti, for your great presentation.
Thank you.
Thank you. Thank you very much. And hope you to meet again soon in some occasion, in person possibly soon.
Yeah, gladly. Thank you.
Okay. Bye. Thank you once again. And with this, we can move to the next presentation. Actually, the next lecture will be given by Dr. Nicholas Nikolaudis and is entitled How the Enterprise Has Embraced Wearables to Keep People Healthy, Focused, and Safe. Dr. Nicholas Nikolaudis is Senior Director at Innovation, Technology and Strategy Laboratory at SAP. He's a passionate technologist with a PhD in computer science from Monash University, who has been architecting and developing market-leading software applications for the past 21 years. During his career, he has been a founder of several startup companies, worked with several multinational organizations, and held numerous roles in development, research, and management. His research has led to numerous publications, patents, and awards in exposing web services from business application to data mining and processing on mobile devices. This lecture will cover 3 different topics about how wearable technology is playing a critical role in the way we work, specifically regarding environment, health, and safety programs, improving focus during learning, and reducing permanent brain damage in sports. So Dr. Nicholas Nicoloudis is with us. He's already shared his screen. So I would like to thank you once again for your availability and give you the word.
Thank you so much. And definitely after the last presentation, that was some great insights there. So really appreciate being able to present here today. But what I'm really going to focus on today is how health and wearables play a role in managing health. This is becoming a big topic, especially in the new world of COVID, how we manage, I guess, people's focus, how we manage their health, and hopefully make things better for them. And I guess one of the reasons why this is important is because we find that, typically people who exercise start eating better, becoming more productive at work, and it basically helps people focus more. And we've actually got evidence of this as well. There's a great book by Charles Duhigg, who has, author of The Power of Habit, who goes through this. And I believe any course that I've attended or participated in emphasizes that, you need having that time to exercise, rethink, recalibrate is a good way to kind of engage your mind, re-engage your mind, and give it a different way or different perspective of how we do things at work. So as mentioned, we'll have a look at different things. One was a solution that we developed called FitSAP, and it was actually developed out of our region in APJ. My manager, Anil Bhaskaran, helped develop this solution, and it started off as a very simple concept, and now it's used by our company globally in many different countries. So I'll talk a little bit about FitSAP. The second example is a collaboration with a company called Emotive. For those who don't know Emotive, they've been in industry for a while. They develop, I guess, specific EEG, I guess, hardware, which you can wear on your head and basically use brain waves to basically do different tasks. And I'll talk a little bit about that when I cover that example. And then the final one is, we talk about normal professional work, but then there's a lot of people in sports work. And what we've done is this is a great example of SAP with a partner called Keytree, which is now owned by Deloitte, and a company called Protect that's developed the actual hardware for being able to identify head trauma in sports, especially rugby. So all these I'll have a little bit more detail on, and I hope you find this interesting. So one of the key things is how we might incentivize employees to be more physically active. One of the things is we've found that when we have more active people, we have more engaged people, and also people who take less absenteeism. In other words, they're likely to be at work and more active. So one of the key things, or what we're seeing a lot of, is and there was also this recent example of, sitting is the new smoking, Dr. James A. Levine. And what he wants us to do is get us away from the chair, because our chair is currently killing us. And so there's examples there of why he stated that, we need to move around, we need to be more active. And so during this time, my manager, Anil, decided, well, we've got a lot of people wearing these wearable devices, let it be a Fitbit, an Apple Watch, or whatever. How can we utilize this data that our employees are already using, and then possibly incentivize them moving forward? So we actually, by using an intern, we grabbed an intern from one of the local universities, and within 2 weeks, he connected something to what we call our business technology platform, which is really a layer of services which we can then integrate. So what we first did is he grabbed, I guess, with this student first looked at all the different devices, and they mostly all had their own cloud or kind of APIs. And then what we did is with those APIs, we then brought it into our business technology platform through an API set, and then we created our application called FitSAP. And then on top of that, we have a custom application which sits there and visualizes all the data that we read in. So we can have a look at daily what our current activities are. And if I have a look here, this is the first version back in 2016. What we were doing was we're keeping tracking of the different steps, support of 5 different devices. There was over 1,500 users in our region, being Asia Pacific, Japan. 60% of the people get an incentive. I know myself, I look forward to it. It's approximately $100. And the nice thing is with this $100, you can choose what you do with it. You could actually give the $100 to charity. You can keep that $100, and I've actually used it a few times myself. I use it to actually buy. I have 4 children, believe it or not. So with 4 children, I use it for gifts for my kids, which is a great thing. And now I've also got 2 different customers that have adopted this same solution. So what started off as an internal good project is now growing as a solution which we can now sell to our customers. Now, not only has that happened, we've also had some great publicity. Several employees took it up, and then including things like walking, kayaking, and then we also had a story which was released on in Singapore around the positive effect it's had to lifestyle. So that's something that's happened up until now, and now what we have is it's actually evolved. It's now become a global engagement, and I've left Anil's name there because Anil was the original developer. But support of key dynamics. We have over 20,000 active users on the platform. Over 60% of the people still continue to get that 100 Singapore dollars a day for their 8K usage. And now we've also support cycling, because another big activity we have is cycling in the group. So this little basic application has shown some positive engagement. It's shown people, taking less leave, and it's also shown, activity and then being reimbursed. And we found that, if it's actually the money, the $100 actually outweighs them taking time off and being unwell. So we've had some positive feedback on that. So that was Fit SAP in whole, again, still active and still being used within SAP at the moment. The next example I'm going to talk about is the work that we're doing with a company called Emotive. And the nice thing is that, depending on the person, you might have people have different ways of learning, right? Let it be, you might have different things going on. People might have family. And what we decided to do is we worked with the company, and what you can see here is these called Emanate earbuds. And not only are they, I guess, provide audio capability, but they sit there and listen to EEG signals and understand if you're concentrating, if you're able to understand, if you're able to focus. And so what we're able to do is actually say, and intervene. At this point in time, you're not focused, maybe take a break, maybe go for a coffee, or maybe go for a workout. And basically using this technology, we've made it become more productive. Now, this also is in collaboration with our new user experience platform, which is called Fiori 3.0. And by using Emotive together with I guess our HR solution, we're now evolving currently what we're doing there. So for us, this has been a really great bit of technology, and we're constantly evolving it moving forward with the Emotive team. I mentioned before something called the ProTech mouthguard. So to give you a bit of insight here, this was the first developed for rugby teams. Now, what ProTech actually is, it's an accelerometer within the mouthguard itself, and it's actually quite, I guess the idea and the concept behind it is quite simple. What it does is the accelerometer in the mouthguard identifies the amount of impact or the amount of G-force being captured, and depending on the amount of G-force, the coach on the side of the side of the field can identify if that user has been hit or if they've had a number of traumatic incidents. Now, by doing that, what we're hoping we're doing is we're minimizing risk and minimizing, I guess, permanent head damage. Now, the way this actually works at the moment is the accelerometer comes into our platform, and we run what we call an in-memory database called HANA. Now, HANA captures all this information, provides that feedback, and therefore we can get that information, and then by providing that visualization, the coach can make some real-time insights into what they need to do. Now, I've spoken about these 3 different technologies, but one area that I've been focusing a lot more recently, and it is very applicable to the wearable space, and I'm not sure if someone is talking about it today or someone's presenting about it, but the whole idea of TinyML. Now, a lot of the examples that you've seen up until this point in time, I guess, has a traditional way of being able to process the data, right? Where basically, you know, we have the data comes in, we grab it on the sensor, we can then either process at edge or in the cloud. But what that means is actually the processing happens outside from the device. And what there is there's different, I guess, different impacts or different things that we need to think about when we do such things. It creates probably, you know, I mean, there's more energy that needs to be consumed. So these small transducer devices are sitting there having to process and being able to transmit the data. The other thing is that privacy by design, and I'll talk about it here. What we can do is by actually processing the data on the device itself, you know, we're not having to send it to cloud to be processed. What we're actually doing is we're performing the analysis on the device, and therefore we're sending a score to the cloud rather than the actual information. And what that really does is that helps with privacy. One of the big challenges, and especially being a company like SAP, is we want to adhere to things like GDPR, right? So the last thing we need is, you know, being able to capture people's information and then having that information, you know, on the internet, then being exposed to other organizations. So one of the things we're looking at doing is obviously utilizing technologies such as TinyML to do the processing at the edge, to then, you know, be able to send that information, not so much the raw data itself, but the score. And the other benefits are things like it has, you know, obviously reduced and best latency, and then we don't have connectivity issues because at the same time all the processing happens at that point. So if you're interested, there's a whole community. I know that there's TinyML. I run the TinyML community here in Australia and New Zealand, but there's ones in Asia, ones in Europe, ones in America. It's definitely a key area which, you know, if you're not already looking at TinyML, jump on board tinyml.org. And the vision of TinyML is to have this at, you know, milliwatts power consumption, and that's why the benefits. And actually a lot of these examples, especially the examples I saw in the last presentation by the team at Cambridge, is really associated to, you know, low power consumption moving forward. But I've shown you where we are, and now obviously TinyML as a technology we want to use to move forward, but then some of the other benefits as well. So some of the things that we're talking about is, you know, wearables pack a lot more compute power than what we've previously known. I currently am wearing my Apple Watch itself, and I check it regularly to check my heart rate, oxygen, blood pressure. You know, we've also got ECG, and we're also looking at different things moving forward as well. You know, and I guess not only is it around being able to track like ECG, blood oxygen levels, but then also identify, you know, we've worked on several different projects where we're using the Apple Watch with stroke victims to identify, you know, how much shaking there is, and also being able to perform different exercises on the Apple Watch itself. And another area we've been working with is obviously with defence personnel. One of the key areas we want to do, we're not only with defence and policing, is identify fatigue. Not only fatigue, but also, you know, identify how different things might impact officers. So, for example, you know, if officers go out into a field and they need to do, let's say they have to travel for 1,000 kilometers wearing a certain backpack, what are the impacts? And so what we're doing is, you know, using this technology such as the watches to track that down, and then giving them different meals and seeing how well they perform. And so using these kind of metrics to make sure that, you know, we have officers then in best condition to be able to move forward. And obviously the adoption is increasing, right? So I know a lot of people in our organization, whether it be Fitbit, Garmin, Apple Watch, are using this information to track. And, you know, employers are taking note and incorporating this into their people strategy. And definitely this is something that we are as part of our HR system. And as mentioned, you know, we get financial benefits for tracking that kind of information. So the whole idea is also prevention. So the use of wearables to promote an active lifestyle, cardio, biking, and everything, and physiological assessment of stress management. So we find that, when people are more active, they kind of, are less stressed and have more activity. Early identification, so use of data like temperature, SpO2, heart rate variability, predict illness as well, and detect early treatment and support is something that we're looking at. This is actually work I know that we did back in the day at Monash around identifying hypertension with early Bluetooth devices using the Open Data Management Platform. This is now evolving and getting even better with some of these newer devices moving forward. And basically also equipping employees the ability to self-service, right? And I want to be, again, emphasize here, as an employee, you don't have to participate in these programs. You have the choice to participate. And then, if you do participate, then say, actually, I want to withdraw, you can withdraw from the program, and you have control of your data. You can delete the data, you can do whatever you like with it. As SAP, you have the total control of your data. And when the data is stored in our environment, it's secure, it's held, so there's no GDPR privacy issues there. We're also looking at it for possibly recovery, right? So the whole idea of support employees with chronic conditions like diabetes and remote monitoring, right? And also then tailoring of treatments through analysis of data, and obviously reducing healthcare costs and absenteeism, some of the key things. To also give you a look, what you saw before was kind of like desktop. We have a mobile app as well. And what we're also looking at doing is looking at different things to work with different agencies. But here's, for example, here's an example of the Fit at SAP change approach. So what we're looking at is, the different things such as, future concepts such as, clever insights from devices, aggregating health data, putting things into different things. This is done without compromising the privacy, as I mentioned before, the privacy of employees, and looking at creating partnership with healthcare providers, insurance companies, wellness and holistic providers. And that way, with this kind of insights, we'll make sure that, the employees, especially employees that work for SAP, have that coverage, have the ability to enter these health and wellbeing programs to be able to access that kind of information. So some key things some key things I want to kind of finish up on is wearables will be an integral part of people's strategy for health moving forward, without comprising data privacy and security. Future concepts of employee health and wellness platform packs, the power of insights are derived from wearables, and wearables can change the paradigm of duty of care from employees significantly, right? So this is us actively, as employees, actively engaging and making sure that we can keep it forward. Now, I want to finish off with an interesting quote, actually, and this was from Tim Cook. And I guess if you zoom out into the future and you look back and ask what was the question, what was Apple's greatest contribution to mankind? It will be about health, and really for them, their Apple Watch has been probably their biggest seller. They are actually now, I think, the largest watch manufacturer in the world because people are using the Apple Watch for all kinds of things. One of the key areas are being health and well-being. So it's something which you can show, something simple that started has now created quite a big emphasis. But I wanted to be quick because I know we were obviously short on time, but I hope that gave you some insight into how we're looking at adapting wearables in the corporate life. If you have any questions, please feel free to email me. I'm happy to get in touch if you want to know more about our programs. Keen to work with that. We're also doing a lot more. There's another program we're working on around something called Project Vitality, which is a digital twin of the person to, again, holistically look at how we manage and health people, look after people. And there's a lot more activities moving forward. So if anything's of interest or if you want to collaborate, I definitely saw some interesting presentations that I might be interested in collaborating with, but please feel free to reach out. I'd love to hear from you. So thank you.
Thanks a lot, Dr. Tonilopoulou. There are questions from the audience for this presentation. There is the question about an answer tool which can be used by the audience. Okay, in the meanwhile, first of all, I would like to thank you a lot for the great presentation, a lot of interesting information which could be shared. In the meanwhile, I have one possible questions.
Sure.
Could you please tell us which is currently the devices, the sensors which are mostly employed for health purposes, if there is something significant apart from smart bands, and possibly which is the feasible future next disruptive, also in this case, commercial devices which could be deployed?
Yeah, look, that's a good question. At this point in time, the one that we're seeing obviously most interaction is obviously the smartwatch. Emotive is an interesting space. So now the whole idea of using earphones to also track brain signal connectivity or brain signal activity, to me, I think there's a potential there. But I think even utilizing, I guess, even concepts like the camera, I know that using, I guess, the camera technologies and even cameras now on our notebooks are getting more sophisticated. Being able to identify if people's eyes are directed at the screen, how often they're looking at the screen, if they're distracted. So for me, I think the evolution of some of these things and maybe coupling, these things, let it be from your wearable to the camera, to maybe the earphones and your brain activity, getting some greater insights and then providing even more information so us to then be able to support the person moving forward. So I think there's the disruption is how we combine some of these capabilities together and then get some deeper insights in how we can really impact and help the health and well-being of employees.
Okay, many thanks. Out of curiosity, for the emotive EEG data collection, are the example we have seen, do they collect the data through the in-ear electrodes or something different?
No, there's little electrodes in the actual headphones themselves, and that's where they collect the activity. Emotive have actually done this for a while, and they had proper headsets, but I think people. I know I used it a few times. It was a lot challenging to try and keep wearing this headset, and it wasn't very flexible. And although it had Bluetooth, it still wasn't a comfortable device to be wearing. So that's when they decided to work on their the little EEG signal capability within the headphones to capture that capability. So I think that's definitely the great bit of technology that they're working on at the moment.
Okay, we have a question actually from Elena Bergamini. Thanks a lot, Dr. Nicoloudis, for your amazing talk. Very interesting indeed. I was particularly interested in the sports-related application you showed us. Could you comment on the validation process beyond the development on marketing on wearable devices in that specific context, like the rugby-related one you presented?
Yeah, look, this was actually done. The university was done out of the UK, and it's a proper business solution now. They validated it with I guess rugby players, and as you can see here, it's actually being used in real life over in the UK for capturing this information. The data is specifically at this point in time for male rugby. I imagine, to take it a bit further, we could also, if any females play rugby, might have different implications, different kind of insights. But this has now been tested, validated, and working with this team. It actually won last year. It won Most Innovative Sports Technology Award. So it's definitely something which has been tested and validated with the rugby community, and I think now we're actually starting to see some other avenues of where they're looking at using this, let it be boxing or some of the other sports, but rugby is where it's been tested so far, and we've got that insight.
Okay, many thanks.
Great.
There are further questions? Oh, another question just now. Can you provide notable policies which resulted from the EEG measurement data?
Notable policies. Sorry, just what exactly do you want to, or can we get, I guess, a little bit more detail? What do you mean by notable policies? What is meant by? If we could have some clarity on that one. At the end of the day, with the EEG data, they definitely, you know, what we found out of the experiments that they did is they found that, you know, once the users, when we tracked them, we noticed that the user was finding or was distracted or had the concentration. We found that by taking the break, they came back and were far more productive. There's a paper that's been published, and maybe I can share the link to that particular paper because that was done with the Emotive team. But there's definitely I guess the academic you know, results there to provide, I guess, the validity of that concentration moving forward. So maybe what I'll do is I'll put the chat, I guess, the link to the paper that was related to that particular study.
Okay, many thanks.
Great.
We still have some time, so I don't know if there are further questions from the audience. Seems there are no further questions at the moment.
Sure.
So if that's the case, thank you once again, Dr. Nicoloudis. Thanks for your availability and for the great presentation you gave us.
Thank you. Thanks so much.
Thanks you a lot. So we can move with the program, and the next lecture will be given by Dr. Danilo Pietropau, and is entitled, oh, sorry for the too much ahead. And the next lecture will be given by Dr. Danilo Pietropau, and is entitled Design an Interoperable Deeply Quantized Neural Network for In-Sensing Computing. Dr. Pau is Technical Director of the System Research and Application Laboratory at STM Microelectronics. He has joined ST Microelectronics 1 year before graduating from the Politecnico di Milano in 1992. He has worked on HDMAC and MPEG video memory reduction, video coding, embedded graphic, and computer vision. Currently, his research work focuses on developing a solution for deep learning tools and application for resource-constrained devices. Danilo is IEEE Fellow since 2019, serving as Industry Ambassador Coordinator for IEEE Region 8, South Europe, and member of the Machine Learning, Deep Learning, and Artificial Intelligence in the Technical Stream Committee of the IEEE Consumer Electronics Society. He has authored 81 patents, 106 publications with H-index 24, 113 MPEG documents, and has been invited in over 40 talks and seminars at various worldwide universities and conferences. Today's lecture is about challenges such as balancing storage, computational capabilities, and achievable accuracy when implementing artificial neural networks on ultra-low power devices such as microcontrollers, with specific emphasis on deeply quantized neural network. So I assume Danilo again is with us.
Thanks, Emanuele, for the nice introduction. Yes, I am connected.
Welcome, and it's a pleasure to have you, and I can give you the word.
Thanks so much, and thanks again for the nice introduction, much appreciated, and also for the invitation that allows me to have the opportunity to speak about our developments from both a research point of view, but also from a path to go in production on the topic of embedding neural network computation into a sensor, which is a huge challenge, and we will see in a while why that's a challenge. To understand that, let me introduce a little bit also the methodology that we need to address and all of us well known that the most adopted deep learning framework from an industry and from a community point of view is based on TensorFlow technology, which allows to design neural networks, both in floating point accuracy as well as with 8-bit precision in two modalities, training-aware quantization and post-training quantization. Obviously, the first one, the former, would allow to achieve better accuracy than the second one. For image application, it has been proved to be the accuracy kept on par with the one achieved during training. However, we see the rise of a new framework which has been built on top of Keras, which is another deep learning framework tightly coupled with TensorFlow, developed by Google. And QKeras had the capability to freely select the bit depth of the various parts of the neural network in terms of activation, in terms of weights and biases, with the bit depth variable between 1 and 32 bits using fractional arithmetic. Why this is important? Because allows many opportunities to reduce the footprint of the model as well as the bit depth of the computation, enabling huge power savings. Let's have a look to an exemplary convnet, which is expressed in QKeras. Instead of the standard conv to the call, one can recognize in blue the QConv to the convolutional calls, which are interleaved with quantized activations and quantized dense layer. These calls allows me to specify the bit depth of the kernels, for example, 8 bits, and as well as the bit depth of the biases. In this example, 8 bits means 7 bits of fractional depth, 0 of integer, and 1 of sign. Also, the activations are explicitly quantized thanks to the call of Q activation. In this example, you can see 8-bit activation quantization as well as binary quantization. So infinite opportunities are available by playing with variable bit depth at all the levels. And once the topology has been defined, there is also a nice report that allows me to essentially profile the number of multiplication additions and also the precision they've been using. For example, if single precision floating point, if signed 8-bit multiplication, if signed, if XOR 1-bit multiplication and additions, because in this case, the topology was hybridly binarized, keeping some operation in floating point and the other in 8-bit. So one can mix and match the precision as it allows to achieve an expected accuracy. So this introduction is important because it proposes a new fundamental way to design neural networks, which are, since the beginning, complexity aware, in the sense that I can save a lot of memory footprint, a lot of computational complexity since the conception state. Now, let's try to design a neural network, and especially let's try to understand what are the implications if we want to embed such neural network in a sensor. The first obvious choice would be to use a microcontroller. Unfortunately, the microcontroller consumes, and in this case, an STM32L4, which is already power optimized, is suggested 100 microampere per megahertz with a significant memory footprint, 1 megabyte of embedded flash and 300 kilobyte of embedded RAM, which are an important contribute in terms of power consumption. On the other side, an off-the-shelf INEMO accelerometer and gyroscope on the same die integrated in one single package essentially suggests that the sensor itself is 70 times smaller than the microcontroller itself, 1 order of magnitude lower in power consumption, 30 times lower in terms of memory, because the sensor itself embeds around 10 kilobytes of RAM, and there are no flash in the sensor, as well as there is a huge difference in terms of CMOS technology, because the sensor uses an old 130 nanometer technology. Therefore, these push very challenging requirement in terms of die area, less than 2 square millimeters, in terms of CMOS technology, an old technology because it's very cost effective, low power, low memory footprint. And therefore, we need, since the beginning, to design a neural network which is able to cope with such challenges. Therefore, we need to investigate tiny neural networks which are also deeply quantized. How? Using the methodology I just introduced. So one opportunity is pushed by binary neural network. And why binary neural network are so promising? Because if we implement multiplication and addition operators, which are at the base of the computational kernel of every neural network, these require significant power consumption that, compared to an equivalent 1-bit multiplier and accumulator, there are several, at least 3 orders of magnitude of power saving compared to full floating point. And also there are equivalent power saving in terms of memory operations, especially considering the external RAM. Once again, 2-3 order of magnitude of power saving. So very nice from an implementation point of view, area saving, power saving, this is what we need to try to meet these requirements. And the binary neural network essentially are based on sign instructions, and depending on the sign, single bit represents both the activation and the weights, and therefore there are no multipliers, there are huge memory footprint saving, and the instructions to accelerate binary multiplier are based on a simpler XNOR and with the leading bit count. However, this poses challenges because what is the accuracy I'm going to achieve? Hard to believe that since the beginning, by binarizing a neural network, the accuracy versus a full floating point neural network is kept. Secondly, we need to implement a single instruction multiple data which are able to cope with parallel XNOR. And this implies that any compiler producing code for the target machine will be impacted. So let's take an example, human activity recognition. I want to recognize a case study. I want to recognize my activity. I can do it if I'm running, sitting, walking, and so on and so far. I would like to use, I could use an image-based sensor or an inertial sensor. Obviously, the choice for me is the second one because it's tiny, it's low power, and inherently produce a low data rate, which means that inherently I can process less information, less samples, and so saving complexity. Applications are various, from assisted living, healthcare, fitness, fall detection, and so on and so forth. So in this case, if I use a sensor, an inertial sensor, I have to play with two fundamental configurations. An ultra low power mode where 10 micro ampere of active power consumption is concerned using only the accelerometer. But if I use both the accelerometer and the gyroscope, then the current consumption jump dramatically to an half of milliampere. So I have these two modalities to play with. What does it mean? It means that any further power consumption I will add due to the acceleration of any machine learning approach I would like to add need to be comparable to these, shall be in the same envelope of that power consumption. Otherwise, there is no reason to embed such a logic. I could use off-the-shelf microcontroller, which are not fully integrated on the same die, on the same process, and so on and so forth. While this is exactly what interests me. And in this case, I could design three types of neural networks, three types of pipeline, with or without preprocessing, considering that I can work with only the accelerometer or with both accelerometer and gyroscope. Why it is important, the preprocessing? The preprocessing essentially is composed by two stages, filtering and vector rotation. The former allows me to separate, let's say, the high frequency from the low frequencies, which means the gravity from the other frequencies. And the second allows me to rotate the local reference system in order to be aligned with the fixed reference system. And therefore, I need these two stages, while the second is based on the well-known Rodriguez formula for the reference axis rotation. Now, the point is I cannot accept to implement this in full floating point, and I need to save complexity. Therefore, a full study on fractional arithmetic has been performed in order to allow the preprocessing to work either on 28, 24, or 20 bits with fractional arithmetic 8.20, 8.16, 8.12. In both, in any situation, the both stability check need to be ensured. Moreover, the cutoff frequency deviation shall be kept under 1%, under an acceptable threshold, which is guaranteed only up to 24 bits. And this is our choice. Let's go to the binary, to the hybrid binary neural network. That is the next step after the preprocessing. Here we carefully binarized some activation right after batch normalization in a couple of stages, after the first convolution and after the second fully connect layer, because the other configuration were not deemed adequate. The weights are binarized. What to say, we experiment a different configuration. Full binarization of the network in red, obviously the accuracy dramatically dropped. Second, in yellow, we just avoid to binarize the input, which are considered 16 bits, and the parameter for the batch normalization. In that case, the yellow curve shows an increased accuracy, not yet satisfactory, while the green one, which is now satisfactory, is achieved by the pipeline depicted in below with the careful quantization of the activation, while, as I said, the weights are always quantized, binarized. Here, the advantage is that 62% of the operation are binary, which means that they can be implemented using binary multiply and accumulator. We tested the accuracy with k-fold validation on PAMA2 and SHL dataset with 5 activity, with 12 activity, with 8 activities. And you see that essentially on hand, the accuracy of the second configuration, acceleration without preprocessing is compromised because rotation of the ends are captured and are compensated by the preprocessing. That's why the first architecture is more performant. However, on the chest, this is opposite because the preprocessing add only noise to the samples, compromising a bit the accuracy versus the second architecture. using always the inertial and the gyroscope, sorry, the accelerometer and the gyroscope without pre-processing, achieve the best accuracy, the top accuracy. Fine. However, we need to remind ourselves that the gyroscope is quite demanding in terms of power consumption, also of milliampere. On 12 accuracy, the same type of comments can be made. The first architecture is not worth to report because it was really inadequate in terms of performances. On SHL, once again, we have better performances on bag, hand, hips, because the pre-processing add further noise, and because in these conditions, especially on bag and hips, there are no significant rotation to be captured by the compensated by the pre-processing. So in all configuration between about 62% and a little bit more of the operations are binarized. But if we use also the gyroscope, there is a 75% increase in terms of weight memory, and the computational complexity is doubled. However, worth to notice, we are referring to less than 2 kilobyte parameters footprint, and about 50,000 operations, 62% of which are binarized, assuming one classification per sample. So all in one, this could work really at very low frequencies, 50 kilohertz, which is a further help to the power consumption. In terms of hardware acceleration, that's the circuit for the pre-processing, is a pipeline of 3-boot multipliers, 2 carry ripple adders, reiterated in order to, in time sharing, to implement both the filtering and the Rodriguez formula. And the hardware accelerator for the hybrid neural network is essentially composed by a pipeline of core with a serial input parallel output buffer, and with FIFO. There is an additional variant where activation are stored on a small RAM of 2.6 kilobytes. So as you can start to understand, the less than 10 kilobyte requirement can be ensured. The internal part of each processing element, in both cases, full FIFO internal storage or partial FIFO RAM for weight, is presented very simple in the sense that is a cascade 3-level of adders, 16-bit adders. Let's go to the analysis in terms of power consumption. First of all, we say that in ultra low power mode, the accelerometer is about 17 microwatts. Well, in our cases, consuming the design running at 258 kilohertz, achieving 1.5 classification per second, we were on par with the accelerometer in ultra low power mode. So we are in the ballpark. But in this case, using a CMOS 65 high voltage, HVT high voltage threshold, HEVT technology, we were on par. Now, the point is that the circuit has been stimulated using a maximum switching rate, which is not realistic, is a very worst case. So if we go to a realistic case where the circuit is stimulated by real case pattern, even the power consumption is a third of the one of the accelerometer. And therefore, in this case, all the specs, less than 2 square millimeter area, power consumption comparable to the accelerometer itself, less than 10 kilobyte power memory footprint can be met. On 130 CMOS technology, we will see the footprint of the single processing element was about 2 square millimeters. So it was on par versus this requirement. While on 65 nanometer was even better. Let's extend this on anomaly detection for fault diagnosis. And let's assume you want to detect anomalies due to malfunctions of bearings. In that case, we use the CWRU dataset as a source of data, and we designed an extension of the previous circuit based on an autoencoder. So in the top part of the image is an encoder and decoder, and in the bottom part is a classifier. So what is the logic here? The encoder-decoder is capable to detect anomalies. When anomalies are detected, they are classified. So we need an high precision classifier, which is not necessarily deemed to be implemented into the sensor. This could be implemented into the microcontroller itself, while the encoder and decoder are required to be implemented in the sensor itself. So in this case, the accuracy achieved by the autoencoder, which is once again an extension of the binarized autoencoder I presented before for the human activity recognition, and the R is really close to 100% on the on CWRU, and the area under curve is 0.99. However, if we go to the classifier, we notice that the accuracy of the classifier tends to improve if the input window is extended from 24 activation up to 600. When we have 600 activations, then the accuracy starts to be interesting, close to 95%, assuming that the classifier is implemented in full floating point accuracy. And that's the point. While the encoder is binarized as previously explained, and as well the decoder, especially after the first deconvolution stage, the classifier instead is a full floating point because there is no advantages in binarizing part of it. Otherwise, the accuracy will drop significantly, as well as is needed to extend the observation window at its input in order to achieve the expected accuracy as commented before. Here, a profiling of the complexity. Once again, a lot of operations have been binarized. However, is the hardware architecture of the circuit, as you can see, has been extended. It has been fully pipelined. The encoder feeds through a buffer the decoder, which is specular to the encoder, controlled by a controlling unit. And if we go down to inner part, you quickly recognize that the processing elements into the decoder are very similar, if not the same, of the encoder architecture. So this suggests that we can pipeline both, or we can reuse the same encoder architecture in time sharing to implement both in order to increase area savings. The latency is about, of the circuit is about 123 cycles. We input 16 samples, and the processing takes 3,632 cycles. We did an implementation of a tiny FPGA versus the state of the art. We reported the accuracy versus while the others not. We are superior in terms of dynamic power consumption, and that's thanks to an extensive usage of saving techniques based on carefully design of the hardware operators at 16 bits, leveraging the fact that 62% of the pipeline was binarized. 16 bits is due to the accumulation, inner accumulation during the operation. Also, the total power consumption is definitely one order of magnitude lower. and we save, sorry, and we save a lot of lookup table RAM and flip-flop. Frequency is halved, essentially. The operating frequency of the circuit of the FPGA is halved, and we save a lot of dynamic power, because when I'm referring to 0.122, actually 100 milliwatt are due to quiescent power, so the active power is really marginal. Most is due to the quiescent power of the FPGA itself. When we go to silicon process, especially on 130 nanometer HVT, max frequencies is up to 100. It could achieve also 250 megahertz in 64 general purpose technology. But what is important is that also the ODR, so the sampling frequency of the sensor, could be pushed to more than 1 megahertz. Actually, we are not, as ST, producing such high frequency accelerometer. So the computing capability of this circuit are well above also of existing sensor. Once again, the dynamic power consumption tend to be higher in 130 nanometer, lower in 65, with an ODR measured at 20 kilohertz, showing that also the greater part of the technology, of the power consumption is due to leakage. Considering that we are using a TCMC technology, Euro practice, so we are not referring, I'm not referring to a particular ST technology. So there is ample space for further optimization. In terms of area, 3.5 square millimeter and 130 nanometer, in 65 and half of square millimeter, which is really a tiny architecture that can be further optimized if we sacrifice the full pipelining of the hardware design. Classifier. The classifier has been implemented on STM32 microcontroller, and therefore in running mode, the current consumption is 80 microampere, because let's remind that the classification is performed only when detection, an anomaly is detected for just 8 milliseconds on an 80 megahertz microcontroller, and which is an L4, STM32 L4, and the properties of the classifier has been automatically profiled using Xcube, which is a tool that automatically generate and validate pre-trained neural network on our microcontrollers. The footprint of the classifier is 300 kilobytes, RAM 5 kilobytes, so there is no point to implement such a classifier in the sensor itself. It can be hosted as another of the many tasks the microcontroller can perform, also leveraging the fact that there is a floating point unit in the microcontroller architecture. That's nice that's our story from a research point of view, how this is going to impact production. We are announcing, actually it has been announced at the IEEE sensor conference, the IIS3IS sensor. This is a super integrated inertial sensor with accelerometer and gyroscope, which is integrating on the same die at 130 nanometer a DSP using an enhanced 32-bit Harvard architecture, where dedicated instruction accelerate binary network running up to 5 megahertz with an ODR of 3 kilohertz and 10 megahertz with an ODR of 6.6 kilohertz. The device encloses also 40 kilobyte of RAM, which is used to host both program and and temporary buffer during the neural network execution. In terms of benchmarks, benchmarking this ISPU versus a general purpose microcontroller, such as a Cortex M4, which is already a very tiny microcontroller, there is one order of magnitude power saving at both 5 and 10 megahertz, which definitely allows to be comparable to the power consumption, assuming that we are using also the gyroscope. Let's remind that the gyroscope is quite demanding in itself, it was quite demanding in terms of current consumption. When we benchmark an hybrid binary network on the DSP, which is super integrated with the sensor. Let's remind that this is a micro machine, and on the same time we have some logic which is integrating the DSP. We have a huge saving in terms of footprint, an order of magnitude, not so much in terms of execution time, 30%, but due to the fact that this is a realistic network for anomaly detection. While if we would assume a fully binarized network since the beginning to the end, then there are many more advantages, both in size as well as in execution time, because the binary multipliers are parallelized to an instruction word of 32 bits. I hope I wasn't too much out of the time. Sorry, I didn't measure my time, but I wanted to share all the information and all the effort we are doing from both both a research point of view as well as production point of view in terms of the hot topic, at least in our opinion, of embedding on the same silicon neural network machine learning algorithms super integrated with micro machines. Thanks a lot for your attention, and I'm very open to get any question you may have.
Thanks a lot, Danilo. Actually, the presentation has been really great, full of very interesting cutting edge elements. There is one question I see from the tool. Thanks for the talk. It was really interesting. I'm really interested in this topic. I would say that I have one curiosity more than an actual question. I was wondering if there is some research ongoing in embedding generative adversarial network, and if yes, how are the performance?
We are looking to into these from a toolchain point of view. So, for example, one of my efforts is on tools that automatically allow the deployment of pre-trained neural network on such a device. So in terms of operators, layers that are needed by a GAN, the tool allows the deployment. I cannot comment on performances because so far I was not yet focused on a use case that pushes the need of GAN network. However, I am running a project with the University of Glasgow trying to design generative adversarial network to improve security aspect of neural network, especially on visual and audio applications.
Thanks a lot. Actually, I think that beyond also wearable computing, these applications are very interesting also for edge computing and all and every application that requires computing the raw data directly from the sensors. There are another questions.
And we are trying to push even further. I think there is a great space to further go down to these type of solution. What I mean is that, for example, what does it take to embed machine learning in environmental sensors. And so go even down to area and power consumption in such cases. So, sorry to interrupt you, Emanuele.
No, many thanks, many thanks. There is another question. What are your comments on potential use for home continuous monitoring of gate analysis and balance?
This is one of the domain we had in mind when designing such a solution. Continuous monitoring means also suggests also the capability to be always on in terms of sensor. And this is one point. The second point is to be in a kind of sensor swarm scenario where you can have a lot of samplers, which are the sensor themselves, distributed in an environment that are measuring itself from different carry position of installation positioning, and having them to be independent, to be also ultra low power in order to dramatically extend any battery powered system they are embedded, and to be independent from the microcontroller was one of the requirements that pushed us toward this direction.
Okay, many thanks again. I have one curiosity just from a technical point of view. I haven't understood, maybe I missed it, but the training of the network is done offline, directly in binary version, or do you first train with floating point position and convert them the outcomes?
That's a very nice question. Thank you, Emanuele. That's why I introduced QKeras at the beginning, because QKeras, which is a drop-in replacement of Keras, part of the Google offering in terms of deep learning framework, allows training-aware quantization. And therefore, when designing the neural network with Q, conv, layers, Q activation, and so on, the AI designer specify the bit depth he or she would like to use by the neural network, and then those drop-in replacement behind the curtains run quantization, dequantization using the Keras runtime, and therefore any quantization error is compensated by the training-aware step-by-step iteration. That's why it's important to have a view of such environment, because definitely are very important. Post-training quantization going so down in terms of bit depth, at least in my experience, proved to be inadequate in terms of accuracy.
So also for pre-trained network, they should be trained again, basically not from scratch, but almost in theory, just because they have to be trimmed to low amount of bits.
Honestly, I don't have experience on fine-tuning from a floating point network, but yes, I think the full training is required. Full training, full validation, and so on. At least it was what we did in this in the presented work.
So the architecture remains, and then it's trained again. Okay.
Has to be thought since the beginning as an hybrid binary network. Then, if I may, a further question could be, yes, but how do you distribute these bits here and there? And that today is an uncrafted project, is an uncrafted effort. However, we start to see tools that automatize that. For example, how to QKeras, which is based on grid search. If we want more optimized search, for example, based on Bayesian optimization, reinforcement learning, and so on and so forth, at this point in time, only commercial tools such as Google Vizier are offered, unfortunately.
Many thanks, really, actually. There are further questions from the audience. I do not see any additional question. So if no more question, I would like to thank you once again a lot, Danilo, and it has been a pleasure to have you with us, and hope you to see you soon in some occasion. Okay.
Thanks so much. Really great to be with you today.
Many
Bye.
thanks again. Really great, actually.
Thank you. Ciao.
So thanks again also to the audience. We will now have a lunch break. So we will be back with the workshop in an hour, actually, at 2:30 in Central European time. So have a good lunch and see all of you later. See you in a while.
See you.
Hi. Hi, can you hear me?
Yes, yes, indeed.
Okay.
Yes.
So good afternoon to one and all present here. Welcome back to the track 2 sessions. So I would like to welcome our speaker, Dr. Arun Vaidyanathan from Movelle, the Netherlands. So he's going to talk about wearable technology, simple is better. Arun Vaidyanathan is responsible for business management of the wearable sensors business line, including the Shanghai site and local Excensus engineering activities. Arun joined Excensus in March 2008 based in Excensus HQ Netherlands office. Prior to this role, he has been a lead engineer and a research engineer involved in developing multi-sensor fusion algorithms and leading technical developments for the Excensus inertial sensor modules business line. Arun holds a MS degree in electrical engineering from Ohio University, USA. So I would request Dr. Arun Vaidyanathan to start his session.
Could you please confirm whether you're able to see my screen?
Yeah.
Yeah, perfect. Thank you. Thank you for the kind introduction, and it's glad to be part of this workshop. Yeah, today's presentation I have titled it as Simple is Better. To give a bit of a context to this subject, my talk will highlight the challenges in wearable technology with the advances that's taking place in different technological domains. You see multitudes of data coming out from every nook and cranny, let's say, and managing this data and extracting relevant information is quite important. And my presentation will just dig a bit deeper into it and give some context from historical perspective onto why keeping it simple is the best way to go and move forward. So my first slide is, I just want to give an idea of what is wearable technology. I know we are in a workshop for wearable sensors, but when I ask this question to either young researchers or students, the immediate answer that I get or response I get is, oh yeah, the AR VR headset that most of the companies produce right now, that's wearable technology. Yes, that is part of the answer, but we have to look at it from a historical perspective. My favorite example of a wearable technology is basically us as human beings when we started our evolution trend with the discovery of fire and water and being hunter and gatherers of the world. You have a club in your hand. That is basically a wearable technology, or a spear that you can put it in your in a slingshot or so is a part of wearable technology. If you break it into essence, wearable is basically anything that you can wear on your body. So moving forward with that thought process, you can see a lot of applications of wearable technology. The simple things that we use on a day-to-day basis, like the shirts we are wearing or contact lenses we are wearing, or the AirPods, or the spectacles. If you're hitting the ski slopes, you're using wearable technology. If you have a bag, that's a piece of wearable technology, because that makes your life easier and helps you accomplish a set of objectives on your day-to-day life. And right now, this wearable technology has got a huge impetus with the rapidly changing landscape that we have seen the past 2 or 3 decades. And giving perspective to that, I want to say that this particular technology, what we call as wearable technology, has been a part and parcel of our human evolution right from the beginning. We have always been dependent on this. We will always be dependent on this, and there's no other way. Wearable technology is just a fancy term for the digital age. But one thing to keep in mind is we will be always using it and dependent on this. Moving forward, I just want to show what has happened in the wearable technology space over the past 2-3 decades. I mean, we all remember, I know there are going to be a lot of mix of age groups in the audience, but I come from an age group where we still used to write letters. And then things changed during the 1990s to 2000, where there was an internet boom. And moving forward into 2000 and 2010, the noughties, as we call it, there was a plethora of smart computing devices. And these smart computing devices enable a lot of applications to be deployed just on a handheld wearable device that you can just snugly fit into your pocket for your day-to-day usage. And what it started, so from the 1990s to 2010, 2015, we really started the connectivity, the true digital age started. I mean, I know some people would say, oh, it was with the invention of the telegram. Yes, of course, the communication process started, but in terms of digitizing communication, the true digital age started around this 1990s, because it's not about invention, but what the 1990s internet boom did was it scaled technology rapidly to be adopted easily by masses. I mean, that's the true success of technology. It's not about having access to technology only to a few pockets or a few geographical regions. But in 1990s and 2000s, we already saw the deployment of this technology to a wide range of geographical regions, and people of all ages, size were able to access this technology and able to access this information. And moving on in the 2010 to 2015 and later on after 2015, we also saw a lot of stress being put on computing infrastructure through cloud. And with this, a lot of data being accessible and available to lots of entrepreneurs and innovators. And this enabled the development of, let's say, body sensor networks, smart home concepts, cloud computing concepts, and basically machine learning and AI-driven analytics. Looking into the same analogy as we did with the hunter-gatherers thing, also I want to point out that machine learning or artificial intelligence is not something new. Our brains have been evolving for the past hundreds of thousands of years, and we have been passing on information from generation to generation, learning from the mistakes of our past generation. Take, for the example, this hunter or gatherer who is looking for new sources of food. They would try new sources of food and probably have some fatalities along the way, but they pass on this information about the food being poisonous or not. Is it good to eat, and it's good for yourself or not? And does it help you get this necessary nutrition that you need? So It's the same way if you take that process that we have passed from generation to generation, you can apply the same thing in machine learning and artificial intelligence driven analytics. Conceptually, if you think about it, we are collecting data sets about ourselves, the way we live, and we are running heuristics on the back with algorithms, though in a digital world, to learn about these processes so that they become, so we are basically training the machine to predict from our past experiences about what's going to happen. And that's what we did. It's just that with the help of the computing power we have, we are not going to take hundreds of thousands of years to evolve now, but we are going to take the help of machines to make our life easier and better for everyone. So all these concepts, in a gist, are not new, but it's just we are applying what we have learned from the past to new technology in the human digital world, let's say. And having said that, this was always key in a sense that we always had this thought process in the mind. The sensors were always going to get smaller and cheaper. The data was always going to be, let's say, become more affordable and more available and more accessible. But what changed the last 2 years is the pandemic. And the pandemic has brought about certain, it's acting as a catalyst to accelerate certain adoption of these technologies. So I just want to show you a video moving forward on what this has done, especially in the entertainment segment. I just wanted to highlight that this video is just a way of how certain applications are evolving with the pandemic. Like 5 years ago, this was not something needed. It was a comfort. You can work from your home was seen as a, let's say, a luxury for the high-tech people. But with the pandemic, it has become a necessity. And of course, people have to continue with their remote work and also produce goods effectively and efficiently. And so 5 years ago, this would have been just a luxury. But now with wearable technology, and especially technology from Novella, you're able to have people animate and produce content right from the comfort of their homes. And this is also an application that just came out, and due to the pandemic, we knew it, but the adoption rate of our technology because of the pandemic also accelerated because people were forced to work out of their small workplaces at their homes. So the wearable technology here is an enabler to produce content now for the entertainment world, but we also have similar examples in the health sector and also in the sports sector. Moving ahead, what we are trying to do is to have motion tracking as a service. As I mentioned, affordable information is only the key step. I mean, with sensor miniaturization and driving down on the costs, you get data from numerous resources, which is cheap. But this multitude of data needs to be filtered. I mean, depending on the application, these data need to be filtered, and objective data needs to be analyzed and presented in a form which is relevant to that particular application. So the context of this message is not only that the huge amounts of data is important, but to take further synthesize the data and extract the relevant parts of the data for your particular application is key. So So there is going to be a lot of research, and there is a lot of ongoing research in different fields, especially in human motion analysis, in sports and health, especially in performance improvement, in injury prevention, in both preventative and recovery mechanisms, to understand this objective data, to understand what are the deficiencies, how can we link the data to the deficiencies, and basically zero in on those biomarkers. So that particular relevant info is what we are targeting, and it will be more and more key moving forward. In the next couple of slides, I want to give you an example in terms of ergonomics and health and sports field about how this wearable technology is being applied. And here you see one of our Xsense NBN suits being used for two different applications. One on the ergonomic side to monitor workplace injuries, and on the other side, on the sports side, where a coach is trying to see how the trainee is performing her tennis serve, basically. So, and all of this is being made possible by digitization of motion. And why is it so key? I mean, when people think about it from a perspective of motion, it doesn't ring a bell, right? But about 3 or 4 decades ago, we were, at least I was using cassette players or 8-track players to listen to music. I mean, but that all changed in the 2000s, and in the 2010s, we all shifted to MP3 players on USB, the CD players, and AirPods, and iPods, basically. And that kind of changed the music industry. And so the key point is digitization in the music world changed the way the music industry worked. Different business models, a lot more application and a lot more accessibility of music, and it also brought about more talent to the fore with the digitization. Now, the same thing is happening in the motion industry. Take, for example, if you go to a physiotherapist about, let's say, 2 decades ago, even in some cases now, there are physiotherapists who wanted to, let's say, measure your knee mobility, basically, after you have come out of an ACL injury or so. And they have this goniometers that they use to measure the joint angles, and then they try to measure objectively what your range of motion is after post-injury, and how is it improving with all these rehabilitation exercises. What we are seeing is, with the adoption of these technology, wearable sensor technologies, the digitizing motion is for sure changing applications in the field of entertainment, health, and sports. And for now, physiotherapists are looking at just mounting certain sensors in the lower part of your body or upper part of your body, and trying to get objective data and complement it with their subjective analysis, that is their experience, to help patients recover, let's say, from rehabilitation, give advice on proper posture and motion, in gait. They are looking, technology is being used for injury prevention and injury recovery. As I highlighted in pandemic world, we are also seeing more adoption or more eagerness to adopt this technology in telehealth applications. Of course, we are looking at an explosion in the player and fitness tracking. And also we are looking at pre-surgery and post-surgery monitoring and recovery. And all of this digitization plays and helps in better interaction between human and machine applications, basically. So having said that, Movella in itself is playing a big role in digitizing motion, and we wanted to show why we are here. And to summarize what we are doing, we are already part of a very data-driven world. We have, as I mentioned, multitude of sensors spitting out huge amount of data. Making sense of this needs to be structured. Technology, of course, in all kinds of in different fields, is making this data accessible, affordable, and easily deployable. That means a lot of innovators, entrepreneurs are trying to apply this technology to new applications and trying to make things and life better for everyone. And the key moving forward is to how to filter and extract the relevant information out of this multitudes of data. And the next step and the most important part of the puzzle is to translate this relevant information into application-specific metrics, and also in an easy to use, let's say UI basically, either on your phones or on your iPads or on your laptops. And to summarize, the most profitable way and the most sustainable way to bring about change in in everyone's life by the application of wearable technology is to basically keep it simple moving forward. And that concludes my presentation. And I wanted to intentionally keep the presentation shorter so that I can entertain a lot of questions. Thank you. If there are any questions, I would be happy to entertain them right now.
I have a question.
Yeah.
Does wearable technology affect the environment? If so, how? And how it can be resolved?
That's a very loaded question, Professor Vadrajan. It's yes, indeed, wearable technology, especially sensor manufacturing, does indeed have an impact on the environment, at least 2 decades ago. But most of the chip manufacturers over the period of last years have taken a vow to make this particular sensor technology or production of wearable technology more sustainable and environmentally friendly, let's say. And there are pledges being taken by most of the biggest chip manufacturers and also companies like us, where we adopt sound practices engineering-wise, technological-wise, and also environmental friendly-wise. So yes, this is a big topic of discussion, and there is a lot of change happening in the industry, and a lot of things have changed in the last 15 years.
Thank you. So there is no more questions as of now. So if any questions comes, it can be taken offline to directly to Dr. Arun Vaidyanathan. So I would like to thank Dr. Arun Vaidyanathan for his special session and very detailed information and very useful, and how simply we can use wearable technologies, all those things. So thank you, sir. Thanks for your time.
Thank you. Pleasure.
So we are moving into second speaker. So I welcome the second speaker, Veli-Pekka Seppo from Revenio Research Limited, Finland. So he is going to talk about turning academic research to medical device business. Professor Seppa is currently working as an R&D manager at Finnish medical device company, Revenio Group. Since starting in the company in 2015, his main responsibility has been R&D for Revenio's Ventica system, CE Class 2A medical device. But he has also been involved in design, analysis, and publication of clinical studies, product marketing, and direct contact with key opinion leaders, customers, and distributors. In 2014, he founded a startup company to commercialize the Ventica technology, and in 2015, a license deal was made with Revenio. Seppa is the original inventor of the Ventica technology, which he developed as a doctorate student at Tampere University, Finland. He received his Doctor of Science in Technology degree in Biomedical Engineering with honors in 2014. During 2007 to 8, he worked as a visiting researcher at University of Berkeley, USA. He has authored over 30 peer-reviewed scientific articles. His H-index is 11 and holds more than 20 patents. I request Dr. Seppa to take it over.
Thank you very much. Thank you. Let me just try to set up my screen sharing. Can you tell me if you can see now full screen the slide there?
Yeah, it is fine.
Okay.
It's good.
Thank you very much. I hope you've all had a nice workshop on wearable devices. My presentation is actually not that specific to wearables, but I think it might be interesting for some of you who are thinking about commercializing your research at some point. So as the chair already described, I was a researcher at Tampere University in Finland, where I made research around a technology called impedance pneumography, which can be used for measurement of breathing. And at some point, it started to look like that this could actually have commercial applications and possibilities. And I founded a startup company to commercialize the research and the technology. And then while looking for funding for the company from different kind of investors, I ended up talking to a Finnish medical device company, Revenio, and they proposed to have a license deal with my company. And as part of that deal, I moved to do the R&D and various other tasks related to the technology at Revenio, and eventually a product called Ventica came out from that. So I'll try to share some pieces of information and advices that I've found or discovered during this rather lengthy journey from research to business. And well, the first step is, of course, forming a good team. So you'll need to first understand what kind of activities your company is going to perform and which one of those you want to have as a in-house and where you want to use external workforce. And typically the areas for a medical device technology startup could be like this, that there's you need to have marketing. Can you tell me if you can see a pointer moving there?
No.
No.
Oh, yeah, now?
Yeah.
Right. Yes,
It's
good.
good. Yeah,
Thank you.
good.
Thank you. So there's typically there's marketing, of course, as in any company, and finance, operations, meaning sourcing of materials and manufacturing, servicing devices, deliveries, warehouses, these sort of things. Then clinical studies in a medical device company, R&D, of course, and everything needs to be done under the medical device regulation. So there needs to be a quality department. And when you're forming the team, of course, you need to understand that working in a startup requires certain kind of mentality, and not anybody is fit for that kind of job. And of course, you can combine several tasks to one person, or one person can have more hats. And there are certain parts that in most companies make more sense to have done by external partners. Then IPR, intellectual property rights, that's a very important part in a technology startup. So oftentimes in the beginning, when the company is founded, it might not have many other assets than the team and the IPR coming from the research background. So it's crucial to have good protection for the IPR and inventions. The first thing, of course, that everybody understands when we're talking about IPR is patents, and they are really important. But there's also trademarks and design protection and trade secrets. So there are certain situations where trade secrets might make more sense, keeping your IPR or some parts of the IPR as trade secrets instead of patenting it, because patents and their contents become public approximately a year from filing. So after that, anybody can read how your technology and invention works and maybe come up with ways to go around your patents. Whereas if you keep your technology as a trade secret or some parts of it, nobody will know how it works, and it's more difficult to copy it or come up with similar approaches. And just as an example, that it's really worthwhile when you are forming your IPR protection to have these kind of brainstorming sessions with patent attorneys and patent consultants to come up with what you can actually protect and what you can patent. So for example, here is one of our patents, which is about where you can place these skin electrodes on the patient when you're doing this impedance pneumography measurement. So for me, it sounded first like a ridiculous idea that you could actually patent this, but then it turned out that you really can. So it's worthwhile to be innovative when you're thinking about what can be protected. So once the team and the IPR protection is there, it's time to look for funding to do the development of the product and run the operations and marketing. And there's many sources where you can acquire funding, like business angels, which are wealthy private persons interested in investing, venture capital firms that invest other people's money, basically. Even crowdsourcing nowadays, there's numerous examples of medical device companies acquiring crowd sourcing funding, which might first seem quite surprising, but it's happened. And then you should always leverage all the free money you can get from EU and your local government support. And then I guess as a last resort, you can apply for loans. So basically you'll need to have a good pitch deck and a business plan to be able to present your case to the investors. And it really can take quite a lot of time. It's basically a full-time job for somebody who's doing it. And like, it's not uncommon to use 6 months or more from the beginning to the point of having the funds secured at the bank account of the company or as a term sheet. And then it's time to prepare for the product development. So as I already said, it's really good to not try to have everything in-house in a small company, but utilize partners. And there's almost any area of the company can be externalized or done in part with external partners, such as hardware and software design, regulatory matters, clinical studies, and manufacturing and sourcing and IPR and so on. There's a picture here of me in a EMC, electromagnetic compatibility laboratory. There's you can't really see it, but there's the Ventica devices on the table there being tested for emissions and immunity of electromagnetic fields. And well, I mean, it's clear that this sort of facility, no startup can have that. So that's one example that is always practically externalized. And then you'll need to have it's, as far as I know, it's still not mandatory to have a certified ISO 13485 quality management system in a medical device company, but it makes everything much easier when you have that. I guess it's practically actually a requirement nowadays to have such. And what does the product development then look like when you do it under a quality management system? So of course it's company dependent how this is set up and organized, but what I'm showing you is, I guess, a quite basic scheme that most companies use. So there's a number of standards that the product needs to conform with, like general medical device standards, and then EMC, this electromagnetic compatibility devices, or standard specific for home use devices, and usability testing standards, software standards, and so on, so on. So they pose requirements to the product. Then this is always, or has been for quite a long time now, always increasing in importance, the risk analysis and management that is done by the company and is product specific. And then there's market requirements. Basically, this is what the customer wants. So somebody needs to really get a good insight of what is needed by the customer, how they want the product to function and how it should look like and so on. So from that, typically there's a top level requirements compilation, that might be called system requirements. And then it's is split down to smaller, more technical requirements. So if we think, for example, an example that the device should have, there would be a marketing requirement that the device shall have a reliable yet easy and fast way of exporting measured data to a computer. This could be one marketing requirement. Then when that is translated into a system requirement, it could say like the device shall communicate with the PC software through a USB 2.0 interface with a micro B connector. Then splitting that further down, it will give a hardware requirement or several software requirement and mechanical requirements. So for the hardware, it could be saying that there needs to be circuitry for USB 2.0 on the PCB, and there needs to be a micro B receptacle on the board as well. Then for the software, it could say something like that there needs to be drivers for communicating with USB, and for mechanical, it could say that the connector needs to withstand, for example, 50 Newton axial push force, and that there needs to be a connector for USB 2.0 or something like this. Then once the requirements are in place, it's time to implement it, meaning that everything is designed, hardware, software, mechanics, and so on. And at some point, if it's a device that is a physical device, so in medical device terminology, also a software is referred as a device. But if there's a physical hardware component to it, you need to produce it somehow, somewhere. And then you reach the stage of verification. So for each of these requirements, you need to have a test that verifies that, yes, it does conform to that requirement. There needs to be preset criteria, and you need to check that, yes, this criteria is met. Then usability testing is actually all along this way here, so that in the beginning you need to have just some really like a mock-up of the product, for instance, a PowerPoint pretending to be the software user interface, and then you start to ask the potential end customers that would you like it to look like this, and what kind of views you'd need, and so on and so on. And once you proceed with the development, at some point you will have the final end product or something very close to that, and then you can use it in the real environment with the real patients or subjects and real users. Once you have all these tests done and you're happy with the product, it's time to ask, at least in Europe, a certification body to evaluate that your product actually conforms to all the standards that are relevant to it. So basically there's a list of all the standard requirements, and they go through them one by one and finding evidence that, yes, you confirm your product passes this and this and this and this test. And then you get a report or certificate for each standard. Then a very important part, and oftentimes can be quite difficult even, is to perform the clinical evaluation. So this means that every medical device has something called intended use. So that's a very important few sentences that state that what exactly is your product intended to do in terms of clinical use. So for instance, that it measures the intraocular pressure in patients aged 5 to 60 or something like this. Or it can specify that it can be used in home environment, for instance, and so on. And then in the clinical evaluation, you need to find through literature, pre-existing literature, like published studies, or by performing bench testing, or then this is of course the most tedious way, by performing new clinical studies. You'll need to find evidence that yes, your product indeed does what you're stating in the intended use. Then you compile this all to a big set of documents, and that's handed out along with the certificates given by the certification body. In EU to something called a notified body, and in US the FDA, and they will then, if everything goes well, at some point approve your product as a medical device of certain class. That's that really in a nutshell. Then some points from marketing. So developing the marketing message, this is sometimes called the upstream marketing, is very, very important. So especially I think in companies with strong research and engineer background, you oftentimes have the problem that it's being marketed by like from engineers to engineers, instead of really trying to understand the needs of the customer and trying to position the marketing and the product like that. For instance, that you're saying that the device is an easy way to measure signal X. Whereas you should be saying that this is a product to help adjust the medications of patients with condition Y. So for average clinician, well, usually clinicians are somewhat interested in how the device works and what exactly is it measuring, but moreover, they're always interested in how does this benefit me and my patients in my daily work, and that's how you should position the marketing message. And that's really not trivial to understand it and to build it in the right way, and it should not be overlooked. It takes time. Then once the message is in place, you need to convey that message to the customers, called downstream marketing sometimes. So you need to build the marketing material like brochures, white papers, website, etc., and have presence among your customers. So there's often we use a term called key opinion leader, KOL, which refers to medical professionals that are highly reputable within the specific field of medicine that your product is in. And you want to be in contact with them, to have them use your device, do research with your device and so on, having booths at medical conferences and presenting new research results there and so on. And then all sorts of web ads, social media and so on. And I think the most important part is for medical devices is building credibility. So when we talk to customers, there's the most, let's say the main questions that they have are often for something that is completely new, that what evidence is there out that this is really saying what you are saying it is doing. And then the second question is that who sorry for that. So who in my country is using this? So they want to have reference customers. So clinical studies done in reputable institutions, large enough and published in good quality journals, and then customers. And then, as always, something unexpected will happen probably several times along the way. You just need to adapt fast to that. Thank you very much. I'm happy to answer any questions you might have.
I request participants to send your questions and question and answers tool.
If you have any questions afterwards, you can also just send me email. You can see my address there.
Sure. Thank you. Meantime, I have a question. Is all the medical devices has to be approved by FDA or not notified? In case, what are the challenges in it, getting the approvals?
Yeah, so once you have it, this really depends from area to area. My most knowledge is from European countries. So in every country, you need to register the medical device after it's been approved by, let's say, a notified body. And in some countries, they endorse either the approval by a notified body, the European notified body, or by the FDA, or then they might have even their own bodies. I believe this is the situation, for instance, in Japan. And well, either of those are the what the most of the countries endorse, the FDA or the notified body system, the European CE mark. But I mean, what are the difficulties along the way? Well, I mean, there can be just anything, because the evaluation and assessment that they perform is quite thorough. So it can concern like the manufacturing process or design process or lack of clinical evidence and so on. Really everything starting from the requirement stage, ending to manufacturing and clinical evaluation is under their scope when they evaluate the device. And basically the rule is that if it is not documented, it does not exist. So you need to produce a lot of documentation.
It's good, thank you. There is no questions as of now. If any questions participants want to get answers, they can approach offline.
Yes, sure.
Yeah, we have one question in the last minute. Could you speak a little about your experience seeking funding?
Yes, sure. So for me, with this specific case, I never really reached the state of funding because it turned into this license deal with the company that I now work for. But well, as I said, it can be a quite lengthy process, and usually for me the experience was that I was learning while doing it, so that the pitch deck was the material that you present to the investors was improving all the time when I was pitching it, because I received questions from the investors and I understood that, okay, this is something I need to have in the pitch deck, and having it more clever from week to week. But yeah, I mean, it's art of its own.
Thank you. As of now, there is no questions. So thanks for your valuable time and giving an idea about thinking about medical device idea to making it commercialized and making it usable by the people, and patenting and copyrights, etc. It's a full picture of building a medical device. Very useful information to the participants. Thanks again.
Thank you very much. Thank you.
So we will be having a break from now. After the tea break, next track will start. Thank you, one and all present here, and we'll meet again after the break. Thank you.
Good morning, afternoon, and evening to everybody. Just a few minutes and we will start with the fourth and last track of the workshop. So at 4:10 p.m. we will start. Hello, Professor Lee.
Hello, how are you?
Fine, thanks, and you?
Very good.
Nice to meet you. So we will
Nice
start in a couple of minutes.
Sounds great to me. Should I go ahead and share my screen?
Yeah, if you just can give me a couple of minutes to present you, I will share the slides and then I will give you the floor.
Okay, sure.
So here we are. Good morning, afternoon, evening, according to your time zone. We are ready to start this fourth and last track. I am Elena Bergamini from the University of Rome for Italico, and I have the pleasure to start this track about machine learning and artificial intelligence for data analysis and decision analytics. So not to put pressure on the speakers, but I am sure that this is a long-awaited session, as we've been hearing about the use and the importance of machine learning and artificial intelligence in many previous talks and in many contexts dealt with within this workshop. So I'm really sure it will be an exciting and enlightening session and track. So I'm very glad to introduce the first speaker of this track, Professor Ivan Lee, from the University of Massachusetts Amherst, USA, who will give a talk about the use of mobile technologies and advanced computer sciences to promote personal rehabilitation. So just a few words to introduce Professor Lee. Professor Lee got 2 master's degrees in electrical engineering and in computer science, as well as a PhD in computer science at the University of California, Los Angeles. Postdoc at the Department of Physical Medicine and Rehabilitation at Harvard Medical School, and currently assistant professor of computer science and of electrical and computer engineering at the University of Massachusetts Amherst. Senior member of the IEEE Society, Professor Lee covers and had covered different important roles within the IEEE. It is thus a great pleasure and an honor to give the floor to Professor Ivan Lee for his talk entitled Personal Rehabilitation Informatics Using Mobile Technology. So I give the floor to you, Professor Lee.
All right, thank you very much for the kind introduction. Can you also see the shared screen?
Yep.
Awesome. All right. Good morning, afternoon, and evening. My name is Ivan Lee from UMass Amherst, and I'd like to first thank the organizing committee for the invitation. Today, we're going to talk about personal informatics for stroke rehabilitation using mobile technologies and artificial intelligence. This is the content of today's presentation. I'm going to provide a brief overview of the unmet needs in stroke motor rehabilitation. Then I'm going to discuss two specific research topics that are quite important to be investigated in stroke motor rehabilitation. First one is assessment of upper arm use using wearable devices. And the second one is assessment of movement quality using wearable devices. The ultimate goal of personal rehabilitation informatics is really to improve patient care outside a clinical setting using mobile technologies and personal information. So we are talking about specifically stroke motor rehabilitation. So let me briefly go over what the stroke is about. So stroke is the leading cause of disability worldwide, and there are about 800,000 new cases of stroke per year in the United States alone. And we expect this number to significantly increase over the next couple of decades due to the rapidly aging society. Briefly speaking, stroke is basically a cutoff of blood flow that goes into the brain and which damages the brain cells, and as a consequence, the hallmark impairments associated with stroke survivors are this impairment is more prominent only in one side of the leg. So we have a therapist on the right side who's trying to who's asking the stroke survivor participant in our study to make the same movements with the two upper limbs, but we can immediately observe that this stroke survivor's left arm is more significantly impaired compared to the right arm. So left arm is her stroke affected limb, whereas her right arm is the contralateral or less affected limb. And this unique imbalancedness in motor impairments, which is prominent again only in one side of the limbs, creates a very unique challenges, mainly due to the discrepancy between capacity versus performance. That is, what subjects can or are able to do that clinicians would observe in the hospital setting, which is defined by patients' capacity or capability, does not always represent what patients actually do in their home setting, which is defined as performance. In other words, let's say we have a stroke survivor who can lift up his or her arm to a certain or decent range of motion, but that does not actually imply that the patient will actively engage that stroke affected limb while going about activities of daily living, because the patient actually has relatively less impaired limb and could make such an easy choice to just engage or use the unaffected side of the limbs to interact with daily objects. And in fact, patient's performance is the ultimate goal of rehabilitation, really to improve their performance of essential activities of daily living and therefore help them achieve independence in living. However, because there really is no objective means to monitor patients' performance in their home setting and what they actually do in the home setting, clinicians have to rely on sort of a subjective self-reports from patients about their own performance level, which obviously suffers from inaccuracy from subjective biases as well as memory recalls. And this has been identified as a major barrier that really hinders the development of patient-specific interventions that are designed to promote patients or improve patients' performance of in their home environments. And also for patients as well, because they really do not have access to their own data to understand how well they actually perform. It's very difficult for them to be more deeply engaged in the overall intervention or rehabilitation intervention programs. Whereas prior research has shown that if they indeed have access to their own data related to their behaviors, they can be more, that can actually help them develop and promote more healthier behaviors and therefore more engaged in self-care. So what has been advocated in the research field is to leverage wearable devices and mobile technologies to continuously monitor what patients do in their, again, naturalistic environments, deliver that information to the cloud system and analyze it using advanced computational models or artificial intelligent algorithms, and more importantly, carefully process the outcomes of the algorithms and deliver to patients. And most importantly, bring those information back to patients, that is the feedback from clinicians as well as their own data. And in the heart of this is so-called rehabilitation informatics. That is, what type of data or what type of sensors shall we actually place on patient's body or in their home environment? How can we actually analyze those large volume of data to extract relevant information related to their performance? And more importantly, how do we visualize the information so that we can give it back to both patients as well as clinicians so that they can collaboratively work together to help patients improve their performance level, so that ultimately we can put patients in the center of care. So what researchers are currently working on is really to transform the current rehabilitation care system from being hospital-centered, because most of the exercises and rehabilitations are happening in the hospital, and also somewhat reactive healthcare system towards patients' condition, into more patient-centered and proactive healthcare system. And in this talk, I'm going to discuss two specific projects related to this overall vision. The first one is assessment of stroke-affected arm use, and bring those information back to patients so that they can be motivated to improve the performance level via the process of self-monitoring. In order to further highlight the needs, let me briefly explain what the typical stroke care looks like in the United States. So the x-axis represents time, and the y-axis represents some arbitrary number of functional level. A patient is living a normal life with normal functionality and will experience stroke, and then as a consequence, the functional level would deteriorate significantly. Then patient will be immediately hospitalized and receive necessary care, and will go through very intensive rehabilitation care within the inpatient facilities, which spans for about 2 hours per day for about 3 weeks in average. And this is the period where they actually receive most of the recoveries due to the spontaneous recovery process. Then they will be actually discharged after 3 weeks in average, and will continue the care through outpatient facilities. And the goal is really to minimize this residual impairment compared to their functional level before the onset of stroke. And obviously, depending on the quantity, that is amount as well as quality of therapy that they receive, they could either maintain or even improve their functionality as they enter the chronic stages of their recovery. Or if they actually receive insufficient amount of therapy or poor quality of therapy, there still is a chance that their functionality could degrade over time, which is actually unwanted. Unfortunately, only 36% of individuals, stroke survivors, actually get to receive outpatient rehabilitation care in the United States. And for those 36% of stroke survivors who do receive outpatient care, they only receive 30 minutes per day, twice a week for about 3 to 4 months in average. And only 13.5% of stroke survivors get to receive long-term care beyond that 3 to 4 months of a period. And this is substantially insufficient to really support the maximal recovery that patients deserve to receive to improve their therapeutic outcomes. For example, you can think about the rehabilitation care as more like learning a new sport for neurologically intact and healthy individuals. So if there is a healthy individual who wants to become a professional tennis player, probably 30 minutes of training twice a week would not be sufficient. And we expect that person to practice outside of the training sessions and really swing the racket, per se, a million times. And similarly, for those who have lost their motor function, to regain that 30 minutes of a therapy session twice per week is not sufficient. The problem is, how can we improve the motor dosage, right? And our idea, again, is really to monitor how much they make use of the stroke-affected limb compared to the unaffected limb, deliver that information back to patients so that they can be motivated to engage the use of the stroke-affected limb while going about their activities of daily living, so that they can still engage their stroke-affected limb more and more in addition to the therapy that they receive in the hospital setting. And this design is really motivated by a therapy called constrained induced movement therapy. It's a very intensive therapy that conceals the unaffected side of the limbs using a half glove or a mitt so that it enforces the stroke affected limb during activities of daily living. Again, it is a very intensive care, which actually instructs the stroke survivors to actually wear this for 90% of the wait time for about 2 weeks. This is actually one of the very thoroughly validated non-pharmaceutical therapeutic interventions that have shown clinical validity to improve the functionality in patients. And researchers and clinicians were looking into a way to really extend that period of therapy beyond 2 weeks. However, due to the coercive nature and harsh nature of this therapy, it was very difficult for patients to adopt it beyond that 2 weeks of a period. And our approach to, again, extend this period where patients could actually indeed benefit from this is through a human-centered intervention design. That is, we want to place 2 wearable sensors on both limbs to monitor how much patients engage their stroke-affected limb versus unaffected limb, and using artificial intelligence algorithms to design or quantify how much actually they engage, right? And then visualize that to patients so that they can be more aware of their own condition and performance level, so that they can be motivated to engage stroke-affected limb while going about activities of daily living. And obviously, this has to be followed by a very carefully designed training session before this therapy interventions that they could increase their stroke-affected limb in more therapeutically desirable manner. That is, to minimize compensatory movements and really engage their muscles to properly perform the movements, which is similar to what constraint-induced therapy is currently taking. In other words, our design was really to take the therapeutic benefits of constraint-induced movement therapy and cost advantage of telehealth, as well as convenience of at-home training. So the key first is to monitor patients' upper limb use, right? So that we can quantify, oh, you're actually using your stroke-affected limb only 20% of the time, etc. So in order to do that, we used a miniaturized finger worn sensor, which contains a 3-axis accelerometer data and a ultra low power Bluetooth low energy system on chip. And the idea is to actually process this accelerometer magnitude to sort of represent how much they engage their limb during activities of daily living, which is similar to what fitness tracker or activity monitoring platforms actually leveraging. In the research community, the most widely adopted wearable form factor to obtain this type of data has been the wrist-worn accelerometers. However, the caveat to that is that it only captures movements up to the wrist, right? Their upper arm as well as forearm movements, which represent mainly gross arm movements, whereas our finger worn sensor could really monitor both gross arm as well as fine hand movements that is more relevant to the meaningful and goal-directed use of the upper arm during activities of daily living. And in a series of papers, we have demonstrated the clinical validity of this wearable device. Right. So first of all, because we're only engaging 3-axis accelerometer data, we need to inherently it contains a lot of errors to estimate the intensity of movements, because it also captures gravity. So we propose a probabilistic modeling to improve the accuracy of the sensor readings, and also deploy the sensors in both healthy individuals as well as stroke survivors in order to represent how much actually they engage their stroke-affected limb during a set of motor tests within the hospital setting as well as in their naturalistic setting, and try to show clinical validity of that. And not only us, for example, Professor Catherine Lang from Washington University of St. Louis has been a pioneer in this domain, and there actually is a large group of researchers who are working on this field to really quantify the performance level in stroke survivors. Another important question that we need to also answer is that with this large volume of data, what do we do with them, right? So that is, how can we bring those data back to the stakeholders, that is the patient as well as clinicians, so that they can collaboratively work together to understand the data and create a therapeutic programs so that we can eventually motivate stroke survivors to increase the amount of stroke upper limb use. And a way to actually find a sort of a solution to this is a qualitative approach, which our lab has been also heavily engaged in. So we conducted a preliminary and elicitation study to investigate the stakeholders' abilities and preferences for using our system. The mHealth system involves monitoring of patients' performance and how do we actually deliver the information back to patients. More specifically, we first investigated stroke survivors' perspectives for utilizing their own data to self-manage their at-home therapy. And to do that, we conducted a semi-structured interviews with the actual stroke survivors in their home setting so that we can better situate ourselves in their home environment, naturalistic environments, in order to better understand the challenges that they actually go through and really understand what information do they need. How can we visualize the data so that they can extract information that are relevant to their personally important goals? And for therapists as well, we also conducted a semi-structured interviews with 15 occupational therapists and really wanted to listen their perspectives for incorporating patient-generated, large volume of patient-generated sensory data in their therapy practice. For example, a lot of people say, with this large volume of artificial intelligent outcomes or sensory data, we can develop this patient-specific interventions, but we really wanted to understand what does that mean, right? What does that mean for clinicians to use those data to really tailor patient-specific information? So we wanted to actually hear their thoughts on that. So recently we published an article at ICM INWAT and have another publication that is in line. So far, we have talked about the amount of arm use, right? Using 3-axis accelerometer data to quantify how much or how long they actually engage their stroke affected limb versus the unaffected limb. And this is a very useful information compared to, for example, patient self-reports. However, it's still a very low dimensional data. Another important piece of data is about the quality of movements they actually perform. So let me actually also discuss some of the efforts that are actually put onto this dimension of research. So standardized clinical assessment of movement quality typically involves patients' performance of a predefined set of motor tasks. So over here, I'm showing actually 2 motor tasks pertaining to the Wolf motor function test, which is a clinically validated test for evaluating patients' performance level. And while patients performing this set of predefined movements, clinicians actually observe the quality of movements in terms of their speed, accuracy, and joint coordination, and evaluate their movement quality. In this case, we're using, clinicians are using the functional ability scale, which is a clinically validated scale for movement quality. And it ranges from 0 to 5, 5 being normal quality, 0 being inability to perform at all. And researchers in the field have been trying to understand this process of translating patients' kinematic sort of characteristics into movement quality scales. To do that, researchers have been putting multiple wearable sensors on different parts of the body. While patients actually perform these predefined set of movements, we can extract inertial data representing their movements and develop artificial intelligence and machine learning algorithms to process the information in order to estimate the movement quality scales. And through that process and looking at the important features that contributing to such a machine learning models, and we can understand what are the key kinematic features that could translate patients' movement into clinical scales. In 2010, Shamal et al. Have published the very first work in the IEEE proceedings, where they have shown that the data obtained, kinetic data obtained during the performance of 8 different motor tasks could be used to estimate patients' clinical scales. So, which showed very good agreements. And in our laboratory as well, we recently published an article to IEEE Transactional Biomedical Engineering, which actually took the idea to be able to longitudinally track changes in their movement quality over time as a consequence of rehabilitation therapy. So on the x-axis is the clinician evaluated movement quality as a consequence of rehabilitation. On the y-axis is our machine learning estimated movement quality information. Another question that now we want to answer is how can we estimate movement quality, not only from sort of this standardized and predefined motor tasks, but from non-standardized and arbitrary upper limb movements, so that we can translate what this assessment that is done in the clinical setting into patients' performance outside of the clinical setting. And our solution was motivated by a very interesting observations that we made during interactions with clinicians, that clinicians were roughly very good at making a rough estimation of patients' quality of movements or impairment level, even before they actually administer the motor assessment tools. That is, by observing some arbitrary movements that patients make. For example, they may come into the clinic and take off their jacket and hang it onto the coat hanger, or they may take out a cell phone and interact with them. Right. So by observing those arbitrary movements, patients were pretty good at estimating, making a rough estimate of patients' impairment level, quality of movements. So in fact, actually, humans do have an astounding ability to extract hidden information from the motion of others. That is, whether the motion is biological or non-biological. That is, whether the movement is robot-made or animal-made, or whether the movement is made by males versus females, or whether the movements actually contain abnormality or not. So our hypothesis was that from these, any arbitrary and non-standardized movement, there should be some kinematic features that we could extract and to relate to patients' quality of movements or impairment level. So we collaborated with a neuroscientist and looked into a motor control theories that focus on understanding how our central nervous system plans and controls voluntary movements. More specifically, we leveraged a recent theory that asserts that the central nervous system simplifies the motor control process to generate complex 3D upper limb movements by scaling and concatenating one-dimensional motor primitives. And what does that mean? And let me try to actually explain. So here I'm showing a 3D position trajectory of complex 3D movements that one of our healthy individuals actually made in the laboratory. So it's a basic arbitrary and 3D movements in the 3D space, right? When we actually look at the velocity time series of that movements in each of the anatomical body axis, that is, the x-axis represent medial lateral, y-axis represent anterior posterior, and z-axis represent vertical. And if we segment that velocity using zero crossings, and if we look at the shape, so by looking at the shape, we need to normalize the length as well as amplitude of each segment, that is normalizing temporally and spatially. In average, this segment share a very similar pattern that looks like a bell curve, which can be represented using the fourth order polynomial function. So what does that mean? Okay, so when we actually make a complex movement, that is to move our hand from point A to point B, what we do not do is we do not actually plan exact 3D sort of position trajectories in a temporal domain. That is, okay, at time zero, my hand has to be at point A, and I need to advance my hand by 10% after 0.1 second so that I can get to the destination at 2 seconds. We don't do this complicated process, right? Because it's too much of a process that our brain can handle for all the movements that actually we make in everyday life. But rather, what this theory actually asserts is that we use this one-dimensional motor primitive or template that we can stretch temporally or spatially, depending on how quickly and how large of a movement that we want to make, concatenate that over time over the 3 body axis to create this complex 3D movements. So what we hypothesized in our study was that maybe the kinematic features associated with this motor primitive, one-dimensional motor primitive, would contain information associated with any information associated with movement impairment level or quality of movements that we can extract from any arbitrary movements. So we developed a series of unsupervised and supervised machine learning algorithms to extract features from that one-dimensional motor primitives and developed an algorithm to estimate the movement quality as well as impairment level. So to validate the idea, we recruited stroke survivors with varying degrees of impairments and asked them to perform 1 to 2 minute long random that is arbitrary, but voluntary upper limb movements spanning their entire range of motion. And we evaluated our algorithms using leave one subject out cross validation in order to minimize sort of overfittings and as well as report the generalizable estimation results. So on the left side is the we found that one of the feature that is highly correlated with actual overall quality of movement that we evaluated from our subject. And also we were also able to use the features that we collected from any arbitrary movement in order to roughly estimate their impairment level. So the x-axis is a clinician evaluated impairment level, and the y-axis is the estimated impairment level. So while this very easy and convenient sort of motor assessment protocol of this random movements could really help gain fine-grained view of patients' motor trajectory over time and really support this vision of precision rehabilitation. And also this type of data could really help rehabilitation specialists to assess whether patients are really responding to their interventions and to assess if an adjustment to their intervention strategy is indeed needed. But what we are also more excited about this is that now that we can extract information about movement quality and impairment level from this arbitrary and non-standardized movements, we believe this could serve as a stepping stone towards this unobtrusive estimation of movement quality and impairment level while patients just going about their activity level. In other words, we can leverage this technology to really translate the assessments of movement quality that has been done in the clinical setting into patients' naturalistic environments to better understand their performance. So with that, I'd like to thank my close collaborators as well as my research team members, and also like to acknowledge the funding agencies who have kindly supported the work that I presented in this work. And with that, thank you very much.
Thank you very much, Professor Lee. Very, very, very interesting talk. Very clear and rich. Any questions from the audience? So I may start while the attendees maybe type some questions. I think you touch really a lot of very, very interesting and crucial aspects in the domain of the use of wearables in healthcare, actually, and rehabilitation, very interesting. And among them, I would like to focus on two crucial aspects. So the importance of monitoring the patient in the real life, which is, I think, crucial because we know that between motor capacity and motor performance, there is not always well, actually there is a correlation, but they are not the same thing. So it's very, very important to monitor the patient in his or her real life and everyday life. And this is very, very, you did really a very interesting job. And the other aspect I would like to highlight is the motivation. So you talk a lot about motivation. I work in a sports science faculty, and my colleagues, psychologists, they often say, okay, no, we all know there's no need to underline that we need to move, but the most important thing is we need to convince people to move. So we need to motivate people. And this is the same in rehabilitation. So this is another aspect. I would like just you to comment on these two, and particularly on the first aspect, so on the need to monitor the patient in the real life, which I think really it's an interesting point.
Yeah, thank you. Actually, you're on the right point about two important sort of studies that I also find about stroke motor rehabilitation. First one is, again, monitoring patient performance in their own environments. And we're also looking into a variety of sensing modalities to enable that, not only wearables, but also sort of sensors that could be embedded into patients' home settings, right? To monitor, sort of bring in more rich context of what patients are actually doing in their home setting. And furthermore, so that we can better understand what are the challenges that they actually face. So during actually, I didn't, discuss in depth about our conversation with the occupational therapists with the collected data from the wearable sensors, but although they really find that sensor data very useful, another question that they had was, so can we actually understand what, so obviously there is time that performance level degrades over, degrades, right? They really wanted to understand what patients were going through at that specific time so that they can, really, come up with this personalized intervention program so that they can help them improve the performance while going about that specific activities. And obviously that needs to be done in sort of a privacy non-intrusive manner, right? We don't want to place cameras in patients' home setting. There are a lot of contactless and wireless sort of approaches to understand that information. And that's one of the research topics that our research group is also working on, so that we can combine those ambient sensing as well as wearable sensing together to really make a rich information. And that's the second topic, motivating patients. While this type of solution would not be for everybody. There should be some people who can really benefit from this, while some people would not really be motivated further to improve their performance. But at least identifying or giving this technology to that subset of patient is important, we find. And more importantly, I think this field of study is somewhat under sort of emphasized in wearable communities. We sort of naively think that, oh, if we make the sensor and process the information using cool machine learning algorithms and to estimate something, it could naturally be translated into patients or clinical settings or to patients, but that's not really true, right? And that's why we have seen a lot of failures in wearable solutions or smart solutions. So the only way to the most effective way is this human-centered approach to really talk to them, understand them, and see what they actually need, what solutions they need, etc., so that we can really design this technology that is human-centered or patient-centered.
I fully agree. Thank you very much. I totally agree. We have a question from the audience, from Sylvia. How do you integrate data from the stroked arm and the unstroked one?
Yeah, so the way, there are a large number of metrics that can really quantify the amount of stroke affected arm versus unaffected arm. The one that we found the most relevant to the context that we are working on is the amount, or say duration, of stroke affected limb use for intensive use of stroke affected limb versus the unaffected. So it's more like a ratio between how often they engage their stroke affected limb versus unaffected limb.
Okay. Thank you very much. Another question from Randy. How does the speed of recovery for patients who undergo therapy using standardized movements compare with those who use arbitrary movements?
Oh yeah, that's a great question. That's actually to be it remains to be further investigated. We are still in a very early phase of even developing this approach to use this arbitrary movements to understand their quality. Again, even if we actually are able to accurately estimate their performed movements, right, quality of their performed movements, using that or translate it into real clinical practice to create this personalized therapy programs is an important and also a topic that reserves a long long time investigation into it. So I hope I would have an answer for that, but unfortunately I don't have it yet.
It's a very challenging, it's a very nice question and challenging. And yes. If there are no questions, I have one more curiosity. It's really a personal one, as I use also wearable sensor, not for upper arm movement monitoring, but for example, locomotion. And I was interested, do you consider estimating parameters related to the smoothness of movement, which for upper arms is very important, but also in locomotion? And if yes, which parameter do you quantify?
Yeah, that's a great question. So actually, remember that the shape of bell curve shape that I actually showed that represent the one-dimensional motor primitives. So how smooth that curve is, because our arm is bounded to our limb. So if we want to reach out, we have to accelerate and then decelerate. And that's why it's actually making this bell curve. And then when you come back, it's reversed. So that how smooth is that curve is in terms of sort of the velocity and also jerkness, right? I mean, jerkness is the conventional measure of smoothness. So those actually was playing an important role in our kinematic features as well.
Yeah, no, I totally agree. Thank you very much, Professor Lee. Other questions? Okay, if not, was really, really an interesting and very, very nice talk. Thank you very much.
Thank you very much for the invitation again.
Thank you to you. We can move to the next speaker. So good afternoon, good morning, good evening, Professor Inan. Just a second, I will present you. Perfect. Now, okay, can you see my screen? Okay. So I think we can move to the second speaker of this track, Professor Omer Inan. And okay, from the Georgia Institute of Technology, USA, who will keep some way the focus, if we can say like this, on patient-specific and personalized treatment, but actually who will deal with the use of machine learning-based methods applied to wearable vibration and acoustic sensing measurement, which is really interesting topic. So just a few words to introduce Professor Inan. Professor Inan received his master's degree and PhD in electrical engineering from Stanford. He then moved to the industry and he was the chief engineer at Countryman Associates Incorporation, a professional audio manufacturer of miniature microphones and high-end audio products from Broadway theaters, among others. So he is currently the Linda J. and Mark Smith Chair in Bioscience and Bioengineering and Associate Professor in the School of Electrical and Computer Engineering, as well as Adjunct Associate Professor in the Culture Department of Biological Engineering at Georgia University. So he has received several major awards for his research, which mainly focuses on non-invasive physiological sensing and modulation for human health and performance. Last but not least, as I work in a sports context, I would like to mention that Professor Inan, while he was in Stanford as an undergraduate, was the school record holder and the 3-time National College Athletic Association All-American in the discus throw. So congratulations, that's very interesting. So well, it's really an honor and a privilege to give the floor to Professor Inan, who will give a talk entitled Wearable Acoustic Vibration Sensing and Machine Learning for Human Health and Performance.
Thank you so much for the kind introduction, and hopefully you guys can hear me okay?
Yep.
Great. Let me just share my screen so that I can present my slides here. Great. And I'm just gonna minimize the video over here so that it doesn't take up any of the screen. Okay, well, thank you all for joining today, and I hope you enjoy my presentation. And I'm not sure, you know, for question and answer, I guess the audience is not able to just jump in and interrupt. So I guess I'll give the talk and then we'll do the question and answer at the end. But Elena, if you see a question during the talk, I don't mind at all if you jump in and interrupt me and ask the question at the time, because I always find that to be more interesting than waiting till the very end. So feel free to throw in your questions, guys, and then Elena will interrupt me and ask them. No problem at all.
Okay, of course, I will.
So I'd like to start with my disclosures. So I am actually a board member and scientific advisor and co-founder of 2 companies that spun out of my lab. One is focused on cardiovascular monitoring, one is focused on joint health monitoring, and actually we just founded the second one very recently. So I just want to put that up front. We have really 3 areas that the lab focuses on. We have many projects actually, but this is kind of the 3 maybe specializations that are core to the lab. And I'm not going to talk about the third one today. I'm going to focus mainly on our cardiovascular monitoring, and our knee health monitoring work. And these will really focus on wearable sensing of acoustic and vibration signals and machine learning associated with those signals to be able to derive information on health or performance. So I'll start first with the cardiovascular work. Of course, this is an international workshop, and so I apologize that this data here is just focused on the US, but I think that those of you abroad also will appreciate the importance of heart failure as a major, major health problem that both has correspondingly high mortality rates and is usually, either leading cause of death or one of the leading causes of death in most developed nations around the world, and also is becoming so in developing nations as well. And other than just the mortality, heart failure is one of these conditions that really has a massive impact on quality of life, and also has an impact on healthcare costs. So persons with heart failure are usually stepping in and out of the hospital, spending weeks, days and weeks in the hospital being diuresed, so to reduce the fluid volume, and then they'll go home. They'll kind of be okay for a while and then get worse, have decompensation events, and then go back to the hospital. And it's kind of it's a cycle from there that just repeats. And so, one of the areas I think that really is in sore need of new technologies for improving the care of these patients is heart failure. So we're going to get into that more in this talk. Diving into the details of how this kind of cycle progresses, patients with heart failure have fundamentally a failing heart, and so they have a insufficient amount of blood and oxygen and nutrients that's being pumped to the periphery and to the organs. And so what ends up happening is the body is starved for oxygen and nutrients in the places that need it. And then there's a cycle of compensation events that the body goes through to try to preserve the necessary oxygen and nutrients to those tissues and organs. So what starts to happen is, in a normal heart, if the body starts to collect more fluid and increase the blood volume, then the heart will be able to pump more volume out. And so the normal compensatory cycle of the body starts with starting to retain more fluid. As the body retains more fluid, there's an increase in the filling pressures to the heart. So how much the heart is being filled actually before it pumps. Unfortunately, in a patient with heart failure, the heart is already weakened. And so this increase in fluid into the heart, rather than having a positive effect on the output of blood from the heart, has a detrimental effect. And so you actually have a adaptation and all these attempts by the body to try to increase output, but unfortunately all these just lead to more and more retention of fluid, ultimately weight gain, swelling in the ankles, fluid in the lungs, and what's called congestion that leads to decompensation and ultimately hospitalization. So we're going to kind of come back to this spectrum of events as we go through these slides, but you can imagine that at some point in this process, it would be really advantageous if you could detect that this is going on, and if you could intervene by changing the person's status through medication accordingly. So there are many technologies that are being investigated as possible methodologies for doing exactly that. People have looked at weighing scales for a long time in the context of heart failure management, because of the fact that if you start retaining a bunch of fluid, the presumption is that your weight will start going up. And in some cases it does, in some cases it doesn't. The problem is that weight gain is not specific. The person could be also gaining body fat. A person could actually be gaining weight but losing fat or losing skeletal bone density and have conflicting things that cause the weight to change, stay the same. So the other problem is, if you look back at the spectrum, the time window for prediction from weight gain to decompensation is very short. And so it's not really it's not a specific marker, and it's not a really good leading indicator. People have also looked at other sorts of technologies for trying to detect fluid volume in the chest through intrathoracic impedance, and this very expensive technology called REDS, which costs about $43,000. All of those are kind of late indicators and have some issues with specificity. There is one device that has actually shown good effectiveness in being able to predict these hospitalization events and reduce them, and that's this implantable device that goes into the pulmonary artery that's called CardioMEMS. And this sensor is actually a pressure sensor that's implanted in the body, in the pulmonary artery, and estimates filling pressure. With that, you get an early indicator, a leading indicator of what's going on. The problem is, of course, it's implantable, it's very expensive. You know, not all heart failure patients have access to this. In fact, many don't, most don't. And so there's limitations to that technology. So our objective in this cardiovascular monitoring space has been for some time to have an affordable wearable sensing system with associated machine learning to be able to detect as early as possible hemodynamic congestion and allow the titration of care for patients with heart failure. So this is kind of the concept, you know, as a block diagram. Effectively, you have somebody, let's say, wearing a wearable sensor. That wearable sensor has some signals that are measured on it that are presumably relevant and related to hemodynamic monitoring in patients with heart failure. And then some signal processing machine learning algorithms derive some information from those sensors that are pertinent to being able to detect hemodynamic congestion and ultimately predict decompensation. And then with that, a clinician or caregiver can look at some dashboard of information, and from that determine when the patient needs to maybe increase their diuretic dosage to reduce fluid volume, maybe increase their vasodilator dosage, or decrease, or whatever changes they may have to make. The hope is that this closed loop ecosystem could then lead to a reduction in hospitalizations and improved outcomes for patients with heart failure. So we've worked on a lot of different technologies in this area. The ones that I'm going to focus on here that have seemingly had the most benefits so far and have the most promise, we think, going forward, are going to be related to the measurement of the vibrations of the chest wall in response to the heartbeat. So every time your heart pumps, there's forces that the heart is imparting on blood. The blood then has to move through the arterial system, and so there's forces that are imparted by the blood on the vessels. Those forces actually translate to small vibrations of the chest wall that can be detected locally with accelerometers. So these types of signals were measured first in the 1960s and 70s by actually Russians and Americans as well, with the goal of being able to monitor astronauts during spaceflight. And probably they were accidental findings at first that then led to a couple folks named Salerno and Zanetti in the 1990s who further investigated these signals and tried to relate them back to underlying cardiovascular events. There's been a lot of work since then, actually very good work from Italy, from Marco Di Rienzo in his lab, who had some of the first wearable seismocardiogram measurements demonstrated, as well as, of course, many others that we've teamed up with before to write position papers in the area. But it's really a very interesting field. And our group was excited about taking these signals and trying to use these measurements in patients with heart failure to see if we could predict elevation in filling pressures and changes in physiology associated with compensation status in these patients. So that's what I'm going to talk about today. A couple of our devices, these are kind of older versions of the devices that have now since then improved. They're smaller now, they last longer, and they have a little bit better signal quality as well. But these are a couple of versions of our devices that we highlighted in this review paper in Journal of Applied Physiology. One is a chest-worn patch that uses adhesive to stick the electronics and sensor onto the chest and measure these chest wall vibrations, which are, you know, milli-G level vibrations. And on the right, you see a watch that the person actually actively presses against the chest to be able to measure these SCG signals. This is the newest version of our patch that's come a long way since the previous version, but similar operation where there's a couple of commercially available ECG electrodes that are snapped into this adhesive patch. Those electrodes then act as the adhesive to be able to hold this patch against the chest and measure the seismocardiogram signals from the chest. In addition to the SCG, of course, we then measure the electrocardiogram or ECG with those two electrodes. And we also measure several different channels of photoplethysmogram signals, which are these optical measurements of blood volume pulse with reflectance PPG architecture. And from those, actually, this recent paper that we wrote that was just accepted a couple days ago to biosensors details the ability to estimate SpO2 accurately as well from this patch from healthy persons who are doing breath hold exercises. The SeismWatch hardware has also improved since our last instantiation that was in that review paper. This is kind of the latest version of the hardware that includes ECG electrodes as well that the person can contact with their hand to be able to provide a timing index for the seismocardiogram signals. And we did quite a bit of work that started out of a center grant that was led by Professor Rama Mukamala from Michigan State University, where we also collaborated very closely with Professor Jino Han from University of Maryland. And we did a lot of work demonstrating that pulse transit time, first of all, could be derived from a combination of these cardiogenic vibrations, in this case, seismocardiogram signals, together with peripherally measured PPG signals, and that pulse transit time measurement could also then be used to estimate accurately blood pressure without the need for a cuff. So we did a lot of work where we compared these measurements to the phenometer, which is this finger-based arterial blood pressure measurement system. And we also, in this case, in this paper that's being cited here, compared it against a home blood pressure cuff with serial measurements from persons taking this device home to demonstrate that at-home measurements could be possible with the SeismWatch hardware. But getting back to heart failure, we did this study at the University of California, San Francisco with Professor Liviu Klein, who's the head of advanced heart failure treatment there, and also a cardiologist working with patients with heart failure, the head of mechanical support as well, mechanical circulatory support for patients with heart failure. And we performed a very simple study that was leveraging a typical clinical protocol that's followed very often for patients with heart failure in the clinic or hospital, which is that someone with heart failure will walk for a total of 6 minutes. It's called the 6-minute walk test, not really too creative of a name, but they'll walk for about 6 minutes and they will record how far the person walked, so a 6-minute walk test distance. And that's sort of this, somewhat crude, but actually pretty good way of determining how their heart is doing, because you kind of see if they're doing an exercise task, how well was the heart able to compensate for now an increased need for blood flow and oxygen delivery to the muscles as well. And you see basically how they were able to sustain that. So what our hypothesis was in this case was that if we measured seismocardiogram signals from these patients and they performed the 6-minute walk test, we thought that the structure of seismocardiogram signals before and after the 6-minute walk test would be substantially different for patients who were compensated heart failure versus decompensated heart failure. And this was the first time this sort of analysis was done with SCG signals. And it was also the first time that in patients with heart failure, there was a demonstrated difference based on clinical status in SCG signal characteristics. And I think one of the most important reasons for that was the fact that we coupled SCG signal measurement to this exercise stressor task. What was more important and exciting from this data was that for several of the subjects that had serial measurements, so from when they were first hospitalized, first admitted to the hospital in a decompensated state, to when they were discharged after, let's say, several days or weeks of diuretics and fluid volume being treated, there was a difference in the similarity score. Basically, the seismocardiogram changes with respect to exercise improved in all of these patients. And for one of these patients who then was readmitted several weeks later with volume overload, we saw then that the graph similarity score reverted back to the decompensated value as we might expect. And for another patient with a heart transplant, it actually decreased substantially. So this increase in GSS, what we'd wonder is if we could measure this at home, would there be actually an ability to predict this with enough of a time window where one could intervene? So that's kind of where we were at. At the same time, we wanted to better understand in a fundamental way with some clean experiments how the SCG signal changes during exercise and how those changes compare to gold standard measurements. So we performed a study in a total of about 75 patients with heart failure where they wore the wearable patch and they had this breathing apparatus for cardiopulmonary stress testing at the same time. And they performed this stressful cardiopulmonary stress testing exercise. And as they did so, we tried to compare the SCG signals measured with our device to the oxygen uptake as measured through the face mask. So we had time series data from the electrocardiogram, from the seismocardiogram, and also VO2 measurements from this CPET hardware. And for each of these moments in time where a VO2 measurement was available, we would take a surrounding window of ECG and SCG signals from which we would try to extract features. With those features, then we trained a random forest regression algorithm to be able to estimate VO2 as compared to the actual VO2 measured from the breathing apparatus. And there was a lot of work here that went into how to deal with motion artifacts, how to properly extract these features in a robust sort of way, which features end up giving the most information. So there's a lot of stuff that's kind of detailed in this paper, but not going into in this talk that much. The last step was then, other than just determining oxygen uptake, could we classify the clinical status of these patients as stage C or stage D, which is the important classification clinically that they make with this test. And so we had the data set separated into two groups. One was the training and validation group, where we did cross-validation within that subset. And with that cross-validation, we optimized hyperparameters. We also trained the model, obviously, and then from that model that was trained in that subset, we then went to a held out test set where we determined the ultimate results. That's what's shown here. So the correlation analysis shows the VO2 estimate compared to actual, which had a pretty good RMSE. If you think about, the range was from about 2 or 3 milliliters per kilogram per minute all the way up to 26, and the RMSE was about 2.2, so representing about 1/10 or 1/15 of that range. The ROC curve also had a good area under the curve for the clinical classification that we wanted to make with this data. So this was kind of a nice result for us, showing that there's some information in this SCG signal that really might provide value clinically. But ultimately, what we were very interested in is the ability to accurately determine filling pressures, and specifically determine congestion status based on filling pressures as compared to the ultimate gold standard, which is right heart catheterization. So we performed a study with 50 subjects where we did baseline pulmonary pressure measurements, and 20 subjects where we measured acute changes based on a vasodilator challenge. And this work is still under review, but I just want to give you sort of the overview of what we did and what we found. So of course, again, we have time series measurements of ECG and SCG signals. In this case, the gold standard is the right heart cath data. And again, we performed some outlier removal, noise reduction. A lot of this pipeline of SCG analysis we've at this point solidified, and we do some feature extraction for regression against the right heart cath values. And so again, we had a held out test set for which we estimated both changes in pulmonary artery mean pressure and also pulmonary capillary wedge pressure. And in both cases, we had pretty good agreement, pretty low error, and a significant correlation between our estimate and the value that the right heart cath produced. So this data for us is really exciting and indicates that we may have some success in the at-home study that we're going to try to do over the next few years to be able to actually predict and prevent decompensation events. Lastly, I want to say a couple words about work that we've done in blood pressure estimation. I kind of touched on it earlier when I talked about SeismoWatch, but we do have some work. This is in this case subjects at home, as I mentioned, where they took the watch home. They also took the cuff home, and sort of performed this measurement session every hour or 2 hours or so, except while they were sleeping. And we tried to assess the agreement between our estimated values of blood pressure with pulse transit time and the actual values of blood pressure as measured through this Omron cuff. So I'm going to move on now, as I think we have not too much time remaining, I guess. So I want to make sure that we get into the knee health monitoring work that we've done as well. And I'm going to kind of breeze through some of this so that, so that we can make sure that we get into all of it and have time remaining at the end for questions. So trust me, I guess, in saying that the knee is an important joint to monitor. There are many patient visits annually in the US, and of course, this is very common to have knee injuries or arthritis worldwide as well. And so it's a very commonly injured body part that leads to, of course, very severe injuries as well. If you have an anterior cruciate ligament or ACL tear, you might be out of athletics for 9 months, 12 months, it could be a long time before you're really ready to get back to one of these very challenging and high performance activities. So our lab has been very interested in the sounds emitted by the knee joint during movement, and the possibility that we could have wearable measurements of these sounds act as a longitudinal marker of knee health and biomechanics. And so we've been building these sorts of braces and sleeves, lots of different types of hardware to be able to measure these sounds from the joint, with sort of embedded systems to be able to capture all the data, and importantly with context. So we have these miniature accelerometers that go around the knee joint that allow for the measurement of joint acoustic emissions during movement. But at the same time, we have inertial measurement units to measure joint angle as well as bioimpedance to give us some information about tissue health and edema within the joint. So we've done quite a bit of work in these sorts of areas. I'm going to skip through the details of the hardware for a second and talk about some of the results we've obtained that are kind of the most exciting so far. So we performed a study in collaboration with Hubert Lim and Dr. Eric Peterson. I guess Dr. Hubert Lim and Dr. Eric Peterson. I don't want to leave out Hubert's professional title there. Sorry, Hubert. So we actually took these braces to Minnesota and measured wearable, with the braces, wearable measures of joint acoustic emissions, bioimpedance, and kinematics in patients with rheumatoid arthritis serially while they were undergoing a different clinical trial there at the University of Minnesota clinics. And what we found was that actually through this very interesting, again, under review, but pretty far along work here, this very interesting approach where we tried to do kind of a two-step process of first extracting ESR from the joint sound signals, and then second, using that together with kinematics and bioimpedance to estimate this clinical gold standard score of disease activity, which is DAS28 ESR. And what we found was actually we were able to accurately classify disease activity in these patients. And this is a total of 10 subjects with 5 visits per subject. And so a total of 50 data points where we were able to get an AUC of about 0.81 or 0.82 for the overall data set. And so what's interesting here is, so you have this wearable sensor data from the knee that's able to capture a more systemic level of inflammation for patients with rheumatoid arthritis. And so it could be that if somebody goes home, let's say with RA, and they're on a new therapy, and you want to know as soon as possible if that's working or not, serial measurements of this DAS28 ESR estimate from our system may allow those medications to be titrated. It may allow for early determination of whether something is working or not for that patient. In addition to rheumatoid arthritis, we've actually done a lot of work in juvenile arthritis, so juvenile idiopathic arthritis, or JIA, where we teamed up with Dr. Sampath Prahalad of Emory and Children's Healthcare of Atlanta. And this is some data where we investigated how joint acoustic emissions were different for persons with GIA versus healthy controls. So kids with arthritis versus kids who don't have arthritis. And also for the same kids with arthritis, but after treatment. And these treatments are sometimes biologics or injections, various different things that they're trying. One of the hardest things in GIA is to determine if a treatment is working or not for a patient. And so the ability to, again, as early as possible, determine if something is working. To determine if you're moving basically from this cluster down to this cluster would be very beneficial clinically. And so we're excited about this as a possible tool for helping to manage GIA. Lastly, I want to talk a little bit about a non-health related application, or not necessarily health, but something that's maybe more interesting from a performance standpoint. So when you're performing various sports exercises or activities, let's say squats, medicine ball throw, different sorts of things that you do in athletics, you're always putting some loading on the joints. And when we talk about loading, you can think about the external load applied, but what's maybe most interesting is actually the joint contact force, or the forces internal to the joint that are contacting from area to area. And if you think about these joint sounds as maybe tribologically generated or generated due to the friction of things rubbing within the joint, then it kind of makes sense from a theoretical standpoint that as you change the loading properties of the joint, you may change the characteristics of the sounds that you measure. So we did some early studies in persons performing vertical leg press, where we determined that indeed with vertical leg press, as you increase the weight that the person is pushing, you do see changes in these sounds that are reproducible and quantifiable across subjects. But we wanted to go beyond that, and this is where kind of the combination of the wearable sensing and machine learning comes in again, where we had people wear these sensors while at the same time where EMG measurements, electrodes for EMG measurements from 7 different sites, as well as several markers on the body to be able to determine kinematics. And they would walk on instrumented treadmills and other sorts of terrains where there were force plates, so we could measure ground reaction forces. All this was done while they were performing different activities, so level ground walking, incline walking, decline walking, and at different speeds, and also while wearing harnesses or weighted vests to change the loading properties of the body during these activities. And while doing this, we set up a machine learning architecture where we had a hybrid EMG informed neuromuscular model based on OpenSim to be able to estimate the gold standard joint contact forces while the person was performing all these activities. But at the same time, we took the joint sounds measured with our contact accelerometer on the knee from 4 different sites to form a feature matrix, and then to train 2 different models, one with a leave one condition out training and one with a half and half, 1 minute testing, 1 minute training. Both are subject specific models, which we think would be necessary in this case. And we used extreme gradient boosting for the regression approach. So what we found was, compared to the baseline subject average approach that someone would use if they didn't have any of this sort of measurement, we were better. We were able to improve on that with leave one condition out and with the half and half approach. And of course, the half and half approach possibly may overfit. And so it has actually a very low mean average error for the joint contact force measured. But the cool thing was this was for a wide variety of activities and conditions where it's not just vertical leg press, it's kind of something that's maybe building more towards a interesting model for athletics and possibly also for interfacing to exoskeletons and some of this other work that's out there. So great. So with that, I want to definitely thank the amazing students and postdocs that I'm working with, and of course the collaborators as well, and the sponsors for everything we've done. We need to update this picture. It's a couple years old now, but the group is really doing fantastic stuff, and I'm happy about everything that they've done. Cool.
Thank you very much, Professor Inan. Wonderful, really, really amazing, amazing stuff. Are there any questions from the audience, in the chat or in the Q&A Don't be shy. Okay, I can start if I can. Really, really interesting. And I was particularly intrigued by the last part of your presentation. As a biomechanist and a motion analyst, it's really amazing the fact that you can, let's say, predict or get information about the dynamics or the kinetics of the joint by joint acoustic emission, by analyzing the acoustic emission. That's really, and I have a question about the, let's say, the influence. How important is the sound in the environment? So the fact that the environment is silent enough, or is it important or not?
That's a great question. It depends on the sensor that you use. So one of the reasons why we use these contact approaches. So if you had just a microphone, like the one that you might measure someone's voice with, sitting on the knee, then you'd be very susceptible to background noise. And also would not be a very good way to pick up sounds from the joint, because you have the fluid-filled knee and body going to the air-filled space outside. And so there's a major impedance mismatch there that would reduce the signal integrity. So with the contact measurement, you essentially use the skin as a membrane.
Okay.
It's like a stethoscope. And you put the accelerometer in contact with the skin. And so you measure the vibrations of the skin in response to the acoustic emissions internally. And so with that approach, you're actually very immune to background noise, because of the fact that even if something is very loud, the ability to couple into that small area of skin for, let's say, a spherical wave that's emanating from some sound source, like someone's voice or some other equipment or machinery, that spherical wave has a large surface area associated with it, and you're just capturing some small segment of that along that tiny membrane at the knee. So you're in very close proximity to the sound you're trying to measure, and you're very far away and not picking up very well the ambient noise. So it's pretty immune to that. And in fact, it's an approach that's used for speech detection in loud environments. They'll put a microphone in this manner on the throat, right, to pick up throat vibrations, and it does very well.
Yeah.
So fortunately, that's not one of the biggest issues.
Okay, thanks.
Rubbing noise is very challenging. So we've had to do a lot with the packaging and adhesives to be able to deal with the the movement of the stencil actually on top of the joint, which can be a problem.
That's okay. That's really amazing. We have a couple of questions also from Chiara. Thank you for the presentation. In your opinion, what is the potential of inertial sensor technology for continuous use in daily life?
Well, I mean, I think that inertial sensors are used a lot, right? So any of the fitness tracking equipment currently uses inertial sensors to do that. And I think that phones also are using inertial sensors. So you may not know this, but inertial sensors are everywhere already, right? They're already being used continuously in daily life. I think that there's a great potential for that. And I think there's some possibility to complement those with other sensing modalities to maybe get more in-depth information about specifics, like maybe joint health, that kind of thing. But really, technically, all of what I showed in this presentation is very highly focused on inertial sensors. So accelerometers for picking up chest wall vibrations, those are inertial sensors. It's just that they must be much lower noise than the ones used for fitness tracking, right? And same with the sensors used for joint acoustic emissions. Those are also inertial sensors. They're accelerometers with very wide bandwidth. So, they go out to about 20 kilohertz or so, and again, have very low noise. So that's why we're able to pick up such small signals with them. But yeah, I think there's a great potential for inertial sensors for sure.
No, definitely. And a couple of questions from Ramsey. Is there an open source database of joint acoustic signals, me specifically, that you recommend? And also, have you implemented deep learning on knee acoustic signals?
We have. We had a recent paper in TBME, IEEE TBME, that talked about using deep learning to be able to determine asymmetry in a squat task from these signals. I'm not sure if there's an open data set actually for joint acoustic emissions, but if you want to contact us and ask for any of our data, let me know, and we could probably share it. But I'm not sure if anything is openly available now. It should be, actually. It should be.
Yep, that's really interesting, really.
Yeah.
So another question from Ziad. Which better for HF prediction, AI or ML? So into artificial intelligence or machine learning, which library?
I mean, so I'm not sure exactly what in this context, what would differentiate. So by AI or ML, you know, I mean, I guess in this case, AI might be also taking into account some of the decisions that are made based on the information, like, you know, medication dosages and that kind of thing. I think physician in the loop AI in this case makes more sense because you want to make sure that you're using this as kind of a decision aid that helps to ultimately go together with all the other information that the physician knows. Maybe one day that's not the case, but I think that's far away, honestly. I think that physician in the loop AI makes a lot of sense. Which library? I mean, whatever you want to use. A lot of times we use Python for this stuff, you know, we use scikit-learn for a lot of stuff. I don't know. I mean, it depends what you're using, I guess. That's what you're trying to do.
Yeah. Thank you very much. Any other questions? Okay. So thank you very much, Professor Inan.
Great. Thank you.
A very nice, interesting talk. Thanks a lot.
Thanks so much.
Thank you to you, really. And I think we can move to the next speaker, and we'll leave the floor to the next chair of this session. It is Professor Silvatti. So here we are. Goodbye to everybody.
Hi, everyone. Are you listening me?
Yep. Yeah. Everything okay.
And are you seeing me?
Yes. Everything's perfect.
Okay. I'm not sure. It's okay, but I hope so. Let me see. Oh, okay. Here. Okay. So I'm going to introduce Simona Carini. That is a research assistant in Dr. Ida Sims Research Lab at the University of California, San Francisco, where she has been a principal contributor to several projects on clinical trial annotation and visualization, and to the Human Studies Database, and the Data Federation Project for the Clinical and Translational Science Awards. Since 2013, she has been involved in the definition of data schemas for semantic interoperability of mobile health solutions for Open mHealth, and then for the IEEE P1752 Open Mobile Health Working Group. Simona talk will provide an overview of Open mHealth and IEEE P1752's past and ongoing work. So thank you so much, Simona Carini, for your time, and the floor is yours.
Grazie, Amanda, for the introduction. And now there's the always the moment of will this all work? Sharing my screen.
Okay.
Okay, seems like it's happening, right?
Yep.
Okay.
Yes.
Good. There's always that moment in which you don't know if everything is going to crash or everything is going to work. Thank you. thank you for inviting me. I'm going to start my presentation, and I know we have Q&A at the end, so hopefully we'll have enough time for those. So thanks again for the introduction. My focus is going to be on the work that I've done within OpenM Health, and more recently, the IEEE P1752 working group. So the focus of our work is wearable data, and kind of we've heard this, from also the previous presentation. This is important data that could help people and their healthcare providers across the board to understand health and health states, and then inform actions, and with the goal of improving health and in some cases change health behavior. So there is gathering data, and also in some case providing data, delivering data using mobile technologies to achieve behavior change. For example, in physical activity of medication adherence or clinical treatments. And so the focus has been on digital biomarkers, which I'll go through in the next slide. And also, using this wealth of data, as we heard, for, providing analysis of, doing analysis of health state, and then providing decision support. So just quickly, a digital biomarker is physiological and behavioral measures that are collected by means of digital devices that can be on the body, inside the body, and then the idea that they characterize, influence, or predict health-related outcomes. And the focus has been on a number of digital biomarkers, and the examples is number of steps, total sleep time, heart rate variability. So the assumptions is that many, we have already many, but many new will be defined, and there will be new sensors, new person-reported outcomes. This is when the person reports on their health state. And then hardware and software are continually changing, and then digital biomarkers increasingly combine output from multiple sensors and sources. And the data will flow far and wide. We just heard talking about open source data sets. And then, so they will go to multiple actors that will be used for multiple purposes. So standards are needed to allow interoperability, to make this all work, data from different sources for different uses. So the challenges are, there are a large amount of data that are gathered from sensors and apps, and they need to be, for various purposes, they need to be aligned, harmonized, and combined, but still maintain the original meaning. And as an example, this acronym BYOD is very used in clinical research, for example, or where it means the person brings their own device instead of being provided a device. And then moving forward, with this data, at some point, there is this integration with the workflow in the clinical setting, which is based on electronic medical records. At least my knowledge is for the United States. And so the standardization helps to make sure that there's a clear syntax, semantic, and the relevant context for the measure is also provided. And then, of course, beyond that, there's all the concerns about privacy, security, and ethical concerns, and patient burden. There are, and we've heard about this, and so there are a number of concerns. So interoperability is like a big concept, and the focus here is on structure and semantic interoperabilities. The idea is that the data has a known and defined structure, and then the meaning of the data is mutually understood by all the parties, and not just the data for the metadata. And I like also to talk about person-centric interoperability, the idea, because we have more and more of this different sensors and apps to rely on the person. So also make it interoperable for the person that interacts with all these different data generators. So standardizing mobile health data and the metadata makes the data exchange, the reuse, predictable and consistent, and then allows data aggregation, data analysis, visualizations, and of data that comes from multiple sources. And then it allows this to be easier and more accurate, and facilitates the development and validation of digital biomarkers. It also reduces the cost of using this data. And the idea is that researchers across the spectrum spend time on analyzing the data and getting insights from the data rather than aligning the data, trying to create a consistent data set if the data all adhere to the same standards. So my manager, Dr. Ida Sim, in 2011, co-founded with Dr. Deborah Estrin, a researcher at the time at UCLA, started OpenM Health as a nonprofit focused on standardized data representation of measures for self and clinical care. This is 10 years ago, when mobile health was very early, but it was clear that the need was there for agreeing on a standard representation for these data that was started to be looked at and used beyond just self-care. And our work is being funded by a federal grant, just ended this year. And again, our focus was standardizing data and metadata representation using schemas, and I'll provide more details, and provide tools to use these data. So as part of our process, we submitted a proposal to IEEE to bring this standardization work within the IEEE forum. And so the working group P1752 was born. Before I go more into the details, just a couple of examples of the need for that. So this is without going too much into details. So, but in the slide you see blood glucose value is 128. We don't know the units of measure. When was this? What's the time stamp here? And importantly, for a use of this specific data point is when this was measured, what was the temporal relationship to a meal. This is blood glucose is influenced by meals. So the instance on the top is not very useful. So the other instance has got all the information that is needed to make sense of the value of the blood glucose. Value is the same, but we need all this other information. So this is another example that very often, and for many measures, depending on the use, you don't want to have the individual, more than the individual value. There's this idea of looking at summary values. For example, in this case, you want to have to be able to represent average fasting glucose over a 3-month period. So the value again is the same, but instead of being associated with a timestamp, so being an individual, is associated to a time interval, and it represents an average of however many values were recorded during that time. So this again shows the complexity of the data that goes beyond just a number. And this is another example for blood pressure. Again, I'm taking a couple of examples of data how it could be out there. Very hard to not clear very much that HP is actually the high number and LP is the low number of the blood pressure. And again, you can see on the right side, hand side, a proposal for something that is very clear. It has each value as its own unit of measure. And again, it contains other contextual information, which is important for processing properly the number. In this case, because it's blood pressure, it's the body position and where it was actually, where in this case, the cuff was placed for the measure. So this is sort of showing a little bit the need for the need for the standardization work that we started. And then besides data, there's also metadata, and the metadata can be a lot, many things. So for example, is the data point, what is the source? How was it measured? What is the sensors? The name of the sensor, the version of the sensor, how it was acquired, what is the privacy level? Is this a value that can be used by anybody, or there is some restriction placed on that? And this can go on. So metadata can actually be fairly complex, but it's very important, particularly as, again, I'm referring to something that people mentioned, is that when there is a creation of a data set, so there is the data itself with all the information that is relevant for the data, but then there's also this other information that defines the data set and each instance in the data set that allows whoever uses to make sure that they know, where the data comes from, how it was acquired, whether it was processed, and if so, how, what kind of algorithm was applied to the data, and so on. So this is all information that is important for, again, using the data for whatever use across the board. So this is all sort of like the justification, if you will, for the work that we started. And so picking up again from the story from Open Health to IEEE 1752, that's a working group, and we started working in early 2018. And the purpose, as explained here, was to provide standard semantics in the form of common data and metadata schemas to enable the meaningful description, exchange, sharing, and use of mobile health data across a wide spectrum of use cases. And if you're interested, of course, this is the website. We have a public-facing website with instructions on how to join our mailing list, which includes over 230 people at this point. Participation is completely open. Our work is sponsored by the IEEE Society for Engineering in Medicine and Biology. And as you can see here in the purpose, we've focused very much on, again, on data representation. So a lot of topics that are incredibly important, but they're out of scope for our working group. For example, security, communication protocols. There are other groups within IEEE that are tackling some of these. And so in collaboration with them, we provide support, recognizing that, everything, all these aspects are important. And so this is our specific focus. So at the beginning, we defined the priority areas. We also, saw what was the expertise that was available, and so we focused, because you can't do everything. So we focused on three aspects: sleep measures, physical activity, and then a minimum metadata set. And then, as we started, IEEE was also piloting an open source. And so we were part of the pilot. And so all our work, as I will also show later, is available on a website, on a repository that is managed by the IEEE open source project. So after 3 years, our the standards that I just listed, they were actually approved and published in late summer of this year. So there is a document, and then the bulk of the standard is actually the schemas. And as I just said, they are open source. This is the repository. So anybody can go there and take a look and provide feedback, ask questions for the repository, everything that people do with schemas. And in the repository, we included also a lot of sample data as documentation. So again, we chose a JSON schema for as language for describing our schema, our data standard. And the unit for instances of data is a data point, which is a single, it's a single instance or a series of data points that all share the same metadata. And the structure is that every data point or data series has a header. That's where the metadata is stored. And then a body, which is where the actual measure is stored. And I'll show examples. So a quick tour of our repository, and the schemas there are a lot of them, and they are organized in folders. That's just for readability. Then the schemas are assumed to be all living in the same folder for validation of data. So a schema is a template, and again I'm going to show shortly. So again, this is just shows that each folder has a set of schemas, and this is just as an example the metadata folder. And this is an example of the sample data. So the sample data structure repository section of the repository mirrors the schemas section. And so there are folders, and in each folder there is a set of sample data for the relevant schemas, with some a bit differences. For example, physical activity is a single schema, which is fairly complex. So we provided sample data that describes the various different that provides an example of different activities, which are not just sport. We also looked at other types of physical activity that includes people with special needs, like wheelchair users. So a schema is a template for instance data. So usually I try to choose a simple schema, mostly for space. So this is a schema that describes a measure for ambient temperature, which is it's actually an environmental variable, which is important for some measures. And so the schema basically lists what are the data elements that are considered important to describe an instance of ambient temperature, and it lists which ones of these properties are required, and the others are assumed to be optional, but and either recommended or used only in specific cases. Like in this case, is a descriptive statistic only applies when the instance is actually a summary measure. And in this example, the temperature unit value actually references another schema, which defines what are the allowable units for a value that represents a temperature. So this shows an example of a full instance of ambient temperature. So as I mentioned before, so this is a data point, and as I mentioned before, there is a header part and a body part, and the header is where the metadata is stored. So very quickly, the unique identifier, a reference to the schema, which models the elements that are listed in the body. And then in this case, the header points to the fact that this value was sensed versus self-reported, the acquisition rate of the sensor. And as I mentioned before, metadata can go on for a long time, but we made a choice within our IEEE work to have a list, actually an array of references to external data sheets where some of the information is stored, particularly information that tends to be static. For example, the study protocol, if this value was collected within the context of a study protocol, or in this case, the ambient thermometers, characteristics for the thermometer that was used to measure the temperature. And again, in the body, you see the two required data elements. This is a value in degrees Celsius and the timestamp. And I provided an example also of something fairly more complicated. This is an example of an instance of physical activity, just the body, just again for space. So you imagine that there is the header. But the idea is, again, I wanted to show you something more complex. The physical activity, this is an instance that describes an episode of running. So it's associated with a time period. You usually run for a certain period of time. And then all the information that can be measured about an episode of running. And because it's running, so it makes sense that there is, for example, cadence, speed, and then elevation gain, and then two elements that are considered important for the evaluation of physical activity within a context of more like self-care and prevention is the amount of moderate activity and of vigorous activity. The idea being that there's a recommendation of having a physical activity of at least moderate physical activity at least of 150 minutes per week. So as we completed the work before, again, focused on sleep measures, physical activity, and metadata, we also made plans to expand the work. And so P1752 became a family of standards. So the work done has a .1. And then we started work on the next set of measures that focused on cardiovascular, respiratory, and metabolic measures. And we started a few months ago on these measures that are also very important for, again, self-care and clinical care. So this is sort of like an overview of things that are done. We also modeled generic surveys for patient-reported outcomes, and these are part of the because they're particularly used in sleep research. And so these are part of the standard that's been approved. These are some of the measures that are in the work on the right for the current work of P1752.2. And then OpenM Health also, OpenM Health started developing a lot of these, and there is still some work that we did that it's currently not part of IEEE. It has to do with medication prescription and medication adherence. And also we besides the cardiovascular and respiratory measures, we also will probably add more details to the metadata schema. Again, recognizing that the work that we did was what we called a minimum metadata set, as needs arise for tracking more detailed information of data that is collected. Okay, so in summary, what I presented is our multi-year work on standardizing data and metadata from wearables with the goal of promoting data aggregation, analysis, visualization, any use of data that is based on the idea that data comes from different devices at a different time and measures the same signal or digital biomarker. So one thing that I should clarify here is that, as you've seen on the slides, you've seen, heart rate, ambient temperature, blood pressure. So our focus so far has been on calculated measures and not what it's called, base data or raw data. So accelerometry and gyroscope for, this is our focus has been more so on data that is calculated using, so-called raw or data like PPG signals and things like that. So our goal was to provide a clean syntax and clear semantics for mobile health use cases. The idea again is to provide templates for these measures, and each template includes a list of the data elements that are important with clear naming, references to accepted and standardized units of measures, and a definition that again provides a clear semantics for any use case. And our IEEE, first part of the IEEE work, 1752.1, was published this year, and it's composed of a document that, but the document references, the bulk of the standard is actually the schemas, which are stored in an open source repository managed by IEEE. So the schemas are basically the standards, the way I say it. And we're continuing our work to cover additional clinical domains. The current work is under the project called 1752.2. And as I showed, we're focusing on cardiorespiratory measures and metabolic measures. And then we plan to also further develop the common metadata approach. And we're also promoting adoption, in several ways. One project that is, again, part of IEEE that we're going to start shortly. It's called the Industry Rapid Activator Program. And the idea is to partner with some industries, some people from industry to showcase the use of the standard. So that for us is coming up in the new year. And then I didn't touch about this very much, but the idea, and I'll do it here. So one of the uses, of course, of these data is to provide insights to physicians. And right now, at least in the United States, the emerging standard for electronic medical records data is it's an HL7 standard called FHIR. And as our work within OpenM Health, we were actually provided an implementation guide that supports basically the transformation of standardized mobile, wearables data into FHIR's observations for use within the electronic medical records. And by use, I wanna clarify is that I don't mean necessarily that data from wearables needs to somehow become part of the electronic medical records, but it needs to be made available. And we've heard this, earlier also mentioned, as this data gets collected in the daily life of people, their healthcare providers could use, some visualization, some insights on what happens when the person is in their environment. And so that's sort of what we call clinical integration on the each EHR-based clinical care, again, at least in the United States. And with that, I conclude my presentation. I thank you again, the organizers for inviting me. I thank you all for listening to me, and I'm open to questions.
Thank you, Simona, for your nice presentation. So we are open for the questions.
Yeah, if I can, I have a question. Hi, Simona.
Hello.
Very interesting presentation, and a little bit different from what we have already seen in terms of research. You have explored a different aspect of the wearable in general and in general of the data. Yeah, I'm curious about companies, and in particular, if you get some information about how receptive and interested are big companies like, I don't know, without any kind of name, but on, just to say something in using the proposed standard, if there are any kind of benefits for big companies.
Good question. Grazie, Carlo. So yeah, without naming, but so this is the big complicated story of standards, right? So it's like, and I come from a situation, I come from research, pharmaceutical research and development, where I understood very early the benefit of standards. So some companies are receptive. Let's put it that way. Some companies are receptive. There is, I think, what's going to happen. I mean, of course, you know, our standard now is being published, and it, as part of our working group, we actually had some industries, some people from the industry. We have this huge mailing list that includes both, you know, people from academia, people from industry, from different parts of the industry, because it's not just the device developers. There's also, you know, the people who are trying to, you know, create this connection between wearables and clinical care, for example, a lot of them. And there is, everybody feels the need for standards, because the moment you're trying to do this, they're putting together data from different devices and trying, you know, you understand how important it is. The person that feels less the need is, you know, the individual user. I mean, because as a user, you only have one device, and, you know, interoperability doesn't sound, you know, very important. But, you know, if you start having more than one device, and again, if your physician has, you know, people with different devices, then standards become important. So we're working there, and the way I see it is that it's going to be a slow process, because, you know, everybody has to change a little bit in order for us to meet, but the need is there. If you, I mean, I presented at a panel last week, and they asked people, you know, what is the biggest you know, obstacle to, you know, expanding the use of wearable in clinical care, and top one was, you know, lack of data standard, or, you know, difficulty with data standards. So we feel it, as I said, that for us, it's like to promote the use of standard. And the idea is that we need to meet in the middle. And the idea is that, you know, maybe data representation internally is one way, but the API of the data matches, you know, is compliant with the standard. And so that's one way. And then for the users to kind of, you know, nudge the data generator to generate data in a standard way, because it's time saving for them. I mean, again, if you talk to researchers, you know, there's so much time spent on aligning data, on making sure that you can map this to map that. So the standards is that kind of thing that you have to spend a little bit more at the beginning, but you see all the gain, you know, down the line. And so it's going to be the way I see it, it's going to be a combination of, you know, data generator understanding the important, data user, data consumers kind of asking for it, and possibly at some point, you know, the regulatory authorities might also get in, you know, into it, in part because as we, you know, this is sort of like a separate topic, but, you know, measures from wearables are more and more used as, you know, in clinical trials. And the moment you get into clinical trials, you know, regulatory agencies, you know, come into play. So it's a process, and we're here. So I don't know if I answered directly the idea. And actually, by the way, so just to say, pretty much all the big ones, they are aware of our work, because, as I said, OpenM Health has been around for a long time, and some have used it. Let's put it that way.
Thank you.
Thank you, Simona. We have another question from Handy Fernandez that is compatible with existing clinical codes. For example, logging, SNOMED.
Yeah, great question. So because there are some geographical differences in the use of this standard vocabularies. Actually, thank you so much for bringing up this question, because I realized I didn't mention. So the schema themselves do not make a choice, but in the standard itself and also on the website, we recommend that people associate schemas with the standard vocabularies that is most relevant for them. And we make some suggestions, which include SNOMED, LOINC, and then another project within IEEE, which is called 11073, that has developed also a list of codes. So because the choice is really use case dependent, so we make a recommendation without making a specific choice, because again, SNOMED has some geographical, limitations. I think LOINC is more like just a US thing. So in Europe, it may have other things, but definitely that adding a reference to the relevant code is important. And again, that's in the standard. Thank you.
So thank you, Simona, for your interesting presentation. I think the standardization is a very important step for we change the information. So thank you so much. And now I think we have to close. We have time now for a coffee break. And after that, we are going to return with another presentation. So see you.
Thank you.
Soon.
Thanks. Bye-bye.
Thank you, Simona. Bye-bye. Ciao, ciao. Hi again, everyone. Hi, Professor Mandiki.
Hello, good afternoon.
Good afternoon. So I'm going to introduce Professor Danilo Mandic, that he has been working with Signal Process in Imperial College London, UK, and has been working in the areas of statistical signal process, machine learning, and bioengineering. He has received 5 Best Paper Awards in Brain Computers Interface, runs the Smart Environments Lab at Imperial, and has more than 5,000 publications in international journals and conferences.
I wish
I
had 5,000, but I don't. It's 500.
Sorry, I put a 0 more. I'm so sorry.
Thank you for that.
500, but it's a lot too. He has received the 2000 Denis Gabo Award by the International Neural Network Society. And his work on hearables appeared in IEEE Spectrum MIT Technology Review and has led to several granted patents in this area. He will show how their current hearable systems that is based on the earplug with embedded electrodes, optical, mechanical, and temperature sensors can be hearable, used to measure the electrocephalogram, electrocardiogram, pulse, respiration, temperature, and behavior cues. The ability to stream narrow and physiologic data in real time makes hearables a viable solution for the integration with smart environments and in future e-health. So thank you, Professor Danilo Mandic. I'm so sorry for my mistake, and the floor is yours.
Thank you so much for such a nice introduction. Let's hope that it will lead to a good talk too. So can you see my screen?
Yes.
Okay. So, sorry, I lost my voice a little bit. Hope it will come back. So what is hearables? Hearables is a paradigm whereby you use sensors embedded on an earplug and inserted into the ear to record the neural function that is EEG and vital signs like ECG, respiration, temperature, and such like. So let me tell you a little bit what this is about. So when I think about this, I think a little bit about, so what is the challenge of for brain-computer interface in the 21st century? So if you look at this chap here, he's an elderly person who has sleep apnea, so he can't sleep well. So his life is really a living nightmare because he cannot relax, he cannot do anything. His family, his wife is also suffering because he can't sleep, and then he goes to hospital for diagnosis and perhaps treatment. So what happens there is that they put onto him this so-called sleep kit or a polysomnogram graph, and this is the EEG sensor, then EOG for eye movement, then this is for airflow, for ECG, respiration belt, and then data logger. So he's supposed to exhibit his normal sleep patterns overnight with this. I'm afraid he's not. And so he's most likely diagnosed suboptimally and also treated suboptimally. Okay, another interesting thing is, here's a concert for brain and orchestra. And this is work by the RIKEN Brain Science Institute, where I was a visitor. So what you're going to see is a conductor, the person in the middle. He's a PhD student in music. And he has an EEG cap. So he's imagining chords. And this is the visualization of those chords. So he's imagining chords, and then the system is detecting the EEG patterns, electroencephalogram, passing that to a MIDI system and creating chords. The chamber quartet are following. And this is a little bit on abstract music, but you'll see that they're playing completely in unison. So this is basically blurring the boundaries between the ability and disability. So we're going to see some visualization from brain patterns to the 4 chords is imaginary. So the classifier has 4 classes to the so-called piano roll, which is then blasted onto the MIDI and played by a synthesizer. Okay, so just stop then with this music and continue. So I hope that convinces you that with a little bit more convenient ways of recording EEG, we could really do much better. Because in this case, he's having an EEG cap. Look at that. So that is not really convenient, and he has to be seated. Now, how about bringing the EEG into the real world? So in that sense, we need to move from wearables, which are any wearable sensors, to hearables, which are sensors in the ear canal. So the current wearables are mostly based on the smartwatches which reside on the wrist. So when you think about this, you cannot record neural function from the brain on the wrist. That's not possible. The second thing is the sensors are not tightly fit to the wrist. Even for PPG, for respiration and such like, those measurements are not really very precise. In addition, in many activities like talking, walking, sleeping, running, whatever, the arms are moving relative to vital signs and neural functions. So that all poses difficulties. On the other hand, the head and especially the ear canal have a privileged position on the human body because the distance between the head and heart, lungs, brain does not change in most daily activities like sitting, talking, sleeping, walking, or anything else you do. So clearly, there's an opportunity to record all those data variables from the head because it has a privileged position and hopefully less artifacts. However, there's obstacles. The main obstacle is that in standard sensors, you would record from the normal position or best positions. For example, for the ECG, you record from chest, from EEG, from brain, and such like. For lungs, maybe wherever you want. But the propagation of signals from their source to the ear canal is subject to attenuation because you have all these cavities in between, like a windpipe is a cavity, mouth cavity, sinus cavity, which all attenuate the signal. So you're guaranteed to have interesting responses without movement artifacts from the brain, from the ear canal. On the other hand, the signals are going to be weaker. There's another thing that the Mother Nature has been very kind to us, and the ear canal actually has a very special electrical properties. So here's our simulation. Everything we do, we first simulate in the console multiphysics and then put our sensors forever and so on. So this is an MRI scan of a real head, and inside we put the all the tissues. So gray matter, white matter, pia matter, dura matter, cerebrospinal fluid, scalp, and all the rest. So each tissue has electrical and magnetic properties, and the console multiphysics software helps us to understand both propagation of the signal, which you'll see later, and also the artifacts. So for example, here's the external electric field in the form of a dipole. So what we measured was the attenuation of this field in the ear canal. So this is the depth of the ear canal in millimeters. This is the percentage of power of the electric field. We see after about 8 millimeters. So you have only maybe 2 or 3% remaining of the electrical field, external. So this external field is of course very dangerous for inconvenient for scalp wall electrodes, and you have to throw away those epochs. But for in-ear electrodes, clearly it's not an artifact. So because the ear acts as a Faraday cage of sorts, if you imagine the ear canal, it is surrounded by conductive tissues because skin inside is conductive. Then you have various liquids outside and so on, so that you have a real Faraday cage effect. Okay, so hearables. So the paradigm allows us to monitor the state of body and mind of an individual. So in our take on hearables, we'd like to monitor as many variables as we can, from temperature to body blood pressure to blood oxygen level to physical activity, movement, mental effort, stress, respiration, cognitive load, many other things. The first thing that hits you when you want to design new sensing equipment is the data acquisition. So this is the standard data acquisition device which we have in our lab. It is a GTEC device. It's got 16 channels which you can configure any way you want. It's manually operated and it costs about 10,000 pounds. But clearly, you cannot put this onto that elderly person that we had before. You cannot put that on this person and expect that they move with that in real life. Instead, you need something which is much more amenable to hearables. And indeed, if this is the evolution of the EEG recording, this is the standard EEG cap. And it takes a skilled person and a lot of time to put all those electrodes and check impedances and so on. This is the emotive one, which is more convenient, but of course it's not exactly well fixed. This is the in-ear one. So you can just insert the earplug yourself and you have all the sensors there. And with the advent of technology, you'll be able to monitor everything in a 24/7 fashion. Okay, so going back, so to bring the neuroscience into the real world, we had to invent our own biosignal recorder. So the first incarnation was this little device here, which we call the IAM, imperial amplifier. So it is operated of the coin cell battery. You can see it here. It has 8 channels, which can record EEG, ECG, and such like, and exactly the same resolution as this one. So with that, we can go into the real world. So this is our IAM. This is the envisaged electrode and electronics placement on the earplug. And this is our new device, which is called the BioBoard. So BioBoard is smaller than your palm. And it's a system which records biological responses. I'll explain a little bit more later. So the BioBoard has Bluetooth, USB port. It can record electrical biosignals, impedance, blood oxygen level, temperature, motion, and respiration rate, eventually blood pressure, and so on. So why is it so important? It's important because if you want to have electronics embedded on your earplug, then there's very little you can do in kind of modifying things in the development process. So you need some sort of evaluation board. And for us, this evaluation board became a standalone device. You can see it between 2 fingers. And you can see clearly the USB connector. You can record data from microphones, PPG sensors. It has accelerometer on board. It has a data acquisition device, Bluetooth, SD card, and power management, many other things. So in about half a year or so, we hope to be able to offer BioBoard to the international research community. The next thing is, people often ask, so how is it possible to record EEG from the ear canal? So again, we leave nothing to kind of chance or trial and error. So what we try to do is we try to have a model of everything we are doing. So this is a very simple so-called one sphere model of the head, again in COMSOL multiphysics. You can see head and ear canals. You can see 2 dipoles, parallel and perpendicular to the skull, and clearly the lines are the lines of the electric potential, electric field, and this is why you can record the EEG. You can see also those lines passing to the ear canal, and this is why you can record your data from the ear canal too. So we are out for a winner, definitely. So over several years and many tests and trials, we established the functionality of in-ear EEG. So this is to demonstrate electrode impedance. So we had 5 subjects who wore the in-ear EEG devices over the working day. And these are the median, I think, and impedances and their spread. So you can see that the impedance was never higher than, say, 12 kilo, which is still perfect, and usually it was between 5 and 10 kilo ohms, which is fine. So this is the auditory steady state response from the ear canal. So this when you play modulated sound to the ear canal and the brain demodulates the carrier, in this case 40 Hertz. So you can see that both the ear and the scalp channels have very good auditory response. This is steady state visual evoked potential with the light flickering at 15 Hertz. You can see a very nice 15 Hertz peak for ear EEG and the harmonic. For the master channel here, the actual peak was small, but harmonic was high, and this is what the central channel sees that. Okay, so I hope to have convinced you that the in-ear recordings are not only desirable, but also they're almost there. They're almost ready for you. There's many things you learn by doing biological data analytics and so on. So here's something we learned when we wanted to record sleep stage 2. So this is the EEG from sleep stage 2. We're talking about delta band in the EEG, but what you see is not EEG. What you see is some kind of interesting pulsations which have nothing to do with the EEG. It took us a little while to realize that these pulsations are basically artifacts coming from the hard shell and the sensor on the shell touching the skin of the ear canal. So because the ear canal has very tiny blood vessels which pulsate according to heartbeats, so we were able to pick up those heartbeats. So clearly, with this hard shell, it's maybe not good to look into this sleep stage 2 because you have artifacts. But hey, on the other hand, you can have pulse. So that motivated us to move on and try investigating about maybe some softer shells. So we went to the stress strain gauge at the materials department and examined many of those materials, silicones and hard and soft and so on, and memory foams, viscoelastic material. So we then converged to this medium in red viscoelastic material. This is stress versus strain. You're looking at things like Young's modulus and such. So and then this is this viscoelastic foam, which is soft. So when you insert it, you squeeze it, and then it conforms to the shape of the ear canal and relaxes. We also patented the electromechanical sensor, whereby a mechanical sensor, for us it was the MEMS microphone, was put beneath a soft electrode so that it can listen to these tiny blood vessel pulsations. So we can have pulse because the ear foam is soft, you would no longer have those artifacts in the EEG. So indeed, the EEG without those artifacts is there. Okay, we can now continue. There's many other things you can do with those microphones in the ear canal. And one of them is to do exactly what they're meant to do. Because in our prototype, we have 2 microphones. Again, for us, it's a micromechanical transducer. One is pointing upwards, the other is pointing outwards. So if somebody is reading text with a similar microphone, this is the external microphone in front of the mouth. It was the best of times. It was the worst of times. It was the best of times. It was what the middle of the world. It was the impact of the similar of the impact of the spring of hope. It was the winter of despair. That's right again. It was the worst of times. It was the age of wisdom. It was the age of foolishness. It was the impact of birds. It was the impact of. So clearly, this is the external microphone in front of your mouth. This is what happens here. So this is pointing towards the side of the ear canal. It was the best of times. It was the worst of times. It was the age of wisdom. It was the age of foolishness. Pretty good. And this is the microphone pointing inside the ear, towards the eardrum.
It was the best of times. It was the worst of times. It was the age of wisdom. It was the age of foolishness. It was the impetus.
Okay, so what you can see is in time versus frequency. Time frequency, that this is the original speech, and you can see that wherever there's consonants and vowels, there's kind of burst of activity across the spectrum. While from the ear canal, from microphone, you cannot see those activities like here, because the signal is low pass filtered. So clearly the tissue, human tissue, acts as a low pass filter. Okay, so what else can we do? So we can monitor fatigue. So I promised to talk about kind of doctorless hospitals. So I'm just gear shifting to various modalities. So this is my student who volunteered not to sleep overnight to be fatigued. So we looked at, he was doing some computer kind of puzzle matching game, and he was getting tired over time. So he was making errors. So error, many errors, 3 errors, 2 errors, 3 errors, and so on. So it's well known that the fatigue is demonstrated in the elevation of the alpha rhythm in the EEG, around 8 to 12 hertz, something like that. So this is the alpha band power for scalp EEG. So you can see whenever he was making errors, you had elevation in power over the baseline, the red broken line. When he was making many of those errors, there was quite a lot of alpha power. This is the same from the ear canal. So you can see that from a simple earplug equipped with the EEG sensor, you can clearly monitor fatigue in an unobtrusive, discrete way, self-administered, and also over many hours. Okay, so going back to this lovely chap who is suffering from sleep apnea, we recorded scalp EEG in red versus sleep EEG for him. And you can see that for sleep scientists, you can see that, for example, delta, which is deep sleep, these are the delta waves from ear EEG, delta from scalp EEG. They're never going to be the same, of course, because it's different site and different propagation, but still you can have perfect delta. This is the so-called K complex. It's the theta activity from ear canal, theta from scalp, alpha from the ear canal, alpha from the scalp. So clearly you can use the in-ear electrode for sleep studies. And we have done many sleep studies, and we had really fantastic match between the ear EEG and scalp EEG. So the next thing towards doctorless hospitals is ECG. So electrocardiogram is normally monitored from chest, and there are 3 leads normally. One is horizontal, the other is diagonal, 3 montages here: horizontal, diagonal, and vertical. So to show that we can record ECG from the ear canal, we did the, again, multi-physics simulation, this time on the MRI scan of the upper torso. So we had this kind of real body shape with all the organs. So we inserted electrical and magnetic properties of every single tissue, including oxygenated blood, deoxygenated blood, gray matter, white matter, lungs, cartilages, bones, everything. This is what happens. So look at here. So this is the below and above direction simulated. This is the left and right, and this is the front and back. So see, as the time goes, the heart muscle or the heart vector is rotating, and around the R peak here, you can see R peak, the heart muscle fires. And you can see clearly the high potential difference on chest at the position of the R peak. So this kind of peak in the ECG. So what is interesting is that you can see the same from the wrists. So which indicates that you can record ECG from the wrists. So indeed, in the last 8 years, students in my courses have been recording their own ECG from the wrists, and they've been passing their exams based on that. So maybe 3 years ago, when Apple launched the smart ECG watch, whereby you bring a finger of one hand to the crown of your watch, which is insulated to the other hand, and you can record ECG. So clearly, they're doing exactly the same. recording basically from the wrists. Okay, so with that, let's finish the heart cycle. You can see the heart vector goes in 3D, and now there's depolarization, but you can see little lines here around the ear. So clearly, maybe it's possible to record ECG from the ear canal. So to do that, I'll just cut the story short, because with our mechanical sensor beneath the elastic electrode, so we can record so-called mechanical platysmogram, which is pulsations of the small blood vessels in the ear canal. So this is the NPG, mechanical platysmogram. And clearly, because the electrical signal is fast, so the hair fires first, and then a little later, the wave of blood comes to the ear canal. So the in-ear kind of mechanical activity or blood vessel activity is delayed with respect to the electrical one. So this helps us a little bit to locate in-ear ECG. So what you'll see here is the chest ECG versus in-ear ECG. It's a bit compressed. So you can see that the chest ECG has amplitude about maybe 1,000 of some units, while ear ECG 20 of some units. So it's 50 times smaller amplitude in the ear canal. And of course, it's smaller because the signal propagates through all those cavities that I explained, the windpipe, mouth, and sinus. However, we have also seen that the artifacts in the ear canal are lesser than those on the outside of the body, because not only because of the Faraday cage effect, but many other effects. So when you do little processing, little averaging of those cycles, this is the average cycle from the arms and the average cycle from the ear canal. You can see the striking similarity between the two. So now we can record ECG from the ear canal. So these are discoveries, of course, all by my team, and if you Google my website, you will see those publications related to hearables. What is interesting is then, here's another, a little more primitive simulation of the propagation of the ECG to the head. You can see the lines of electrical potential, and then between the two sides, obviously, of the head, you can record ECG. So what you see here in black is the ECG recorded from two conchas. That's the outer part, cartilage of the ear canal. And you can see very beautiful ECG, obviously. So this is from the arms. You can see beautiful ECG, and you can see that kind of sine wave on top. That is respiration. So this kind of waving, that's respiration, because the ECG is modulated by respiration through a phenomenon called respiratory sinus arrhythmia. This is the same signal recorded from two conchas. You can see that the signal is noisy, as we said. The R peaks are still there, and you can still see the sinusoidal movement. So you can detect respiration from the ear canal. Now, if you remember the elderly chap we mentioned on slide 1, he had the respiration belt here. So this is the respiration recorded from respiration belt, and this is respiration demodulated from the ear canal. You can see it's exactly the same signal, just opposite sign. So we can get respiration from the ear canal for free. So now I've been through EEG, ECG, MPG, mechanical platysmogram for arterial health respiration. Let's see what's next. The next thing is the blood oxygen saturation. So recently, in 2020, we found a way to use a PPG sensor from inside the ear canal to monitor the blood oxygen level. So this SpO2 is a variable which is derived from the PPG wavelengths and amplitudes and so on. And it corresponds, it's a proxy to blood oxygen levels. Of course, it's very, very important for current COVID situation and so on, where people are deprived from oxygen. So we had several participants, and my student was basically asking them to, in the pink areas, to hold breath. So the blue is the blood oxygen level, SpO2, from finger, PPG sensor on the finger, and then the red is from the ear canal. So anything below 94 is dangerous. Okay. So normal levels are 96 to 98 or something like that. So you can see that in red, the in-ear SpO2 was a little bit lower than that from the finger, and I'll explain why. But also it responds because, of course, if you hold breath, then you have less and less oxygen in the bloodstream. So you can see that the minimum of the blood oxygen level is reached much quicker from the ear canal than from the finger. And that's because the proximity of the ear canal to heart as opposed to the finger. The second thing is that which one is more accurate? So we argue that the measurement from the ear canal is more accurate because of the lack of vasoconstriction. So vasoconstriction is a phenomenon whereby when your body skin is exposed to the outside temperature, so our temperature at 36, 37 outside, it's never that much. So it's 20, 22. So the blood vessels constrict. So when you bring a PPG sensor, which is optical, then the measurements are biased. While in the ear canal, of course, it's not exposed to the external temperature, especially when you put an earplug. So those measurements are much more accurate. So this is our earplug, at least the way it's going to be. With the electronics, with the PPG sensor, the hook around the concha, you'll have later some EEG sensors and so on. The next thing we examined was the cognitive load from in-ear PPG. And because the brain is the most active metabolic organ in the human body, and these are the blood vessels around the ear canal, some of them leading to brain. So in a way, very similar to fMRI, where some area of brains gets activated and then the oxygenated blood goes to those areas. So we can see red, 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 according to some activity. We hypothesized that you could actually do something similar using the measurements of blood oxygen level from the ear canal. So indeed, based on our in-ear PPG sensor with those SpO2 measurements, and this is our sensor, we're able to classify cognitive load in so-called N-back tasks, which is when the subjects are asked to remember several of the numbers which are passing on the screen in front of them. So the numbers you want to memorize are several steps behind. So the N3 task is harder than N2 and so on. You can see the confusion matrix. You can see that the accuracy of classification of mental tasks. So you want this to be diagonal, and it's very diagonal, is very, very good. Okay, now that I've finished off that, maybe just a little time to talk about artifacts. So I know that I have altogether maybe about 40 minutes, so I'll need maybe 5-6 minutes more. So for us, no data is bad data because we don't want to throw away data. So these are some of the ideas. So this is the EEG after while somebody was drinking Coca-Cola. This is the EEG when somebody is clenching their jaws. EEG when somebody was eating sweets. EEG when somebody was chewing on broccoli. So clearly, each type of food produces a very distinctive artifact. So if we were able to somehow remove those artifacts or learn from those artifacts, then we would have some behavioral analysis for free. And then we wouldn't have to throw away epochs of bad EEG because the artifacts would be, the data would be with artifacts removed. So to show that, consider this electrode signal. So this is the EEG, while a person was sitting in blue, reading in red, chewing in amber, and walking in purple. So basically what happens is when you chew or do some other activity, move your jaws, the earplug moves relative to the ear canal. That's so-called motion artifact. Those are very, very nasty artifacts, and you would normally have to throw away all the epochs with such data. However, we have our dual multimodal earplug with the microphone and electrode. So of course, this is just a concept. So electrode goes down and we listen through the electrode. So this microphone will pick up any mechanical activity related to the movement of the earplug. And indeed, see the similarity between the microphone signal and EEG when the earplug is moving. So we are going to use this as a reference in an adaptive signal processing configuration to remove artifacts. So indeed, so this is the situation for the chewing artifact. So the EEG data with chewing artifact are in blue. Look how nasty they are. And this is the power spectrum of EEG data with chewing artifact. So quite high artifacts. The amber is background EEG. So after digitally removing in real time online the chewing artifact with the help of the reference of the microphone, you have the signal in amber filtered. The baseline is blue. Filtered signal, which is more or less same as the baseline. So we have totally removed the artifact in real time, and we don't have to throw away the epoch of EEG. And here, so see in blue the electrode with artifact signal, and in red the denoised data. It's perfectly valid EEG. Okay, so here we. So we're almost at the doctorless hospital stage. So hearables allow for unobtrusive, discrete, convenient, self-administered way of recording EEG and vital signs. So we have been working in this area for 10 years, and all of the research I've shown or the results in this presentation is from our team. So please, of course, visit our website for more information. It's not exactly up to date, but I can improve it. With hearables, what you improve on is wearability, because clearly this is the mock-up of the electronics and there's a battery and such like. So clearly you can wear it, you can insert it by yourself and wear it for long periods of time. So you're not depending on the lab. What you lose is a little bit of performance, because clearly the spatial resolution on the EEG cap standard is higher than in-ear EEG, but then it takes a long time to put this together, to mount this on a person's head, and by which time the person maybe loses interest. So this is a very, very interesting direction to go, I believe. There's many other things in my team are exploiting now. One of them is monitoring of chronic diseases and target medication delivery. So everybody takes some pills for some chronic disease, but everybody's body reacts to medicines in a different way. So with the hearables, you can record the EEG, ECG, pulse, respiration, many temperature, many things, and understand how, in a very personalized way, how somebody's body reacts to the prescription, dosage, and you can adjust dosage and prescription accordingly. So you can envisage a health monitoring system based on hearables, where the data are transmitted to some smart device. The smart device can analyze them, and maybe if you're not feeling well, you just put an earplug and go for a coffee. In 10 minutes, the earplug will record everything that you never record normally at the GP. The respiration, pulse, temperature, ECG, blood oxygen level, EEG, and that will be streamed to a smart environment, which will decide then if you need to go to a specialist. If you have to go to a specialist, you can then bypass the GP and the system can book you to a specialist automatically. Or the system made things that you are perfectly fine. Okay, so this is more or less everything I wanted to say today about hearables. Our hearables are comprehensive and have acoustic, electrical, optical, and inertial sensors with all sorts of modalities and capabilities, from identity, so biometrics, so cybersecurity, to behavioral analysis, progression of disease, health monitoring, sleep diagnostics, brain-computer interface, dementia, aging, and many other things. So more material are maybe present in some of our publications. And with that, I'd like to thank you for the opportunity to talk today. And I'll be happy, delighted to answer some questions. Thank you very much.
Thank you so much, Professor Mandiki, for your interesting presentation. And so now we have some questions from Hendy Fernandes. He asked, does the hearables device interfere with the wearer's hearing?
Yes and no. So, because it is motivated initially by hearing aids. So, if you have a solid earplug, like memory foam, then of course it blocks your hearing. But you can also have an air duct. You can have a hole in the earplug, like in those customized earplugs, or even soft earplugs, so that the hearing is not interrupted. So both ways is okay.
Okay, another one. No, I think open. Okay, I have a quick one related to the breathing signal. How is the accuracy of the results that Professor presented today?
So just regard to the respiration, yes?
Yes.
So let me then go back to my presentation. Maybe that's the best way. Share screen. So respiration is with a very, very high accuracy, obviously. You can record respiration in many ways. So I didn't want to go into detail here, but from the microphones we have on the hearables here and there, they record just about anything that comes to the ear canal. So again, this is time, this is frequency, and the vertical lines are inspirations and expirations. So this is the slow respiration, this is the fast respiration. You see, the vertical lines are in and out. And when you integrate that, you can have very nice respiratory signal like here or there. So that's one way. So the second way would be from the respiratory sinus arrhythmia, which is basically the envelope of the ECG, which is of course modulated by respiration, both from the chest or arms and the ear canal. You can see the amplitude of RP goes up and down, which is due to respiration. So if this is the respiration from a chest belt, like here, and these are respiration from arm and concha, they're the same. It's the same signal, the same periodicity, just different phase. So this goes up, this goes down, and likewise. So it's just times -1. So very, very precise respiration indeed.
Okay, I think Carlo Massarani has a question.
Yeah, thank you, Professor Mandic, for the very interesting presentation. Yeah, I'm interested also in the respiratory signal, and I'm curious to know if you have tested the device during high-intensity sport activity, where the breathing sound should be higher in the and much more. It should be easy to distinguish from the external environmental noise.
So the answer is, I'm just trying to stop sharing. Somehow something is stuck. Because I would like to see who is asking me, and at the moment, now it's better. Okay, so yeah, the answer is yes. So the student of mine who is working on blood oxygen level and so on, he's competing in weightlifting. Okay, and weightlifting is good because they're not running, they're not doing many things, they're just stationary and lifting heavy weights. In his case, he's lifting 310 kilos like that, and I don't know. Wow. So clearly there's many patterns of respiration, because there's also holding breath and exhaling very, very suddenly and inhaling and preparing for lifting, where you have to breathe in certain way to oxygenate yourself. So in all those cases, obviously, this is working very, very well.
And just one more question, but without like a aerobic physical active, did you try something like that or no? Like a cycling, running?
Yes, so we are currently undergoing many trials with the army partners. So they're looking at fitness of soldiers, and they're running on a treadmill with our devices. So that's ongoing.
Okay, thank you.
I can't tell you. I mean, I think it'll be good. I just can't tell you right now how it's looking like.
No, okay. And I think we have time for one more question. Let me check if, but maybe how near, Professor, are you from provide this for kind of commercial prototype or commercial, like to sell this, like have this in market?
But that's a good question. So we are closing to that stage, and so we are hoping that the hearable with everything we have will take a little bit of time, not too much. But we are almost ready with in-ear PPG and also in-ear EEG. Yeah, so I think that we are in the process of kind of setting up something for in-ear PPG.
Okay, I think we have to finish. Thank you again, Professor Danilo Mandicchi. It was a very interesting presentation. And now I would like to invite the General Chair of the conference, Professor Carlo Massaroni, and I'm finishing here. Thank you, guys.
Thank you very much. Pleasure talking to you, conference.
Thank you, Amanda, for chairing this last session. Unfortunately, we have to close this today's workshop. Let me share the screen. Okay. Yeah. So it's a great pleasure to present the closing ceremony of the IEEE WSAIM 2021. As you probably know, I'm Carlo Massaroni, one of the general chairs, together with Professor Bonato and Professor Varadarajan. I'll start with just some numbers, some statistics of this edition. Then I leave the floor to Professor Varadarajan for some greetings. And lastly, I will provide you some information about certificate of attendance, registrations,